Okay, so if you want to be able to read electrical diagrams, then this is a very good training program that I'm allowing you to have for free here on YouTube. That was a paid program that went over the course of 5 days. And this is a real world control and automation project that was brought to me by an electrical contractor. So this is real stuff, and this is a real world project with real schematics. And yeah, by the end of this training, if you actually go through it, you're going to understand how to read and interpret electrical schematics. You're going to have a very solid foundation in electrical controls, and you're going to get a big picture understanding of how control and automation systems work and how they're put together. Now, before you go through this training, I highly encourage you not to binge watch it, like to actually actively learn and engage with it. And to do that, and to enable you to get the most out of this, so you can understand the schematics, so you can understand control systems, so you can advance in your career or business, you need to have the schematics. So I strongly encourage you to download those schematics, and to get hold of those, click the link in the description. You'll be taken to our free community, and the first thing you'll see in there is the schematics for this video, for this training program. So go and do that now before you get into the video. Download the schematics, and it will just make this whole learning experience so much better for you. So click the link in the description now, pause this video, go and download the schematics, and then come back. Right, so hopefully you guys have got the schematic up in front of you there. So first things first is this line that I want to draw your attention to. So this line here, you'll see it on every page. That is the divide from what's inside the panel and what's outside the panel. And just a side note, guys, not all schematics are drawn the same. Like there's differences on how the designer designs them, their preferences, what makes sense to them. Different softwares, like if you're using automated software, they sometimes draw them differently. So there's always, like, even for me, I've seen hundreds of schematics in my time. Even for me, if it's laid out in a particular way, it does take a bit of time just to sort of get to grips with how the designer has designed things before you can start piecing things together. But it's not necessarily how things are designed and laid out. It's understanding how it works. That's what's important. So you will see differences between schematics, but if you understand what's happening and the logic and the controls and the philosophies, then you'll be good. It just takes a bit of time to sort of get your head around how the designers design things. So over here is everything outside of the panel, and everything this side of the line is inside the panel. So outside, inside. So who can tell me what sort of supply this system has? You'll have to unmute yourselves.
Single phase 50 hertz 230.
Exactly that, yeah. And what we've got basically is we've got our supply coming into the panel, right? And then the first thing that it gets to inside the panel is what? Someone tell me.
Isolator switch.
Isolator switch, yeah. And I don't know if you guys have looked at the photos within the shared drive, but that's basically the switch on the outside of the panel, and then the shaft goes into the actual disconnector switch at the top of the panel. So that's what this is. So it's we're putting the line and the neutral through that, and this can get a little bit confusing because the way things are drawn in schematics aren't always the way things are wired physically. So that takes a little bit of getting your head round. And like, as someone who wires a panel, you can wire it in different ways. You don't have to wire it exactly as it's been drawn in the schematic. It might make more sense to wire it in a different way when you're actually building the panel or wiring the panel, but as long as it does the same thing as what's drawn in the schematics. So we've hit the main disconnector switch. Sorry, pal, I can't help you at the moment, mate. You should be on page 1 of the schematics within the shared drive. So let's focus on the line, or L1, to start with. So now what we're doing is we're then distributing that 230 volts that's come in through the door isolator, and we're distributing that across the system. And you'll see that horizontal line at the top goes across all the pages. So we look on page 2, right at the top, it's going across there. So, and you can see, let's choose someone. Daniel Mason, my friend. What is coming off L1? You're muted, buddy. Looking for the unmute button. Ricky, I'll come to you instead, mate. What is
Transformer and circuit breaker.
say that again, mate? Transformer and
Other circuit breakers, laptop socket.
oh, cool. Circuit breakers, yeah. That's the first thing that's coming off. Cheers, Daniel. So how are we distributing that power to those circuit breakers? Someone tell me. Any electricians should.
Sorry, can you please repeat, Chris? What did you ask?
Yeah, so how are we distributing this power from the main isolator switch to all of the MCBs?
By a bus bar?
Exactly. It's exactly the same.
From the terminal rail, sorry.
That's right, mate. It's exactly the same as we see in a consumer unit. Any consumer unit, any electrical installation, bus bar. So, well, firstly, we've actually got a 10 mil cable going from the main isolator switch to the bus bar and the first MCB. And then obviously it's being distributed across all the MCBs like we've got like the feeds in a consumer unit. It's exactly the same thing. So that's what we've got distributing all of that 230-volt single phase across the whole system. And obviously they're going, and then that's going via MCBs. And then in terms of the neutral block, I've just told you, haven't I? With the neutral, we're doing that via a neutral block. So again, if you look at those photos, you'll see that there's a neutral block in there. So let's work our way across. So the first MCB we've got here, MCB2, it's a D-type, 6 amps, and that's feeding the primary side of our transformer. Okay, and then we got the neutral here. We'll get to the secondary side in a sec. I mean, this is probably all pretty basic stuff, certainly if you're a Sparks. But yeah, I'll just quickly go through it anyway. So MCB3 is just going to our laptop socket. MCB4 is basically the feed. Well, it is not basically. It is the feed going to our gas detection system. Basically, if our panel is live and switched on, and providing the MCB hasn't tripped, and you can design it in different ways, but it's just easier. If the panel's on, then that passes power to all the field equipment as well, certainly that has like a 230-volt constant feed. So yeah, you can see that goes via the MCB and then to terminal block 1, and then we typically have you should have a local isolator to all of your field equipment as well. So those are the 230-volt MCBs done. So let's just finish off those circuits, and then we can get into the controls. So transformer primary side, laptop socket. We've got our constant power going to our gas detection system, and that's it on that page. Now the controls is now starting on the secondary side of our transformer, and you can do this whether you want to use an AC transformer or you want to use a DC power supply. Doesn't really matter. Typically in most BMS systems you'll see a transformer being used. What we're doing though is we're just stepping down. You're not going to do controls with 24 volts AC because it's a dangerous voltage, especially again if you go back to the photos, the images in the shared drive, you'll see that there's a lot of switches and lights on the panel door, like for status and some control. We don't want 230 volts going to the panel door. That's potentially dangerous, can potentially cause issues. That touch voltage of 50 volts. That's why we're basically stepping it down, just safety really. I'll try and keep an eye on the chat, guys, but it's a little bit tricky. I'll catch up in a bit on that. So so on the secondary side of the transformer, we got our 0 volts, and that's just there's not much to it. That just sort of runs throughout the whole system. So we got our 0 volts, and that's how we distributing that 0 volts. Ryan Mounts. Oh, you've already talked, haven't you? But you can tell me again, mate.
Yeah. Sorry. So that's 0 volts, you said, yeah?
Yeah, how are we distributing that from the transformer? So we can.
Yes, that's going into our first relay, isn't it? So R1, 2, and then you got a second relay. Is it R2?
It is, yeah. It
Yeah.
is, but it's not. So this is when I said how we wire things isn't like physically wire things. It isn't necessarily how it is exactly within the drawings. So it's only you can only really the answer to my question really can only be found out if you look at the images. Basically, what's happening is I'm taking a cable from the 0 volts from the transformer and I'm wiring that into terminal blocks basically, or another little mini buzz bar. It doesn't really matter. But we're doing exactly the same as what we're doing with the neutral block, with the buzz bar of the live. We're doing the same thing for the 0 volts as well. So if you look at the photos, you'll see that I think I've got like, I don't know, it might be 6 or so Wago terminal blocks with a little plastic push buzz bar in there that's basically distributing that 0 volts. And then I can have more cables coming out of those Wago terminal blocks going out to, like you just mentioned, Ryan, the A2 side of the relays. Because can you imagine if I just took one cable from the transformer and then just daisy chained it all the way across all of these devices or bits of hardware, and a problem happens and they're all in series, it's just gonna take everything out basically. So it makes it easier to wire, and there's like redundancy in there as well. So that's kind of what we're doing there. So yeah, that's what we're doing on the 0 volts. Yeah, so now let's go on the 24 volts AC. So on the other terminal of the transformer, we're going, firstly, single cable, we're going to an MCB or a fuse. That's the first thing. And then we've got our 100 circuit. So we're going to start labeling cables now so we can identify them. Typically, you just label them the same on both ends. Simple as that. So, and any time that you see these black dots, it's either we're distributing that, whether it's a power, whether it's controls, whether it's 0 volts, we're either distributing it or we're daisy chaining it. If there's only this will be more clear later on. If there's only like a couple of bits that are connected to that one circuit, then I might just choose to do a little daisy chain. It doesn't make sense to use up DIN rail space in the panel when actually, it's just a couple of terminal blocks that we're going to. So it kind of comes down to the panel builder really to how that's distributed. But you can see straight away, the first thing that we go to is that light on the front of the panel. So, Jake Ward, tell me the control philosophy. I'm complicating things by adding philosophy in there.
Right.
But tell me how that light operates.
So it's picking up the 24 volt from your MCB one and your 0 volts from the outgoing from the secondary, from the 0 side of the transformer.
Yeah. So what's that telling us?
So that's telling you that your 24 volt supply for the panel is essentially healthy.
Yeah. Basically right with what you said. So it's the 24 volt supply for the controls. Yeah.
Right.
So that's telling us that our transformer is working. That's telling us also that the MCB hasn't tripped. When that's on,
right, yeah,
that's telling us that's giving us a visual representation on the front of the panel that the transformer is good, which means that all the rest of our downstream should be good, unless there's obviously issues with those individual bits of controls.
Right, yeah, I see what you're saying. So be a bit more descriptive. Yeah.
Yeah, but bang.
Yeah, fine.
So that's the first thing that's happening. Who can tell me, Danny Hitchcock, what's the second thing that's happening?
It's putting the 24 volts down to The safety circuit lights, gas valve.
Not quite, mate. Look.
The top where sorry.
No, you're right, mate. So the next thing along, the next rung that goes vertical from that healthy light, what's happening? What's it going to?
The test lamp.
Yeah. Now I'm saying things like, oh, the first thing, the second thing, the third thing. Obviously, this is all happening at the same time, but just as we're working through the schematic, it's easier to sort of break things up. Because obviously, as soon as the transformer's live and firing up, then all of these things are made live at the same time. But yeah, you're right, mate. So the next thing we're looking at is that rung going down here, and this is going to our lamp test button. So this is a black push button on the front of the panel, which is normally open. If you look closely, there's a gap there and there. So it's normally open push button, which means, Danny, tell me what the next thing that happens once power's gone there. We press that button. Then tell me what happens.
Puts power down to the safety circuit failed lamp, gas valve closed lamp, and the gas valve open lamp.
Yeah.
So they illuminate.
And what's the name of that, or what number circuit is that? How are we identifying that? And what is the identification of that circuit? I'll have to zoom in a bit.
Circuit.
The 400, is it the numbers? The 400.
Yeah, exactly. So everything then that goes from so we got our circuits that are coming out of the MCB over here are 100. So everything up until it gets to a point that's different. So ultimately, basically, this is the same circuit. This is all the same circuit. Everything is on that 100 circuit there. And then once we go through something, whether it's a light, whether it's a switch, whether it's a push button, contact, whatever, then it changes and then it's another circuit. We identify it differently. So now it's the 400 circuit, and as we press that button, like you said, Danny, we're sending that power now to the safety circuit failed light, the gas valve closed light, and the gas valve open light, and we're also distributing that circuit across all the other pages where there's lights as well. Who can tell me, why do we have that little control circuit in there? Someone tell me.
So you can identify when the lamp fails.
Yeah, it's pretty simple stuff. It's just a quick test to see, are all my lamps operating as they should do on the BMS panel? Because if we're pressing that and one of the lamps isn't coming on, then how long has that not been coming on for? There could be a problem, that we haven't identified. Now, it should also, the light indicators on the front of the panel should also, if it's a modern panel, should also be doubled up with a PLC input as well. So we should also know through, like a HMI or an email or a text message or an app notification that, something's happened. But that's just like, like you said, Matthew, just allows us to do a quick test to make sure that visually, like engineers on site can see, or users on site can see the status and make sure that things are, or the lamps are working as they should. Right, so let's now have a look at the gas detection system. What's the time? We've got 20 minutes. Okay. So now we're going to get into the controls. So the gas detection system, ultimately, I'll just give you a quick rundown of basically what it says. It says in the manual. And guys, this is a massive thing, and it's so important. Like people think controls people, not everyone, but some people think that electrical controls people and people that do all this stuff with panels are like wizards. We're not at all. We just make sure that we read the manual. Like as soon as you read the manual, you can understand how any piece of equipment is controlled, how it works, what you need to do to make it work. pieces of equipment individually. Obviously, when it comes to like the controls of it and the design and the logic, that's a little bit different. But in terms of understanding how a piece of equipment works, everything has a manual. I'm sure some of you have heard the expression RTFM, read the fucking manual. So that is massive. That is like, if you're going to take one thing away from today, if you want to progress into doing like controls, you've got to read the manual, because you're never going to be able to understand a system or piece of equipment, how to design a system around that piece of equipment if you don't read the manual. But let me give you a quick sort of rundown of that manual. Basically, and we talked about it earlier, the safety circuit, like the run enable circuit. Basically, what we got is this gas detection system here. It's looking for the circuit here, and we'll go into a little bit more detail in a sec. It's looking for a closed circuit. It's looking to see that circuit's closed. And once that is closed and healthy and good, it opens this gas valve. Basically allows gas into the system. Obviously, if there's a problem, gas and ignition sources, and if there's problems, basically we don't want gas going into the system. So that's what that does. At the same time, we've also got two relay outputs that I think we can, I can't remember off the top of my head, but anyway, we've got them set up. Whether you can configure them or not, we've got them set up. One just as a generic fault output. So that will tell us, that will tell us basically if that EM stop circuit, emergency stop circuit, is healthy or unhealthy, if it's true or false, if it's on or off, if it's 1 or 0. That's what that does. And then this operates, the gas on off operates in the same way based on the status of that incoming gas valve, if I remember correctly. It will make more sense as we go through it. So just going back, so what we've got here, this is our run enable circuit. So all these things, all these circuits are in series. So what we've got a little supply. So the actual voltage and supply is coming out of our gas detection system. So let's just say, for argument's sake, it's 24 volts DC. It probably isn't. It's probably something much lower than that. But let's just say that it is. So that comes out here. This is our positive side. And now again, you can wire this however you like, whatever makes sense to you. Like, you could have just come straight out of this EM stop straight into the things that are in the field. I thought it would be better, and it's more flexible to wire it this way. So we're coming into the panel on terminal block 7, and then we're basically just creating a series circuit with the other devices in the field. So the first device is our panic button, our e-stop. And you can see that it's in a normally closed state. So if no one's hit that, that allows that power to continue through here. And then I've designed it to go back into the panel, terminal block 9. Cheers, Mohammed. Into 9, and then I'm just doing a link here to keep it in series. And then we're going back out the panel on 10. This 24 volts is continuing. And then we've got our thermal links above the boiler. And again, you'll see that they're in a normally closed state. Okay, so if both those boilers, boiler 1 and boiler 2, are healthy, there's no fire, there's no heat, that just sends that signal, that 24 volts, ultimately a signal. Like, the voltage doesn't matter, it's just a signal, on or off, true or false, back into the panel. And then I've just got a link wire going back into terminal block 6, which then goes back to the gas detection system, pulls it to the negative. Pulls it to the negative. And this has probably got a little internal relay. So we're actually basically energizing a little coil in this gas detection system. And then what happens is, as you can see here, like I was saying earlier, we got our contacts, and we got that's a normally open contact. we got our normally closed contact. So there's going to be both configurations in there. I've chose to use the normally closed on our generic fault. So basically that then, so the coil is energized. It then closes that contact. So it closes this, sorry, it opens that. So it was like that. Now it's cut that power. So, and like I said, like on the contact, on the common side, we're feeding it. So we're actually feeding it from our panel, our 24 volts AC. Bear with me, guys. It would have been easy if I for this at least, if I made this normally open, but it doesn't matter. It's so yeah, it goes through here, and then it goes back into our panel, and it energizes R1. And this is how you'll see a relay or a contactor drawn in a panel. So it will just be a square box like that, and it will have A1, which is the positive side of the coil, A1, A2. If you see that, that's indicating that it's the coil side, and obviously it's a box as well. So that two things to tell you that it's the coil side. A1 is the positive, and then this is the negative, as we can see here. The negative just goes to that 0 volts that we got distributed across the panel. So that means the 0 volts we don't need to worry about. That's not really important. But we've energized or de-energized this relay 1. And how I've done it is R1 relay 1 /2. So that /2, again, different designers do this in different ways, but that /2 is saying that there's 2 poles on that relay. One pole is here, so we can see here relay 1, pole 1 is over here, and we get to this later on, but one of the other poles, I won't spend too much time looking for it. Oh, there it is. The other pole of that relay is feeding into our PLC. But that's not important for the time being. We're just focusing on pole 1. So what happens is we've got our constant 24 volt supply over here. So let me just get my head around this and remind myself. And sometimes it's not until you get on site that you might have to invert the way that a relay or a piece of equipment is wired. So it might be that when we get to site, I had to wire that normally open rather than normally closed. Like, you never know as a designer until you're actually on site. So sometimes it might just need inverting, but the principle is if this circuit over here is healthy and good, then what we're doing via that coil of the relay is, if things aren't good, we're sending the signal down this way, bringing on the circuit, safety circuit failed. So if someone's hit the panic button, if the thermal links have triggered, broken, that brings on the safety circuit failed light. But if everything's healthy, then it goes from, so this is the normally closed side of the contact, it goes normally open, and it sends that 100 circuit, which is now 200 circuit because it's gone through a contact, it's changed, and that's then our safety circuit. 200 is our safety circuit, which then goes off to feed other things in our system. Any questions on that, guys?
Sorry, see for when obviously your relay, your R1 pole 2, I'm assuming that then it gets, when it's not healthy and obviously the safety circuit failed, the light comes on, I'm assuming that signal comes from the PLC.
No, so the PLC is irrelevant at the moment.
Right.
So what we got this signal, this power here, this 24 volts AC.
All right, no, I get it now. Sorry, yeah, I can see it.
No, you're right, mate.
Sorry.
You want me to run through it again?
Yeah, go on, mate. Yeah.
So we got that constant 24 volts. It's going through like an internal relay on the gas detection system. So if everything's good or everything's not good, healthy, unhealthy, it's hard for me to explain like in terms of the way it functions. But if everything's healthy, then sends that signal here. So that 24 volts, and this is a 24 volt AC relay. So this is an important thing, guys, to make sure that the coil of your relay matches the control voltage. So this 24 volt AC relay is then energized, which then over here, it changes that contact. So in one state, it's going this way. When it's unhealthy and not energized, it's sending that same 24 volts this way to this light. But if everything is healthy, this is energized. This is a circuit which I think it's not. When we get onto another circuit, it'll be easier to explain because we won't have normally closed can make it harder to explain and less logical. But when it is energized, that then switches from the normally closed to the normally open. So that's no longer on, and this safety circuit is enabled, and then we do things later on in the drawing off that. All right, Alec?
Yeah, mate, I get it. Yeah.
Cool. Okay.
Thank you.
All right, mate.
So I've got a question.
Yeah, go for it, man.
I'm still confused about this contact at the bottom that says it's normally closed. It's normally closed means that EM stop, there's no power coming in from EM stop thing, and it is closed. So this coil R1/2 is energized, meaning the contact on top that's going to the safety is like, even if EM stop is not energized, the circuit would still be working. So shouldn't this contact be normally open?
Yeah, this isn't the best one to start off with when trying to explain, actually, to be fair, guys. I want to get to a normally open one because then it'll be easier to understand. Like, for example, let's just focus on this one. So we've got our supply voltage going in, and then let's say there's a fault. So at the moment we're just sat here, and this is a normally open contact, right? So everything's healthy, and this is the pump, by the way, but don't worry. No, this is a boiler. Yeah, boiler. So this is like the fault signal from a boiler. So we got our constant supply from our 24 volt AC, and it's just sitting there at that contact, right? And then, in a similar way as the emergency stop circuit, when there's a problem, that's going to close. So when there's a fault, that contact closes, and then sends that signal to that relay. And then that relay, R9, when there is a fault, and that is energized, then it closes this contact here, which then brings on that light. If there is not a fault, so let's go back. If there's not a fault, this is not energized, and this is not switched on.
Okay.
That's an easier circuit to understand the principles. Does that circuit make sense, guys?
Yeah.
Chris, can I just jump in?
Yeah.
I get what you're saying there, but I was thinking the same. Doesn't that contact on the auxiliary relay on the gas detection need to be normally open?
Now, it might do. So this is what happens when you're a designer. You think, is that going to be normally open, normally closed? And basically, you don't know is the answer until you get on site some of the time. So it might be, and when we come back tomorrow, I'll look at this when there's no one watching me, and I can actually study it without the pressure, and I'll explain.
No, that's fine.
But sometimes I'll just be like, normally closed, normally open.
Yeah.
And whoever's on site can do it as it should be, and then red pen the drawing to then like get it corrected to what it actually is. So you might be right, guys. You might be that I need to invert that. It should be normally open, but I can't. I just want to be respectful of your time and try and just get across the concept of it.
No way.
So that's kind of the gas detection system.
Now, Chris, it makes sense. It should be normally closed. It's if you look at it, like If there's nothing at EM stop, that means that one of them buttons, the room E stop button is pushed, or thermal link, one of them button is pushed. So this one is normally closed, the contact. So the relay is energized, and this thing, I think this is the normal. This is the energized state of the R1/1 contact you have shown up there. This is not the normal state on top here. The R1/1, it's the energized state you're showing here. So once everything is good, this relay de-energizes and the R1/1 contact switches to the safety side. Yeah, it should be normally closed. Yeah,
Exactly. Yeah.
It is normally closed.
I have done it right. I'm just doubting myself.
Cool. Thank you, Chris.
With things like this.
So sorry, could you just jump in as well? So when there is no fault, the auxiliary one relay is the auxiliary one relay is closed. The relay one is.
Ivan, let me because I think this is going to help everyone, because this is a bit difficult to get your head around, because we've got normally closed and we've got normally open stuff happening. So let me color code it, because this will make it easier to understand. And I know we're overrunning, guys. If you've got to go, obviously go. But let's stick with this, because it's important to understand. So I'm going to draw this in green, because this is indicating that everything is healthy. So everything is healthy here, right? That is healthy. And this little internal relay, that's the coil of the relay. And we've got, let's imagine that this is associated with this over here. And this is, I've got it wired normally closed. Okay, so in the healthy state, let's stick with green. So in the healthy state, we got power going down there, gets to the common. Now that's, because that's normally closed, and we've energized the relay, that's now open circuit. So that is not energized. No, I've got that around the wrong way.
Yeah,
this is what I mean. So it's normally closed. So yeah, I think you're right. That should be normally open. So it's a problem with designers, guys. They just do what makes sense. They don't really spend too much time looking too deeply into it, and they just let the guys on site sort it out.
Chris, can I say something, please?
Sure, man. Yeah.
It should be normally closed, because if everything is healthy, then this is a general fault relay. If you zoom in, it's a general fault relay that there is no fault. So this thing should be open then. But it should be open, and the circuits, the R1/1 would be switched to the safety side. The contact on top would be switched, because the contact on top is also normally closed.
Yeah.
It switches to the other side. It's the contacts on top, but this should be normally closed. It cannot be normally open, because if it's normally open, it closes up, and general fault relay should only work if there is a fault, and which is when any of these buttons is pressed. And
mate, let's because talking about it doesn't register in my head. I need to see it. I might be right, I might be wrong, but let's just go through it like this.
The emergency stop. The emergency stop. It's a relay and a switch, because it's like a push button. When you press this button, you close the circuit. The coil is activated and the relay closed, so it's normally closed.
Okay.
So it's not just a coil. I think it is not just a coil. It's a coil and switch here. This is an emergency stop.
Okay. Just hang on a sec, because it doesn't matter. It doesn't matter. I'm just trying to sort of help understand like the philosophy, the conceptual understanding of it. Doesn't matter if it's normally open, normally closed, but let's just work with it, what I'm doing here. So green is healthy. And let's just, for argument's sake, just so it's easier to understand, let's say that it's normally open. So once the circuit is healthy, everything's closed, sends the power to the coil, it closes this normally open switch. So that allows the power from up here to go through the common and then back and then energize that relay 1. So when everything's healthy, that energizes that relay. Okay, so the coil's energized, the relay is on, and what that means is over here, the contact of the relay, the second side of the relay, that goes from normally closed to normally closed to normally open. So basically what that's saying is, if all of this over here is healthy, then through the relay and then the contact, it allows power and control to go down our safety circuit. This is all I'm trying to communicate, guys, at the moment. Now let's have a look if it's unhealthy. Let's say that someone hits the panic button. Let's say someone hits the panic button, right? And this is an unhealthy state. So what we got our power coming out, and straight away, it doesn't even make its way over here. It's been cut. So what happens now is our normally closed relay stays closed. Let's see what you're saying. Oh no, yeah. Let's just say our normally closed contact relay here now opens. Let's just stick with that for argument's sake. So the power comes down here, but it doesn't get to energize this relay here. So that relay's off, and it's just the opposite. We're just inverting everything. So now that just stays over here. It doesn't go off to the safety circuit is okay circuit. It just stays in its normal state, and it brings on this light here, which is our safety circuit failed. Yourself, buddy. What I'd suggest, guys, is these things, they do take a bit of time to get your head around, like the logic, whether it's closed, whether it's open, and you kind of got to follow things through just sort of in your own time, and just basically, take your time with it to really understand I can't think of the word, but the way it's sort of laid out, the way it's configured. That was like a particularly difficult circuit to get your head around if you're new to it. So yeah, I'd suggest just going over that in your own time and just sort of work through that. And you can tell me tomorrow if that's been wired correctly, if that makes sense, because I'm going to do the same. Because I'm pretty sure I've wired it, designed it correctly. But yeah, I need to take a bit of time to sort of look at it.
By the way, in this circuit, you took both boiler in series. So if you have a failure, you will not know which boiler it is. You will know that there is a problem in the boilers.
No, these are the thermal links. These aren't the boilers.
But if one triggered, you will not know which boiler. You put it in series, both of them.
Yeah,
You could take it in parallel. Just to know which
series. Yeah. So you could do them in parallel, but then it's extra control. But we've got fault outputs from each boiler anyway.
Oh, okay.
The reason you'd have them in series is because you want to knock the solenoid out. You don't want the boilers to run. They're irrelevant to the boilers. They're relevant to the main solenoid.
It's the controls. Like, you're cutting power to the controls because there's an unhealthy state. Like, if you'll know if the safety circuit triggers, because you'll have a light on here and also a signal to the PLC, and the only things that could have caused a safety circuit to trigger are either the thermal links on the boiler or the plant room e-stop button. Also, there's the fire alarm as well. So you'll know. It's just not important in terms of like the whole system. It's not important that you know which thermal link of the boiler went, because it's the fact there's probably a fire. It's probably sort of burnt the life out of these thermal links. So yeah, it's not an important thing to know. Because we're getting on a bit, guys. Let's move on to the second page and we run through this. So the gas detection system also has like carbon carbon dioxide or monoxide sensors. It has a gas detector. So that's also feeding in to this system, to these controls that we talked about earlier. So if it senses that there's carbon monoxide in the air, wherever this sensor is, or there's just another standard gas, it detects standard gas as well, then the same principles happen. It will cut out that safety circuit. Also, if there's a fire alarm signal, it's the same thing. What you see here, you see where this is sort of cut. There's like a tear in it. What that indicates is it's like it's continued. It's continued on another page. So the gas detection system's cut there over here, and it continues over here. So if you see those in the schematics, that's what it means. It's just continuing onto another page. You can see that it's detailed there. But yeah, it's the same principles with the gas sensors and the fire alarm as we've just been through. Pressurization unit is a lot easier to get your head around, guys. So pressurization unit, so similar concept. We've got our power going through an MCB, and that's powering on when the panel's on, basically. Now, in terms of the controls, so our gas detection system is healthy. There's no fire alarm, there's no gas leak, there's no fires occurring above the boiler. No one's hit the safety, or sorry, the emergency stop button, which means that this circuit, this safety circuit, is healthy. So it allows, through what we went through a minute ago, it allows that power or that signal to be distributed further along downstream in the schematic now. So the safety circuit here. So now we're continuing down through the system, and the first point we're coming to here on our safety circuit is the pressurization unit interlock circuit. Okay, so before we get into what triggers the interlock circuit, let's just follow what happens. So it goes down here. So this is the 24-volt AC on the 400 safety circuit into, again, internal relays built into the pressurization unit. And again, this is normally closed. So if everything, we can read in the tech manual how this operates, but ultimately, if everything's healthy, it passes through this contact and then continues the circuit now on the boiler interlock circuit. And this is what we're then using, and we'll look at this tomorrow. This is what we're then using to control the boilers. So basically, what that's saying is, if the safety circuit is healthy, like all that stuff we just mentioned, and the pressurization unit is healthy, then we can pass power on this control circuit to the boilers. Ultimately, that's what it's doing. So we kind of, what we're doing is we're breaking up, we're putting things into series. We're putting like a little system with multiple things in series with now this one single system, the pressurization unit. So if all of these things are healthy on the gas side and everything's healthy here with the pressurization unit, then that allows power to then pass, and we'll see tomorrow, to the controls of the boilers. So the boilers can be controlled, providing that there's no gas leak, there's no safety circuit pressed, and that there's enough pressure within the system. That's ultimately what the interlock circuit does. And what that does, and so yeah, that's what that does. So providing like everything's good with the pressurization unit, we can then pass power or controls to, I say power, what I mean is controls to the boilers. And then also what we've got is we've got this relay here. So this will be easier to understand compared to what we just went through. So now we're not coming off the safety circuit here, because we just want that constant feed You know, we don't want it to be dependent on whether the safety circuit's healthy. We just want that constant 24-volt AC supply if we're feeding like fault or enable signals. So that's why that's on this rung up here. So what we got here is we just got that constant feed going through the terminal blocks into our general fault output of the pressurization unit. And if you look in the tech manual, it's basically, it mimics like the fault output and the interlock output basically operate in the same way. I think there's a few differences there. But yeah, normally closed, so it's coming back into this relay, relay 3, energizing this relay, which switches that contact there. So in its normal state, well, it's normally closed over here at the moment, but because this is now, the relay's energized, it switches that to the other side, the contact to the other side, and then it passes power down here and brings on that normal, which is a green running light or OK light. So basically that tells us in that state that the pressurization unit is not in fault. Now, let's say that it does go into fault. So there is a problem. There's a drop in pressure or the pressure's too high. Then what happens is that goes open circuit here at the pressurization unit.
Chris, would that be pole 2 rather than pole 1 that you got up the top there on that relay 3?
Say that again, mate. Sorry.
So you know where you got the relay there, relay 3, but it's pole 2 rather than pole 1. Have I got that correct there?
So that similar to the relay on the other page. That's just telling us that that's how many poles are associated. It's a 2-pole relay basically.
Right. Okay. So it's not saying it's actually pole 2. It's just got that many. No. Right. I got you.
This is the if you see a square or a rectangle, that's telling you that it's the coil side. It's not the contact side, which is the pole side.
I'm with you.
So all the relays in this project are 2-pole relay. So all of them will have that /2 to tell you. I'll show you again, mate. So let's change the color. So yeah, relay 3, R3, relay 3 /2, 2 poles. And then we can see here on the contact, so this is the contact side now. Again, it's the same relay, relay 3, but here it's /1. So that's telling you that this is pole 1 of that 2-pole relay. So this is what we're doing on the first pole. And then on pole 2, we're feeding into the PLC. So we're basically doubling up on that signal. So we're feeding on one pole a light, ultimately, and then on the other pole, we're feeding a PLC. So what we can do then off the PLC, we can program things to happen. So I'm not going to go into the details of that, but we can, for example, you might program like a text message to be sent to the manager of that hotel to say, oh, by the way, Mr. Manager, your pressurization has dropped within the system. Or it might go to a tech support team that can log in straight away as soon as they get that notification, email notification or app notification, whatever it is, they can log in straight away and see what the problem is and get an engineer on site quickly, like proactively. That's sort of part of the reason for having into a PLC as well. But for the time being, we're just focusing on the mechanical, electrical side, you know, how it used to be done back in the day before PLCs. So yeah, that's what that's indicating up here. It's pole 1 of that relay. So yeah, so basically back to what I was saying. So if there is a problem, that goes open circuit and that now cuts the power to that relay. So that relay is no longer energized. So it stays in that state there. And it passes power to the fault light. This takes a bit of time just to get your head around. Like this is something that I'd recommend that you just spend a bit of time, like tomorrow, this evening, just get your head around. This is probably the better page to do it on, actually, guys. Do it on page 2 and just get your head around that fault signal on the pressurization unit, because it will click. It will make sense then if it's not at the moment.
Chris,
Yes,
it's
mate.
Russell. I was just going to say, just to add, I don't think we've mentioned it yet, but obviously when it's normally open and normally closed, that's like it's non-energized state, isn't it? So when you say you wire it normally open, that's its non-energized state, obviously. So when it is energized, it will close. I'm just adding that in for everyone. Do you know what I mean?
Yeah. That's
you haven't really said that, so yeah.
Yeah, okay, that's a good shout. Because it's you've got to remember that these. I'll use a different color. These are what happens here is also happening here at exactly the same time. So yeah, if it's not energized, then this just stays the same here. Nothing changes over here. And because we've got it wired through the normally closed side, that happens. This doesn't happen because it's open circuit. But if this is energized, this then changes. So the state changes and flips from there to here. So then this is actually open circuit. So this doesn't come on, but now this does come on. So yeah, that's kind of how that relay works. Guys, I'm going to call it a day there because that's a lot to take on, I think. So yeah, I think we'll call it a day there. Tomorrow, we're going to just basically continue. We're going to look at the boilers. So let me just have a look at what's...
You mean on Wednesday?
If anyone has any questions, I'm going to hang around for a bit. So if you got to shoot off. But yeah, so tomorrow, guys, we're gonna answer some questions again. We're gonna come back to this. So any questions that you've got from like looking at it in your own time later tomorrow, we're gonna spend 20 minutes just going over that again tomorrow morning, and then we're gonna look at the boilers. So what I'd recommend you do as well is just have a flick through the boiler tech manual. Just get familiar how the boilers are controlled. There's a couple of like add-on modules that go with them as well. So just get
excuse me, by tomorrow you mean on Wednesday or tomorrow?
Sorry, guys. Yeah, sorry.
Okay, thank you.
Thank you for having that. Wednesday, guys. Yeah. So you got a few days to sort of digest what I've been through. That was a lot to take in, guys. But just spend a bit of time, your own time, going through what we've been through. If you're a bit unsure, just spend a bit of time going through what we've been through, and it will click. Hey guys, me again, and this is just a reminder to actually download those schematics for this project so you're able to learn on a much deeper level. As mentioned at the start of the video, they can be found in the description, so click that link, you'll be taken to our free community where the first thing you'll see will be those schematics. So download them, come back to this video after you've downloaded them so you can actually get to where you want to go, so you can actually understand schematics, so you can become a better engineer, progress your career, progress your business, whatever it might be. Download those schematics. It will seriously help with all of this. Guys that want to hang around for 15 minutes or so, please do, and let me know what your questions are.
Can I pop on straight away?
Sure, yeah, crack on.
So I think it's more of a wiring diagram schematic sort of layout question. So what I think was the issue with this whole debate about normally open and normally closed circuits, and what I personally have issues with, is what's the definition of normal? So is normal being a fault condition, or is it normal being a normal condition? So is there perhaps a way to make a note regarding that when drawing up a circuit diagram or something?
Yeah, that's a really, this is where it's trying to just wrap your head around what actually, so normal doesn't mean whether it's in fault or not in fault. Normal is just how people refer to how contacts, or what the contacts in a relay basically.
Well, I mean, let's just put it into perspective. So page 1, I have an auxiliary 1 relay in front of me. It says normally closed. and it says the condition for that is generic fault. So when the generic fault is in place, is it open or is it closed?
And this is the thing, it's difficult sometimes as a designer, unless you're actually working with the bit of equipment on site and you actually know 100% how it's operating, then sometimes I just, for me, and if I haven't worked with a piece of equipment before, I don't know for sure. So I will wire it as best I can, but it might be when you get on site, the commissioning guy's like, oh, the fucking design team haven't got this right again. And they have to red pen it and, scribble that out and go, normally open actually, mate. And then they send that back to the designers and then they update their drawings. Like, it's just difficult to know for sure sometimes. And yeah, it's kind of like, it's like I said, it's like, don't worry too much about the specifics of whether it's normally open, normally closed. It's just understanding the philosophy, what we're trying to do. And if you need to invert something from wiring it normally open to normally closed, because the opposite thing's happening on site, it's a simple wiring change to make, if something's, it's easy to work out. If something's running when it shouldn't be, then you switch it from normally say normally open to normally closed. If something's off when it should be running, it's the same thing. You just switch it the other way.
Chris, just want to ask this and clear my concepts as well. Isn't normally means unenergized, like when the coil pertaining to that particular contact is unenergized, that is normal state, and when it's energized, that's not normal state. Isn't this about energized and non-energized?
Yeah, exactly, mate. Yeah, that's exactly it. Bang on, exactly. Let's draw it. Yeah. So this is normally open. I'm going to draw a coil in there as well. Actually. So this is the common. This is where we feed power in. See, this is a single pole on a relay, right? And let's now draw the other pole. So now we're looking at a 2-pole relay, and I've just drawn that line down the middle just for simplicity's sake, just to sort of illustrate that it's 2-pole. The coil, though, the coil is associated with both of these relays. But we've got like a common on this pole, and we got a common on that pole. So, and it depends how we've got things wired, guys. So this is normally closed. Normally closed. I'll just do illustrations on the top one, but it's the same on the bottom. So if we've got it wired normally closed, so we've got it wired there, but we might also have it wired normally open, because we might want two different things to happen. So when the coil, bring me back on track if I'm going off on one in a sec, and I'm not answering your question. But like if this coil is not energized, so we haven't brought that relay on. What we've got here is we might have 24 volts over here. We've got that wired like this. And because it's not energized, that's just going straight out here. Normally closed. And then we've also got it wired, we've got something else wired, normally, let's just call this a light, normally open. So at the moment, in the normally closed state, when the coil's not energized, or the relay's not on, we've got this light coming on. But now, let's go. Now the relay is energized, so it is on, and this then switches. That then switches. Here. So this now comes on. And whatever we've got over here wired switches off. But we might not be using both normally closed, normally open contacts. We might just be using one of them. So it just depends on the application, what you're actually trying to do with that relay. Alice, is that coming back to what you were asking? Like that kind of backs up what you were saying, does it, mate?
It makes perfect sense now.
Can I add my observation, which would probably simplify things?
Yes, please do, mate.
I think when looking at this first page, which confused us, would it not help to start always from the end? So when we look at this safety signal R1/1, to make it safe, obviously we have to have energized relay, and that's the first step, and then we go backwards in steps to analyze previous steps, which make this safety healthy. Basically, what's your opinion on that?
Are you saying rather than working forward, we sort of work backwards?
Yes, and then because we are hugely confused whether it should be normally closed or open. But that is our confusion, and we cannot say how field is wired because whoever designed it, having safety in mind, wired it either this way or the other way, whichever makes it safer. But if we analyze going from the end to the beginning, I know it sounds strange. Maybe is it not a better way?
Yeah, no, that's, to be fair, like that's a good way to design things. Actually, is always think of the end outcome and work your way back, like especially if you're doing like programming in PLCs, you sort of think of the end point and how do you get to that end point, and you work your way back. So that is a way of doing it, but I'm just thinking for most people it's logical to work forwards. That's kind of why we did it that way. If you want to work backwards, then yeah, by all means do that. That might make better sense for you or whoever else.
Yeah, just to highlight my idea once again, you were drawing this coil between EM stop, which we assume will energize that auxiliary relay.
Yeah,
and that's where confusion came, because we said normally closed or normally open, but we were making assumption. Okay, we tried to make it fit. Rather than going, if we're working backwards, we are following logical steps. I know it's very subjective, but when we were doing the other way around, we came to this junction where we got ourselves confused a little bit. But anyway, I think that's subjective, basically. What I'm trying to say.
What we're doing, mate, if you're able to hang on, we work backwards through it together. After other people have sort of asked any questions, if they've got them, or if anyone else wants. Does anyone else have any other questions? Firstly, no. Okay. Would that be helpful to people then to work backwards? What Al just said.
Chris, I would like to add to this. What my colleague was saying, if you look at, that's why I said that it makes sense that this contact is normally closed. If you look all the way back to safety on page number 8. It would make sense to you that this switch is basically enabling the safety circuit on page 8. It's R27, I think. I'm not too sure. Let me just go to page 8. Yeah. So it's making this contact. It's energizing this. So if you go to page
27,
yeah, R27/1, and that R27/1 is then enabling the rest of the bit. So it makes sense that contact is normally closed, and if you work your way from here up all the way to the top, so normally closed is the right thing. But like the way it is on the diagram, it's the right way.
Yeah.
I think what would clear this confusion, Chris, is if you tell us the contacts of relay, the way they are shown on this diagram, are they shown in their normal state or in their energized state?
Yeah, so this is, and that's a really good thing to point out as well, because this is something that stumped me when I started. Like, what state are these drawn in? And it's their non-energized state. So that's why when I was sort of going through things, I was sort of going from saying, so it's going from here on the normally closed to normally open, and that's because it's gone from being sort of not energized to then energized. So when that's energized, so that's not energized at the moment. That's not energized. That's how it's wired, not energized. Not energized, right? But then we need to imagine, we need to visualize within the drawing that if it is energized, right?
Increase.
Hang on. Wait. So if it is energized, like we have powered up this relay, it is energized, then we need to imagine that this then goes, it's not there, it's not there, and that contact then moves to here. I've drawn it really badly. But basically, that is no longer there. That's irrelevant. We've energized the relay, so it's now going here. That is the physical state of what's happening within that relay.
Okay, then it's normally open if that's the case. Then
Can I say
it's normally
something,
open,
please?
yeah.
Can I say something?
No. So hang on, just one sec. Sorry, James, just a sec. It's wired in both ways. It's wired both normally closed. So look, we got it wired normally closed here and normally open. But it's the state of that relay that then determines whether we're going down the normally closed route or we're going down the normally open route.
Chris, can I just help with a clarification?
Sure, go for it, James.
So I think it's irrelevant. I think we have dwelt too much. But first of all, I would say thank you for some of the other lights that you have really shared. I truly appreciate it.
Let me see about it.
I'm not home, so I had to stop by the restaurant. So you can't see me, but what you can see.
All right, man. Okay, sorry, mate. Carry on.
So, but let me say what I was saying. First, I would want to thank you for shedding some lights with some of those nitty-gritty things that just puts us off when we handle this controlled documentation. But now, I think the emphasis shouldn't be on whether that particular relay was wired normally closed or normally open. What I think is this. Let's not read into the philosophy of what the designer had in mind. The designer knew that he wanted R1. Look at R1. When 24 volt, as soon as 24 volt leaves the relay, leaves the transformer, they said that safety circuit failed indication light should be on.
Yeah.
Let's ignore, yes. The person wanted the light to be on.
Yeah.
Because the 24 volt on the bus bar already, as soon as, because it's in the normally closed state, I'm talking of R1/1.
Yeah.
As soon as, recall when you said circuit 100, all circuit 100 happen at the same time as soon as the transformer secondary side releases 24 volts so all circuit 100. So
James, I'm going to stop you there. I'm going to stop you there, mate, because you've given me a great idea and you've hit the nail on the head. What I'm going to do, guys, this is what I should have done. I should have done that to start with. I should have just said, guys, this is what we're doing on this page. This is what's happening. You know, like James just said, this is the philosophy, what the designer is trying to achieve.
Correct.
Give a more conceptual view of that page. And then we work into the details of it. That's exactly, by the sounds of it, what I should have done. So what I'm going to do is for Wednesday, and what I'll do is I will do the same thing for today as well, but obviously it's a bit too late now. But what I'll do is I will do like a video and put it within the shared drive of the concept of what the designer is trying to achieve for each page that we're going to study on the days that we're studying them. So you've got a conceptual idea of what each page or couple of pages should be doing before we get into the detail. Would that be helpful?
Yes.
That's a good idea.
Yeah.
But I think even that confusion did help me a lot. So yeah, thank you, Chris.
All right, man. Now, James, that's a great shout, mate. Thank you for coming up with that. Really good idea. So Yeah, I will do that for this page and page 2 that we've been through today, tomorrow, and I'll also do that for the boiler pages again tomorrow, so you're prepared and you can watch it before we dive into the detail of the boilers on Wednesday. Because you can see, like, things, when we get into the detail of things, it takes quite a long time, especially when there's questions of stuff. So if I do, an overall video, so you're better prepared before we get into the detail, I think that's a great idea.
Also, for what it worth, Wednesday I'll be very much available. So my videos I'll be home. Currently, I'm in transit. I had to stop by a restaurant. Apologies.
I'll be able to see you then, James.
When's your next session, Chris? When is it? On Wednesday, is it?
Wednesday, yeah, same time Wednesday.
All right. Cheers then. Thanks a lot, by the way. Thanks a lot.
No worries.
Thoroughly enjoyed it. Cheers, pal.
Cheers, mate. Appreciate it. Yeah, guys, obviously this is a new thing. We're ironing things out, so your feedback is really, really appreciated. And I will adapt things to what works for you guys. So any ideas that James has come up with, Powell's come up with, like, please just let me know, whether it's live on the session or you message me later. Let me know your feedback and I'll adapt it, to what's going to help you guys. So appreciate you all, and I'll see you Wednesday, and I'll put an email out when I've sort of done those conceptual videos and put them in the drives. I'll let you all know. But yeah, so before I'm going to do a quick recap on the gas detection circuit system and the normally open, normally closed. Before we get into that, were there any other or any questions at all sort of that followed on from Monday's session? We all good? Cool. All right, guys, that's excellent. Right, so let's just recap quickly, and you can see where my design work has sort of not gone completely to plan, but the design is there. It's just, like I said, I've just got the inversion round the wrong way, and this is a common thing. Designers don't really care because they're not the ones on site commissioning it, so it's not really their problem, but it should be. They should be thinking about these sort of things. So yeah, so let's just recap this circuit. So let's just imagine then that this part here of the gas detection system, that's sending out a voltage. 12 volts, 5 volts, doesn't matter. 3.3 volts, doesn't matter. But that's sending out a voltage. So it's sending it out into the panel, back out, and this is just the way I've got it wired and designed, through the E button, E-stop button. And then we're going through the thermal links above the two boilers, just sensing if there's a fire or overheat detection, basically. So if they're in good condition, then it continues back to the panel and then ultimately back into the gas detection system. And then let's pretend, well, we don't have to pretend, let's just draw it as it most likely is within, it's probably a little relay mounted to a PCB inside this little device. So it's just another relay ultimately, right? And that's connected to, well, it doesn't matter where that's connected to, but 0 volts most likely. So when that circuit is completed, it then energizes that relay. And then, so let's just hold that there for a sec. So that circuit's completed, it's energized that relay, and at the same time, we've got our constant feed going from our 24 volts going out on terminal block 3, and it's feeding that common of the auxiliary relay, auxiliary 1 relay. And if you looked on that tech manual, we've got both options. We've got normally closed, which I've chose to use, and we've also got a normally open. So we've got both options there of how we're going to wire it out in the field. And what I've done is I've done normally closed, because I'm not going to get into the details of why I've done it like that, but ultimately I'm always thinking of a fail-safe condition, which isn't important that we all understand that right now, but I'm always thinking fail safe, normally closed. That's kind of how I think. So I've just thought, right, okay, well, it's probably going to be normally closed, but I haven't spent too much time thinking about it until now. So now I've thought about it, I've realized that needs to be normally open. So let's just say that actually we're on site, things are operating the wrong way round, and you as a commissioning engineer have realized, right, well, that's operating around the wrong way. The designer's fucked up, standard. We need to just wire this cable here. We need to wire that into the normally open terminal. But what I'm going to do here is just change that. Well, I don't need to do that on the end, but change that to normally open. So that's what we've done. That's the modification that we've done. So now we're going back to that e-stop and thermal link circuit. So that's completed. There's no breaks in that circuit, which is energized that relay, that internal relay on the PCB, which then means that the normally open now closes, which completes that circuit. So this 24 volts now that we fed from ultimately our transformer in the panel is now able to go through that auxiliary 1 relay and power up relay 1, which now means that this contact here has changed state. So it's no longer there, and it's changed from here. So it's changed from not going that way to going this way. And then if let's say if there is a break, like someone smashed that e-stop button, they've panicked and basically think that there's a problem, that's broken that circuit. That's a normally open, that's an open circuit now. That internal relay on the PCB is no longer energized, which means that we still got that feed coming down here, but because that's normally open, it's just stuck there. It's not going anywhere. It's not going to this relay here, which just means that this contact stays here and lights up the safety circuit failed light, which is in line and what we want, because someone's hit that panic button. And the same thing will happen, like if there isn't if the panic button hasn't been pressed, but let's say there's overheating above the boiler, one of the boilers, it's the same thing. It's open circuit over here because those are all in series with each other. So does that just clear things up from yesterday, guys?
Can I ask a question?
Yeah, crack on, Mike. Yeah.
Yeah. When you're starting up and your system is not doing anything, say you isolate the main isolator you put on, what state is all your safety switches when you first begin? So say you put on the isolator.
This here?
Yeah, the main isolator for that. Yeah, or even the main
isolator for the gas detection system, or the whole panel. The
whole panel. Say you switch off, you put on the whole panel.
Yeah.
Before everything kicks in, what would be the state of the relays? Obviously you've got your gas detection section.
Yeah.
Will come on. What would be the state of no fault? And what would your lights be pushing out in the start of it? What would your safety circuits red, gas closed red, and
I know what you're saying, mate. It depends. It depends on the state of things out in the field.
Yeah. So if all your buttons were in, e-stops were closed, your thermal links were closed.
Yeah.
If I went to the panel, to the plant room, and looked at the panel.
Yeah.
What lights would I see at that set moment?
Right. You would see, if everything's good and we got power on, you would have this light come on.
Right.
And that is it.
Okay. Right. Fair play.
No. Sorry. Gas valve open. Sorry. This is another thing that just adds to confusion.
Sorry.
Green.
Right.
Green. So the gas valve is open. It's allowing gas into the plant room through the gas pipework and allows it to feed it to the boilers.
Okay, fair play.
If there's an issue, then that would go off, and you got 2 red lights here. So gas valve closed, and we've also got a problem with our safety circuit. So those 2 red lights would be on if there's a problem.
Okay, good. Cheers.
All right, mate.
Thank you. Cheers.
Quick question, Chris.
Yes, mate.
When you were starting, you were showing this first long circuit, and you mentioned 0 volt. And can you please clarify what this was referring to? Somebody typed it was referring to the coil 0 volt, but I'm not sure.
When I drew a relay down here, are you talking about?
Yes. Exactly.
Yeah. So just exactly like what we've got on all the other relays. The coil of a relay is different voltages, right? You need to make sure that you select the right coil voltage to the control voltage that you're using. So what that means is, so say this, let's look at relay 1. This is a 24 volt AC coil, okay? So that means that we feed 24 volts in the A1 terminal, and then there's a coil in here, right? But then ultimately it needs to get back to 0 volts. So then the A2 side just connects to 0 volts. So A2 on a relay on the coil side is always like the 0 volts or the ground or the neutral.
Okay, it makes sense, yeah.
So, because what we got here is basically when we do apply 24 volts, we do apply it to that. It goes through this coil, it pulls in the contacts, and then it just completes the circuit to 0 volts or ground. So A2 is your ground, 0 volts, neutral. That's how you need to think about that.
And finally, just to be completely sure, this PCB relay that you mentioned,
yeah,
how is it connected to the that normally closed that you had redrawn?
It's just you got to think about it exactly the same principles as what we've got here. It's the same principles, but rather than like a separate individual relay that we're wiring, it's the same principles, but on a PCB, on electronic PCB, so much smaller. And rather than wires, they're using like that metal track stuff that you see on PCBs. And then you just have your like your sort of terminal blocks on the PCB of this gas detection system. The field wiring here connect to. Does that make sense?
So that PCB relay is actually called R1-/2, yeah?
No, I don't know. So don't get too caught up with the relay on this. That was just me drawing it to illustrate a point that the same thing is happening on this gas detection system. It's the same principles as what's happening within our schematics, what we're talking about. Relays operate in the same way, whether it's sort of a standalone relay in a control panel or a relay working on a PCB.
Okay.
Cool. Any more questions, guys, before we move on to the boilers?
When everything's all good, auxiliary 2 relay also comes into play.
Sorry, mate, just say that again.
You see, whenever the system's all good, auxiliary 2 relay will also come on.
Yeah. So it's probably if everything's good. No, actually, I can't remember what it said in the tech manual, to be honest, mate. But I'm pretty sure auxiliary 2 just mimics the gas valve, which ultimately is the same as whether it's in fault or not. Because if it's in fault, then the gas valve closes, doesn't let gas into the system. If everything's good, it opens and allows gas in. So yeah, it's ultimately mimicking exactly what we're doing with the safety circuit.
Yep, no problem.
All right, mate.
Okay, man.
Right, guys, let's move on to the boilers, before we do, let's just quickly recap what we're doing here on the pressurization unit. So pretty simple stuff. We've got that 24-volt supply feeding the interlock circuit on the pressurization unit. There's a few things that determine whether this internal relay on the pressurization unit switches on or off, and I think it's like low pressure, high pressure, or like power is lost. So that's what determines whether that relay is triggering on or off. Healthy condition. Again, let's not pay too much attention to whether it's normally closed, normally open. Until you get on site, you don't know for sure. But let's just say everything's good, everything's healthy, that circuit completes, and then we're feeding that boiler interlock circuit now. So everything's good and healthy with a pressurization unit. That allows controls to run through and off to our boiler interlock circuit. So we just need to keep that in mind. Everything's good with the pressurization unit, which means that we've got voltage along here now. And we've got 2 pages with our boilers. It's exactly the same controls. So I'm just going to focus on page 3, which is boiler 1. And I absolutely love the way that these boilers are controlled. It's really, really cool. Firstly, let's just do the obvious, the basic stuff. So we've got just same as what we had on the previous pages. We've just got our 230-volt supply. Basically, when the panel is switched on, that provides 230 volts supply to our field equipment. So providing that switched on, and our local isolator in the field is switched in the right way, we've got power to the boiler. The next thing is we've got, if you'll notice on this row here, we're using just our constant 24 volts from the transformer. So we are using that for some things, but we're also using the boiler interlock for other things. So who can tell me, why are we using the boiler interlock circuit for some controls and some operation, and why are we using just the constant 24 volt AC signal for other stuff? Gov, how you doing, mate? You have to take yourself off mute, mate.
Not bad. How are you, Chris?
I'm good, mate. I'm good. Good to see you. Can you tell me why we might be using the 24 volt AC circuit for some stuff, and why are we using the boiler interlock circuit for other controls?
I don't know off the top of my head, but boiler interlock is stopping some circuits before they carry on.
Yeah. So yeah, we've got the boiler interlock circuit being controlled, determined whether it's live or not live from the pressurization unit. So that determines whether that circuit is live. Can anyone else be more specific in terms of why are we using the 24 volt AC feed for some things like the lights and the feeds into?
Is it because obviously the pressurization unit is to do with the water side of the system, making sure that that's safe to actually be in play?
Yep.
Is it if you used one circuit, you'd lose a lot. You wouldn't get no indication on other things?
That's where my question then goes. So why don't we just use the boiler interlock circuit for the controls and also the fault lights and the feeds to the?
You lose a lot, wouldn't you? Or would you?
The constant 24 volt AC. So that'll be used for like the indicators, so you could always know the status of the panel. Whereas the interlock side is there for a reason to stop certain things.
Yeah, exactly. So we don't want to cut. For example, we don't want to. So on this 24 volt AC circuit, we don't want the feed that's then going to ultimately power these relays, which is then going to switch these contacts and switch on these lights to tell us whether the boiler is enabled or in fault. We still want to know that, even if the pressurization unit isn't healthy. We still want to know those states. So that's why we're not tapping off the boiler interlock circuit for those things. We are tapping off it for the actual controls, which we'll get into more detail in a sec, the actual controls of the boiler. So how the boiler is like basically on or off of the boiler in simple terms. So that's why they're split that way. And tomorrow, I'll be interested to see if someone can tell me, based on what we just discussed there with the interlock circuit, point out the fuck up or the thing that I haven't corrected, that I haven't red penned around the boiler pumps tomorrow. So if anyone can tell me what I need to do tomorrow, so it's 100% belts and braces, please tell me tomorrow. So let's continue with the controls. So we got power going to the boiler, and we've got our 24 volt constant feed going into that additional clip-in unit that allows us to know the state of the boiler. It's that additional unit, the Siemens OEM unit. So we've clipped that into the boiler, and now we're now wiring into it. And so we got our common supply, and then we've got an enable output. So that's obviously enabled when the boiler's enabled. I think basically, someone can correct me on this because I can't remember exactly, but I think if there's power, I think that then brings on that indicator signal. That enabled signal. Correct me if I'm wrong though, if someone knows different. So let's say there's power on the boiler. There's power on the boiler. That then completes that circuit there, which then allows power to go back to this relay. So it enables that relay, which is relay 4, and much easier to get your head around than yesterday with the normally closed. Once that relay 4 is powered up, that closes this contact. So ultimately, it just goes like that.
Excuse me,
quick question.
This is not 4 point. This is 4.2. This is pole 2 of the relay. This is pole 1.
This is pole 1. Pole 1, yeah.
So this is.
There's other poles, mate, I think.
Okay. So this relay have 2 poles.
Yeah.
1 and 2. Okay.
Yeah.
Quick
just
question.
just a sec.
Okay.
Just on the poles, and we'll come back. Hang on. So yeah, just for simplicity, guys, and so you're all aware, every relay in this design, in this project, every relay is 2 poles. We're using, and it's the same throughout. Like I've kept it standardized throughout. Pole 1 is always used for like the mechanical, electrical stuff. So bringing on lights, basically, as you can see here. So let me just go back. As you can see here, /1/1. So that's the first pole of relay 4 and relay 5. Okay. So pole 1 is on all of the relays within the project, is always being used for like the mechanical, electrical stuff. Now, if we go to the PLC page, and obviously we're going to go into this in more detail later on, but you'll see all the stuff feeding the PLC is on pole 2. And I won't go into any more detail than that, but basically, yeah, they're 2 pole relays, and pole 1 is being used for the mechanical, electrical signals and controls, and pole 2 is everything feeding the PLC. So we know through the PLC what the state of the system is. Does that make sense, Ahmed?
Yeah. It's clear.
So who was it that had the other question?
It was a quick question about enabled signal. I believe, actually I'm asking, is this signal coming on when somebody actually presses some button on that unit, so it doesn't come automatically on when the power is on. It needs some manual action, I believe. Can you clarify that, or that's something important?
Maybe, I don't know. It's details within within the technical manual, which actually, as a design engineer, it's not overly important whether I know. That's more for the commissioning engineer to work out and sort out.
Fair enough, yeah.
Let's just say, for argument's sake and for simplicity, working through this, when there's power to the boiler, when there's power here and the boiler's on, that just triggers that enable signal. So the boiler's enabled, there's power there, it's ready to go as soon as it gets the right control signal. So let's just stick with that because it's easier to understand than having power, then having someone press a button. Let's just keep it simple. It might be that, Powell. I don't think it would be, but it might be.
Yeah, fair enough. Thank you.
So yeah, power's on. It's enabled that relay there, which then closes pole 1 on relay 4 and brings on that green light on the front of the panel. So we can visually see a user or on-site engineer, facilities management, whatever, whoever in the plant room can see that, yeah, boiler 1 is enabled. Great. We got a visual representation on the front of the panel. Now, it's exactly the same principles, guys, for the fault. So let's just run through that from the start again. So we got our 24-volt feed again. It's the same feed going into the boiler unit. And then when there's a fault, when the boiler detects a fault, and I'm sure there's a load of, similar to the pressurization unit, there's probably a load of things that determines whether that puts multiple things that will determine whether this fault output triggers. Again, it might be stuff to do with pressure. It might be something to do with like the ignition not firing. It might be if it doesn't get to temperature in a certain amount of time. Like all of these different parameters that are pre-programmed into the boiler that basically trigger that fault signal if one of these things happens. So let's just say that the ignition of the boiler isn't firing, isn't coming on. So the boiler can detect that, and then so it detects that the ignition's not firing, and then so it closes that internal relay, and then it sends the power back to this relay here, R5, and just going back to what Ahmed was saying, so the /2 here is just indicating it's a 2-pole relay, just to remind you all. If it was /1, it would be a single pole relay. You don't tend to see single pole relays. It's usually 2-pole, 4-pole. That's mostly what you get. But yeah, saying that it's a 2-pole relay. And then we can see up here that the contact side, pole 1, relay 5 is over here. And yeah, so it's now exactly the same as what we did over here. It's now closing that contact. And that 24 volts is going and bringing on that fault light. So again, we can see on the front of the panel straight away, oh shit, there's something up with the boiler. And then the user or operator or facilities manager can straight away see that there's an issue. They need to call a plumber. They need to get onto the phone to the controls people. If they're a good controls company and they're actively monitoring things, they'll have already got a notification through the PLC that there's an issue. So they should already be aware of it. But this is just more, the mechanical, electrical, doubling things up, really. There's, it's that redundancy and also just visualization for people that don't have access to the PLC. If you've got an HMI, which most modern BMS systems have as well, so an HMI stands for a human machine interface. Ultimately, it's just a tablet on the front of the panel. That will also give you some indication as to what's happened. It might have a log in it as well, so like a fault log, so you can see when that fault happened, what time it was, and you might be able to relate that to, I don't know, a power cut or something, and it might help you find and diagnose the problem quicker if you can sort of relate that to something. I don't know. But in terms of the controls, that's it so far on the boiler in terms of the enable and the fault. Does that make sense, guys?
Yeah.
Has anyone got any questions on that? Or
Yeah, all good.
anyone want to just go over it again?
Just assuming obviously the enable is then depowered, the coil is not powered for R4 once there's a fault condition.
Say that again, mate.
So, like you just said then about the fault condition, which could be anything, like you say, the enabled side of that AGU2 would then be not powered, correct?
Not necessarily, because
so you'd still have an enabled light?
Yeah, because it could still be enabled, like it's still enabled for, you know, and especially if if that enable signal is just coming off, you know, is determined whether there's power to the boiler.
Yeah.
There can still be power to the boiler, but it can still be in fault.
Okay.
Good question though. So yeah, they can both be on at the same time. Right, let's get into the cool bit. So, who can tell me what we've got here? What is this?
Selector switch, isn't it? A selector switch?
Yeah, exactly. How many position selector switch is it?
3. Off, auto, and hand.
Yeah, exactly. So we got position 1, position 2, position 3. And again, these are common on BMS panels, common on any panel really. This is how we, or an engineer or user or whoever, can actually sort of physically have control over the system rather than the PLC having the control. So what happens here? So firstly, that boiler interlock circuit, that's the first thing. So obviously, for any power to come down this boiler interlock row, the thing upstream that we went over yesterday has to be healthy. So this circuit here and the pressurization unit needs to be in a healthy condition for that boiler interlock circuit to have 24 volts down it. So providing that is good and in a healthy condition, that means that we can then use this selector switch. So let's use it in hand first. So we got power going to here, and then we need to imagine, so this is in the off position, so nothing's happening in the off position. We haven't got control manually, and this can get confusing. So when you see hand, just think of that as manual control. So it's in hand means it's being manually controlled. When it's in auto, that means it's being controlled by the PLC. So let's just focus on hand for the time being. So I'm on site and I've just switched the panel to hand. Okay, so what that's actually done physically in terms of the wiring is it's basically done that. It's switched that to that position. So what happens now is we got that 24 volts, goes down here, and it energizes relay 6. Now, someone tell me, what does that do? Relay 6 is energized. What happens?
The double pole that's just above the PSU, both of them come on, didn't they? I think. R6, 1 and 2 poles come on.
Yeah, exactly, mate. So, because that relay is now energized, these are now closed. Which means, and we come back to the PSU in a sec, but bang on with what you're saying, Mike, is that allows power now. We got the 24 volt, we got the 10 volts here, we got the 0 volts here. That allows those two voltages to go down this one into 26, terminal 26, and also at the same time, the 0 volts to go into 25 terminal. And then if you look at the tech manual, the boilers within the field wiring is then going into the ground, which is our 0 volts, and our H1, whatever that stands for, H1, but that's ultimately our variable 10 volts. So Mike, I want someone else to answer this. So just looking at that as a whole, as to what's just happened. Danny Gray, can you tell me what's happened there, mate? Like what's just happened in terms of the boiler and control and what it's seeing?
What are you mean, sorry?
Yeah, so what we've just done, we've put it into hand.
Yeah.
And then what the wires that I've just followed with the pen, what's happening at the boiler now? We've energized relay 6.
Yeah, both poles.
Yep, both poles R6 have closed. What are we seeing at the boiler?
Pass, Smith. Not sure.
Jeff Wellock, can you tell me what's happened at the boiler, mate?
Yeah, so H1 is now seeing a complete 10 volts. So you've completed the circuit at H1, whatever that does.
Yeah, so H1 has got 10 volts. Ground has got 0 volts. And if we just following that back, let me just move this. It's just coming from the power supply. So that 0 volts here, and then our 10 volts here. So that's all we're doing. When we switch it to hand, it's as simple as that, guys. We're just allowing the constant 10 volts and 0 volts to feed the boiler. Now let's take it one step further now in terms of what the boiler is actually doing. John Sims, can you tell me what the boiler's actually doing? Now it's seeing 10 volts at it.
Well, I presume it's firing now, isn't it?
Yeah.
So your pilot light's going to come on. The only problem is with that 10 volt, it isn't going to, because you're getting a constant 10 volt and not a difference in voltage. You're just going to fire at full power, I guess, is it?
Exactly, mate. Yeah. That's exactly it. So now in the boiler, what we'd do as commissioning engineers is we would then set when you set the range basically. So if we are seeing 10 volts, then what does 10 volts translate to in terms of output, heat output? Obviously, we don't want it to, I'd like to say, for simplicity's sake, just for this training, let's say that 10 volts equals 100 degrees, but then we're going to have boiling water in a system, which obviously isn't going to be good. So most likely, most systems you'll see like 10 volts will be like 90 degrees. So let's just go back. So we put the boiler switch into hand. We've sent a constant 10 volts from this power supply. We'll come back to this power supply in a minute. But basically, we're sending a constant 10 volts to the boiler. And we've programmed the boiler to output 90 degree heat or water, 90 degree water when it sees that 10 volts. Now, that's not very efficient. And it might not be that when we put it in hand, we might not want, the boilers firing at full power. So what you'll see, and if you look on, you don't have to do it now, but at some point like later or tomorrow, have a look at the images within the folder and you'll see that orange 10 volt power supply has a variable voltage output. So you can select whether it's like outputting 1 volt, 2 volts, 5 volts, 10 volts. So what you'll tend to see is it will be set around, 6 volts. That power supply will be set at 6 volts. So that then translates to, let's say, 60 degrees or 50 degrees heat, water coming out of the boiler when it's in hand.
Is that set from the boiler control inside where that H1 input is? Obviously, there's some sort of variable pot that you can adjust, and it's from the manual that will tell you what voltage is. No.
So the voltage, I'll tell you what, guys. Let me to explain that. Don't know if you can make that out. Oh, that's a bit better. This we come back to it, but that power supply that's outputting that voltage, that 10 volts, is this orange power supply here. And you see that little black circle there and the numbers around it. That's what determines that output voltage. So if it's wound all the way over here, that's max 10 volts. If it's over here, it's like 1 volt, and if it's somewhere in the middle, it's like 5 volts, 6 volts. So that's, in answer to your question, Mike, that is what's determining the voltage that's coming into the boiler. But then there's also going to be settings on the boiler where we say something on the lines of, we program the boiler. So if we're seeing 10 volts from this power supply here, I want you, Mr. Boiler, to fire out 90-degree heat water. If you see 1 volt, then I want you to fire out 10-degree water, and then it will work out that range.
No problem, mate. Is that dip switches inside that? Is it like a dip switch, or are you programming the boiler? Well, what would the voltage part I get, but when you go into the actual boiler, what's your determination? How do you do your settings?
Yeah, it might be on an older style boiler, it might be dip switches, but most likely modern boilers, it's just, they've got a little programming screen on it. Okay, and you just bring up the manual, read the fucking manual, and it'll tell you in there, and you just navigate it.
Cheers.
Just looking at the manual, Chris, there isn't normally, like, I know, like with stuff that, from things that we've done with laser machines before, what have you, normally you have like a voltage sort of graph, like almost, so it says, right, okay, 0 to 10, and then indicates what each one's going to give. But I can't see anything in here for that. But you'd normally expect something like that, I'd thought. But
yeah, Daniel Mason, I think you're holding up the right thing there. Everyone look at Daniel Mason's screen. It looks something like that. So it might already be predetermined, guys. You might not have to do any programming or tinkering around with the display on the boiler. It might already be predetermined. Nice one. Cheers, Daniel. Right, let's go back here. So are we happy, before we get into the automatic control, are we just happy with those principles? That when it's in hand, basically the boiler is receiving 10 volts from that power supply, or whatever we've set it to. Let's just say a constant 10 volts. And just let's go back to the power supply. It's simple stuff, guys. We don't need to spend much time on it. But ultimately, a power supply, if you're not familiar, it receives AC. So we're firing into it 230 volt AC, and then it's outputting 10 volts DC. And so 0 to 10 volts DC is a very common, 0 to 10 volts is probably the most common variable control voltage that you'll see. You're going to see 0 to 10 volt control voltages, or you're going to see 4 to 20 milliamp control voltages. We're not going to get into the 4 to 20 milliamps. It's not as common in building automation. You see it a bit more in industrial controls. I'm not going to get into the details and the differences of that, but ultimately it's a variable control voltage known as it's an analog signal, because it's not digital. It's not on or off, 1 or 0, true or false. It's a range between 0 and 10, and then that 0 to 10 range maps to, like in this example, 10, let's just say it maps to 90, 1 maps to 10 degrees in temperature. So we're feeding it 230 volts, and then out the other side we're getting 10 volts and 0 volts. When it's in hand, it's just very simple. We're just closing those relays there, and we're feeding the boiler with the 10 volts and the 0 volts, and that's it. Now let's go back to that 3-position cam switch, and now we're switching it to auto. So it's gone from here. Now obviously we need to go through the off position before we can get to auto. So we're going here, we're going here, and then we're going to auto. So now we're in auto. This is what happens to the control voltage. And we're firing up, we're activating relay 7 now. and it's exactly the same principles. So now relay 7 contacts have closed, and at the same time, guys, we've got to bear in mind, because relay 6 is no longer energized, these contacts have gone back to their normal state, which are open. So the boiler's no longer seeing that constant 10 and 0 volts. That's been cut off now. It's an open circuit. It's an open circuit. But what we have done is we've closed the circuit over here on relay 7. Now, sorry. Can you tell me, mate, what's happening now? Now that we've opened relay 6 and we've now closed relay 7. What's happening now? What's the boiler seeing now? I think you're on mute, buddy. Can't hear you.
What's happening now? Don't we need to go to page 11 now to see what's he doing?
Yes, exactly. So let's go to page 11. So everyone go to page 11. And actually, I think it gave us even more info. Page 11, D117. So page 11, D117. So is it Savvy?
Yes, Savvy. Yeah, that's it. Yeah.
Savvy, cool. So we're on page 11, D117. What does that tell you?
D117. Where is D117?
We got D over here, and we got
D117.
Did I say 1?
That's page 12, yeah.
Maybe I'm the wrong
page.
Wrong page. D.
Sorry, guys. D. There we go. Thank you. D, and then we got 117 over here.
Okay, page. Okay, D117. That's coming from is it going to D117? What's that? Mini box 01 to 10. Is that the one where it's going to from?
Yep, that's the one, mate.
Yeah.
That's it. Basically, that's just telling us where we need to go to find out where that thing is on the drawing. So you'll often see that on schematics. It will help you sort of get there quicker rather than going through the whole thing. So
okay.
So you can see that D on the horizontal and 117 on the vertical
references. Yeah, okay.
lines up there. So, and yeah, exactly that. So we're now using this mini box from Zenio KNX module. If you ever do any KNX controls, guys, I highly recommend Zenio for any HVAC control. Really, really good hardware. Like, it's compact, it's reliable, it's affordable. The guys there really supportive. Like, they're a good bunch. So I highly recommend using Zenio if you're doing any HVAC control with KNX. But yeah, basically it's telling us to look here. And what this is this is a control module, a PLC, basically. Let's just call it the PLC. And this is a PLC that gives us, you can see here, it's got 2 of them. So we've got 2 0 to 10 volt control outputs. So what that means is we've got, let's go back to red. So we're actually now using the signals from here, and they're going, let's go back. So they're now feeding. So it's actually coming over here. So they're feeding in here, because obviously these are closed now because we've energized relay 7. And that's now
controlling the whole thing.
Controlling our boiler. So now in auto, all the controls is determined by what, Paul Spearman?
So that's being controlled by the PLC.
Bang on, exactly. Thank you, mate. So yeah, so in auto, all the controls is determined by the PLC. In hand, all the controls is ultimately decided by whatever that PSU, that power supply, is firing out. So it's as simple as that. We're just going from the power supply voltage to the PLC voltage. Now, what then determines, Dan Eglinton, what now determines the output of that, or sorry, let me say it again. What now determines what voltage that boiler fires out?
In terms of control, like as in what's coming from the PLC?
Yeah, we look at it we take a step back and we look at the whole system as a whole. What determines that voltage? Like whether it's 1 volt, 2 volts, 3 volts?
Whatever's been programmed into the PLC.
Yeah.
Whatever's been set.
Yeah, so whatever's been programmed within the PLC, and then if we take it another step back, like what might that look like? What might we program in the PLC?
10 volts would be your 90 degrees again, but it's scalable to either. So
I'm asking you a tough question, mate. This is now we're getting into sort of HVAC control philosophy and plant room heating control. So that's a tough question, mate. But basically, what determines that output from the PLC is obviously we need to program that PLC, but it's all determined by the demand. Let's just think about it as a house.
Yeah, if you had thermostats and things like that in the room, or what like you say, what the demand actually is. So if you had a controller on flow temperature or
yes,
things like that.
Exactly that. Yeah. So now we're getting into deeper controls here, but we're looking at flow and return temperatures on pipework and the demand in the rest of this is a school. So like the rooms in the school, the demand there, how much heat we're sending out of the boiler and how much is coming back. And then we're doing what's called like a PI loop, which sort of, determines then the output of that PLC, which is ultimately the output of the boiler in a voltage range, And guys, that is pretty much it for today in terms of the boiler control. How do you all feel about that?
What's the in that Zenio mini box?
Yep.
Where do you program the software or the logic to? I know you were talking about sensors and everything else, but do you have to program any logic in that box?
Yeah.
Okay.
So I haven't opened up ETS for a long time. You see my screen?
Yeah.
Yeah, basically, I haven't got my license key plugged in, but let's bring up Loxon instead. Basically, you're connecting into the PLC, whether you're connecting in through an Ethernet cable, so via IP, however you want to do it, whether it's cable or Wi-Fi, or maybe you're plugging in directly using like RS-232 or 485, a protocol basically to connect in and communicate, and then you're basically programming it. Yeah, you're creating the logic within the software, which you then download to that module, and then that module knows what to do, basically, in simple terms.
Is it standard ladder logic, or has it got its own sort of language and software?
KNX isn't ladder logic, no. Ladder logic you'll see is more common in like industrial PLCs like Siemens and Rockwell and all of those. KNX is a bit of a nightmare, to be honest, guys. It's not the most intuitive system to program. It's done through what's called fucking hell. Someone help me out.
Hi, may I help here? I have my ETS software license active now. So if you like, so I can share and show him the code, how it's exactly working.
Sure. Do you want to share your screen then?
Yeah, like if they are interested in seeing the actual code, how it's working.
Cool. All right. How do you pronounce your name?
Yeah, it's functioning. Like from project, I'm working on it, so he can actually see how it's going.
Yeah. So
the
guys,
addresses and all of that.
Okay. Is it Marceline?
Marceline, yeah, right.
Marceline.
Yeah,
cool.
Marceline.
Cool. All right. Well, anyone that's interested to sort of stay and have a look at ETS, please stay. But that's pretty much it for today in terms of the boiler control. I'm going to stay for like another 15 minutes. We go over this. Any questions we can go over. But yeah, that's it for today, guys. Hey guys, me again, and this is just a reminder to actually download those schematics for this project so you're able to learn on a much deeper level. As mentioned at the start of the video, they can be found in the description. So click that link. You'll be taken to our free community where the first thing you'll see will be those schematics. So download them, come back to this video after you've downloaded them so you can actually get to where you want to go, so you can actually understand schematics, so you can become a better engineer, progress your career, progress your business, whatever it might be. Download those schematics. It will seriously help with all of this. Right, Merceline, I've got to work out how I can allow you to share.
Sorry, Chris, I joined a little bit late. These are all recorded, aren't they? Did you say?
Yes, mate. Yeah,
awesome.
They'll be in the shared drive tomorrow morning.
Sound. Thank you very much.
All right, mate. Group address.
Sorry, Chris, can I pop a question for you before we...
Please, I have a question too.
Yeah, who's first?
I don't mind.
Let him go first.
All right. So the question concerns the relays 6 and 7, which are supplying the manual and the PLC not 10 volts to the boiler. So they are double pole.
Hang on.
Yeah.
Hang on. Let me engage my brain.
All right.
Cool.
Yeah. So it's page 3.
Page 3.
Yeah, D35 and 36. So the relays 6 and 7.
Yeah.
So the previous relays, all 3 pages of previous relays only broke the positive or the line contact, and here we have these two poles breaking both. Why is that here?
Because let's say we only have it on the 10 volts, right? We only have it on the 10 volts. You tell me, mate. So we're only doing it on the 10 volts. So the boiler's only seeing 10 volts.
It's gonna fire, isn't it? Because there's still gonna be 0 volts on the other pin.
Where's it getting 0 volts on the other pin?
Well, it's not, but it's
got nothing to reference, has it? It's got nothing.
There's no potential difference.
Yeah, we need to give it that 0 volts reference as well for it to do anything. But that's why we've got both the 10 volts and we need to also feed it the 0 volts.
Yeah, that's the question. Why do we need to break the 0 volts then? We can just break the 10 volts and it's not gonna fire like all the previous relays with it.
Nothing will work without the return leg. So if we had a 0 volts on this board here, then you might be able to argue that we don't need to provide it, but that's not.
My question is like entirely. No, we miscommunicated. Sorry for that. Why do we need a second pole in there to break? Why not just keep it connected? So, for example, the lamps to the left are connected, are permanently wired to 0. Why not do the same here?
Because we're switching from the 0 volts. Sorry, mate. That's a good question, Ivan. Because we're going 0 volts from the power supply, right? But then we're also taking 0 volts from the PLC. And it's just, again, I don't want to go into too much detail and complicate things, but basically I don't want the same reference voltage being used from let's just say we keep the reference voltage from the power supply. It just adds complications, especially on sensitive analog signals like a 0 to 10 volts. I don't want to risk anything. I just want it to be completely 100% true from the source, which is why I'm switching from the 0 volts on the power supply when it's in hand to the 0 volts coming from the PLC when it's in auto. It's just the right way to do things, basically.
All right, yeah. So basically, every single like this little circuit has their own. I wouldn't say earth, but like reference ground.
Yeah,
pretty much. All right, yeah.
And this
Understood. Thank you.
This is a big thing in controls, guys. Like it's not having, like, if you're using multiple different power supplies, like you might have a 24 volt DC power supply, you might have a 10 volt DC power supply, you might have 12 volt DC. And what can happen is, because there's different 0 volts, different references, if you and we're going off on a bit of a tangent here, guys, so but anyway, if you don't reference all of those 0 volts together, then there can be like floating voltages, and ultimately, in a nutshell, it can cause issues. So either you have like things segregated and 100% segregated, or if there's a chance that like the multiple 0 volts can cross, you want to make sure that the 0 volts are all common together across different power supplies. Or what you do, and this is another good thing to do, good practice, is you have not only all of them common together, or, well, you could have them common together, you could have them common together through earth as well. So you might have like a panel on a site here, and then you're adding another sub panel, but that's got a separate power supply in it, but they're both feeding the same machine. But how you might not have a cable to reference those two 0 volts together, so that could potentially cause issues. So what you do is you just connect the 0 volts on this panel to ground, to earth, and the same thing over here. So then they've got the same reference, and that's going to avoid any intermittent potential issues. Like, you might things might be fine, but there's a potential opportunity for problems to arise. You've also got to be careful if you're on a heavy industrial site where you've got things like dirty earths, where there's a lot of noise getting pulled to earth, then you might not want to do that, because if you're referencing your sensitive analog signals to earth, and there's like loads of heavy machinery going on and off, and there's these power spikes, you don't want to be referencing those sensitive analog signals, in this case, to earth. So it's a difficult one to judge, but they're just things to be aware of, guys. That's all.
I have a question.
Yeah, far away.
Okay, first, thanks. This is quite enlightening. Thank you very much. Just to firm up my relay logic reasoning, I want to go back to the first page and then ask just taking information from the document itself without knowing what was the intention. So I was thinking that for the gas, please, if you can zoom in, I can't see very well.
Yeah. Sorry, guys, I'm going to have to shoot after this question. Marceline, what we do is the start of next session, if you're around on the next session on Friday, we start with a quick overview of ETS, if that's all right with you.
Yeah, sure. No problem.
Cool. Thank you.
You're welcome.
Yeah, so sorry, mate. Carry on, James.
Okay, so for the gas on and off relay.
Yeah.
So I was wondering, the mere fact that the gas valve closed is wired to be red, to the red light. Ordinarily, it's telling me that, the 24 volt, just as soon as the transformer is actually in good condition, the 24 volts.
So you've got 24 volts here from the transformer.
Yes. So it goes through the contact 1 and then gets to that point, telling me that, everything was really good in our 3, the Thermalink and the panic button, everything is good. So ordinarily, that makes sense. But if I look at if that condition exists, if I look at the wiring of the auxiliary relay, it's telling me that it's normally closed. Meaning about that same time, the same voltage just jumps from the common and just goes straight through the normally closed. And then it will switch this guy because it takes precedence. So it will also switch this guy to tell me there's a fault. So I'm thinking that should either be a normally open too.
Yeah. So this is what we talked about earlier. as a design engineer on this, I should care more, but I don't because I'm a design engineer and I'm not the person on site commissioning it.
Okay.
And I can't ever, unless I've worked with the piece of equipment and I know exactly how it operates, physically on site, I can never be 100% sure whether it's normally closed or normally open. So as a design engineer, I've just gone normally closed. And yes, it might be wrong. And yes, things might operate the opposite way round. It's a common thing. What I haven't done as well, so obviously I've built this system now and I've tested it and stuff. I've got a load of like physically printed out schematics where I've just covered it in red pen where I've made little mistakes. But what I haven't done, and I probably should have done, but it's good because it creates this kind of discussion. What I haven't done yet is I haven't corrected those mistakes onto the actual drawings here. So what, if I remember correctly, I've probably actually changed that to normally open and changed this one to normally open, but I just haven't got round to correcting it on the actual drawing, which is pretty standard as well. The commissioning guys, they're red pen the schematics, they take photos, they send it back to the designers, and the designers will never update the drawings.
Thank you very much.
I've got to shoot, guys. Thanks for today. Hopefully that makes sense.
Cheers, Chris.
I'll do that. No worries, man. I'll do that. That technical overview thing of the pumps ready for Friday. So I'll do that. Tomorrow morning, as well as uploading this to the guys that are watching offline. Do you have a question?
Can you hear me?
Yeah.
Okay, I'm so sorry. Okay. Now my question is, well, when you are like showing sensors or you're showing relay or different things in the drawing, is it possible to shift to the images that you have and show us there, or maybe in menu that you have?
No, because I'm not going to, because it means I have to stop mirroring my iPad and like navigate around it. Just what I'd suggest for you guys is just, we will do it occasionally when it makes sense, but generally speaking, no. If you just have like the images up on another page, you can actually work it out from the labeling of what I'm talking about, and you can reference it to the images in the photos. So it should be pretty obvious for you guys to do it. So not to be a dick or anything. It's just gonna be a lot of faff for me, and it's going to sort of take time and whatnot. So when it's absolutely critical that we do, so like with the power supply yesterday, I thought that was important where we could actually show that potentiometer on it. But generally speaking, no, they're just sort of extra things for you guys to sort of look at.
But this is the same systems like you have built it, and the drawing is.
Yes, so the system here, the designs here match.
Match this, okay.
Match the images, yeah. 99%, apart from what I just mentioned about this MPCB. So if you look at the panel images, you won't see an MPCB. You'll see another contact and overload. Reason for that was basically, one, it just looks better having two of the same devices. I was going to put an MPCB in there just so I can explain the differences between the two. And then I realized that actually I can't actually take some of these like the tripped output from this unless I added an auxiliary contact, which I didn't have. And I had, so basically it doesn't really matter, but I decided just to go with two of those in the end. So just to reiterate what I was saying a minute ago, guys, we're not concerned about this for pump 2 because it's exactly the same. Pump 2 is exactly the same as pump 1. We're just going to be focusing on pump 1. So any more questions? Actually, we come to questions again in like 15 minutes or so, guys. So let's get into the boiler primary pump. So it's this is what I call a dumb pump. So can anyone tell me why I'm calling this a dumb pump and why we might have like a smart pump?
This is full capacity pump. You're just putting full capacity of it. You don't make any frequency converting for.
Yeah, that's another way we can look at it. Yeah, it's kind of so that's one thing. We can't actually control the speed of it. It's on or off. Anything else that makes it a dumb pump? People, anyone?
It doesn't have any protection against anything, like a faults inside of it.
Yeah, exactly. Yeah, so it has like no sort of internal fault mechanism. Like there's basically with this, it's like an old school pump with no electronics, no fault outputs, no enable outputs. And what we see on Monday is you'll see the difference between a dumb pump and a smart pump and how they operate differently. Well, they operate pretty much the same way, but there's different controls for it. So this is like a very basic standalone standard pump, basically with no smart control on it. Also, I mentioned yesterday when I was referring to the boiler interlock circuit that maybe I should have had the boiler interlock circuit. So this circuit here continuing onto this page as well. Can anyone tell me why I was considering that? Why I mentioned that?
You cannot run the boiler without this pump. So the pump must start first, and after this, the boiler or the burner will start.
Yeah. I'm sorry, mate. I'm talking more like why haven't I included that interlock circuit on this page with the boiler pump? I'll tell you. So I could have extended this boiler interlock circuit, which if we go back, that's enabled when the pressurization unit is healthy. So providing we got the right pressure and there's not an overpressure and there's not an underpressure and there's power going to it, that means that's healthy, which means that circuit is enabled. So, and we've obviously got our boiler control tapping off that. So for boiler 1 and boiler 2. Yeah, and it goes there. There we go. And I could have done this either way. So I could have extended that boiler interlock circuit and had the boiler interlock circuit, and I could have had the controls for the boilers also tapping off that. So rather than it just tapping off the safety circuit, I could have had it tapped off the boiler interlock circuit. So there's a couple of ways you can think about this. Either like the first way of thinking is, well, if the boilers aren't firing and aren't being controlled, then we shouldn't have the pumps running either. So if the pressure isn't right, then let's cut the control from the boilers and cut power to the actual pumps that are sort of running around the primary side of that heating circuit. Or you could say, well, if there's a pressure drop or a overpressure, then maybe you do want to just run the pumps and keep the heat that's in the primary side of the circuit just running and not waste that heat, and then it exchanges over to the secondary side. I think this is just down to really the M&E designer and what they specify, or down to you as a designer and what you think's the right way to go. Probably if I did it again, I probably would have these pumps, the pump control here, coming off that interlock circuit. It's not absolutely critical, but I think it just makes sense. If there's like overpressure, we don't want the pumps running, on the primary side of the system. So yeah, that's just preference really, but it wasn't specified specifically in the spec. So I've just done it this way. I mean, the pumps are still not going to switch on if there's an issue, if there's a safety issue, because we're still coming off the safety circuit. And can someone tell me what what determines whether the safety circuit is enabled or not enabled? Ricky, my boy, how you doing? Can you tell me?
It's the gas. It's doing the see if the emergency stops and the interlock of the gas system.
Yeah. So still we're still using the safety. So if the if there's an issue with the gas, like there's a gas leak, then obviously it's not a healthy condition. If someone's hit the e-stop over here, then it's not a healthy condition. If there's an overheat above the boilers, and also if the fire alarm triggers. So we still got some level of sort of safety there that's feeding these boilers. But like I said, maybe in the future, next time, I might have them coming off the interlock circuit. So let's get into the controls. So what we've got, and in terms of the power, it's not quite the same as just if we switch on power to the panel, like the boiler, then we have power to the boiler, or boiler pumps in this case. What we've actually got here, because we're using a dumb pump, we need to, and there's no sort of intelligence to it, we need to make sure that, you know, if there's any problems, that we're switching the pump off. Like if it overheats, for example, or there's over temperature, thermal overloads, etc. We need to make sure that we're cutting that circuit, and we're doing that through contactor. Well, actually, we're doing that through this overload relay, which is connected to the contactor. So let me just talk you through that before we get into the actual controls of it. So we got our feed, and that's going through an MCB, standard stuff. And then that's going into, and you can reference the pictures, by the way, guys, in the motor control folder. The two contactors that I've taken, like a close-up image of the two contactors within the panel, because it will be easier to visualize what I'm talking about then. But we've got our feed going into the second terminal of our contactor, and then our overload is basically screwed into the bottom of our contactor. And then what we're doing is we're wiring out of that second terminal, and then we're feeding it back in to the first terminal. So that's L1, and then L1 is then going out of this first terminal here, and then off to the motor in the field. And then with the neutral, it's just straightforward, just into terminal 3 and then out of terminal 3. So when you're wiring like a contactor overload, it's important that you have the full load going through the overload, basically, or contactor. You can do this multiple ways. So some people, and you don't necessarily have to have the neutral. You could have like, say, the neutral just on its own going down here and into the motor. And then with L1, you'd probably do it more like this. You'd go into the first terminal and then like this. Actually, let me just rub that out. You can do it multiple ways, basically. So you could go into the first terminal and then out here and then like this and then off to the motor. So you can do it with you can do it with the line. You could also do it, so say the line just goes straight through, but then the neutral, you're going like this. So it doesn't really matter how you do it. I just habit, and how I've seen other people do it is I just put both the neutral and L1 through. And yeah, I just do it like this. Same thing, whatever way you do it, and you don't have to put the neutral in there. Also, again, it's reading the manual. So in some manuals, it says don't put the neutral in. like the ABB one, actually, which this is, does actually say in the manual, you know, just put L1 through the contactor and overload. You know, you don't need to, the neutral can just sort of go off on its own. But just through habit, I just do it the way I've done it here. There's no right or wrong way to do it, really. So we've got our feed. So let's say our feed gets to this point here. And then you can see these are similar to what we've been going through with the relay logic. So these are in its normal state. These are all normally open. Okay. And then over here, this is our coil. So just like a relay, this is our coil. So when this is energized, that pulls in these three contacts. So another way to think about it is it's like it's a three-phase relay. So that's normally open. And like I said, it's going the way we've wired it. It's then going over here, out here, and then back out. And then, yeah, our neutral's just going straight through. So let's switch it on. Just do that. So in terms of switching it on, and then we'll come back to like how the overload works, because it'll be easier to switch it on, so you can see how that's working first. So we switched it on, and how we do that. So let's first focus on the hand side. So we got, again, same as yesterday, we've got our hand, off, and auto. So this is our selector switch on the front of the control panel. And this gives us, yeah, the ability to either decide if we're running things manually in hand or auto, where the PLC takes control, and the programming and, yeah, lots of other stuff determines whether the pump comes on or not. But when it's in hand, that means that the pump is on all the time. Like there's power, or there should be power going to that pump, unless, which we're going to go over in a second, unless there's issues with the overload, like the overload's tripped out. So let's look at that first. So what we've done is the switch is in the off position, and we're going to switch it to hand. Okay, so that's that. That's not there. So off the safety circuit, going down here, and the first thing that it comes to is the normally closed contact on this overload here. So again, if you're looking at the images, you'll see, if you look closely, that terminal 95 and 96 are normally closed. So that means if in its normal state, like the overload hasn't tripped, there's no issue, it's in its normal state, then that is closed. Which means that when we switch that to hand, that power can go through here, through the hand cam switch, down here, through the overload contact, because everything's in a normal state, and then it powers up this contactor. So it brings those contacts in now. So let me draw it. So yeah, so now it closes those, which then allows that to actually pass through with the neutral as well, and it switches on the motor. Now, Luke, is it Doherty?
Yeah, that's it, Doherty.
So now, mate, what would make that 95, 96 circuit, or sorry, terminal open? Like, it's in its normal state now. What would make that sort of switch the other way?
If it's like an overload on the motor,
yeah,
like an overcurrent, or
yeah, overcurrent, overheat. So in some cases, if it's like overcurrent or short circuit even, then the MCB would trip. But like a thermal overload, like for example, let's say like the bearings were starting to go in this motor or this pump. Say the bearings were starting to go, and there was more resistance, and it was starting to overload that circuit, and there's a thermal overload. Then what would happen then is this relay, this overload relay, would detect that, and then it would trip this, which in turn, because this is in series with the coil that brings on this contactor, it will then, because that then goes open circuit, it then trips this out. It trips out the contactor, which in turn trips the pump out. Now, this is really important, guys, because I've seen people who should really know how to wire these, wire them wrong. You need to, it's absolutely imperative in terms of safety and like fire risks, and just making sure that, if there is a thermal overload within the motor, that you are actually killing the power to it. So it's absolutely critical that this normally closed contact is wired in series with the actual A1, A2 coil that actually controls the contactor. Again, if you look at those images, it will make more sense, hopefully, than me just drawing it here. So I just want to run through that again, and then we go through some questions on that. So in the off position, all right, but then we're changing that to hand, which means that goes down here. The overload over here is in a healthy condition. Nothing's tripped out. So that remains in its normal state of closed. So it travels down here, and then it gets to the coil of this contactor. And because this is good here, it allows us to energize this contact. So that's good, which brings these contacts in. So then we've got power flowing through the contactor and the overload. So they're in series with each other as well. So contactor, then the overload, and then around, and then to the motor. And then with the neutral, it's just straight through. But this has been running in the field for like 5-10 years, and the pump's starting to deteriorate, the bearings are going, or something's happening where it's just, it hasn't been maintained, it hasn't been serviced, so this is starting to wear out. So what then happens is there's more resistance within the motor, and this overload can sense it. This overload senses that. It's exactly what it does. And eventually it will trip out. So what happens is that basically trips out there. So let's draw it again over here. So it's tripped out. This is still in this is still in hand. Nothing's changed up here, but we've got this going down here. But now, because that overload has tripped out, there's an open circuit here. So this can't travel to the coil of this contact, which means now that it's cut, or those contacts, I'll draw it better actually, that these contacts are now open. So that's how the overload trips the actual contact. And that's why it's so important that you have this normally closed part of the overload in series with the contactor. Now what will happen is there's a couple of settings that you can set on this overload relay. You might have like a manual reset, or you might have like an auto reset. So the auto reset, you can switch it to a setting, and basically once this overload relay has sort of cooled down, and like the metallic strips that have tripped it out, or however it works, it might be an electronic version, but once that's sort of gone back to normal, it will automatically reset itself. And then if everything's sort of in the same condition over here, it will then just go back on. Like the motor will then just come straight back on. Now, I don't think that's good, because if it is a problematic motor pump, then you're just switching the problem back on. So with overload relays, I always set them to manual reset. So it actually needs an engineer or operator or someone to actually physically go in and reset it, because it's like, well, it's tripping for some reason. Like, let's investigate. It might be that, that has been in the field, that motor, that pump for 10 years. It's probably about time we replaced it, rather than just sort of bringing the same issue back. So you'll see again on those pictures that there's that blue button, and that determines whether it's in auto or manual. So before we go a little bit further, does anyone have any questions just on the sort of the power side of the contactor and on the overload relay?
I got two, both on the overlay.
Sure, go for it, man.
The first one is probably regarding the double connection, so the loop back. What I've understood from your explanation is that we should either loop the live back or the neutral.
You just leave the neutral out?
So why do we loop it back a second time in the first place then?
Why do we loop the the feed or the neutral back? Why do we choose
so essentially, why not just make the same thing like it's with neutral, or just pass through once and that's it?
Well, you can do. It's like having like a double pole MCB. You're sort of keeping things safe on the neutral side as well. But if you look at all the regulations and stuff, you don't actually have to do that. You only need circuit protection. Can't think of the right terminology. I think it's circuit protection, whatever. You only actually need that on the live, on L1, or obviously if it's three phase, then it needs to be on all of those phases.
All right, thanks. And the second is regarding the overlay. So essentially, doesn't the overlay has built-in contact breakers? Sorry?
It's an overload.
Yeah, sorry. Yeah, doesn't the overload have? So why should it trip the contact? Can't it just cut the power like an MCB or something?
Yeah. So what actually trips? So this device here, that's very important. It's a very good question. So let's just go over that again. The overload doesn't actually trip out the contactor. Who can tell me what actually, like in terms of the sensors or the sort of biometallic strips in the overload, that doesn't actually trip the contactor out. That only senses the thermal overload. What is it that actually trips the contactor out? Who can tell me?
The normally closed switch for the overload becomes open, so then the contactor can't get energized.
Yeah. So that's why it's so important that you're aware. You can't just wire it, like this and expect it to work properly. And just having, let's say we remove that and you just have it going like this, because what will happen is this will detect a problem, but you're bypassing the thing that actually trips this contactor out. So it senses that it's overloading, but nothing's tripping out the contactor that actually provides power to the motor. So you're just, and imagine if that gets worse and worse and worse, the bearings get worse and worse and worse, and it ends up being metal on metal, and then it could potentially cause a fire, and then you've got a fire in your plant room.
So that's the question. Can the overload act as a circuit breaker? Does it break the circuit in case of fault?
So that's when you're saying like, does the overload act as a circuit breaker? Not on what we're looking at here. No, that's why we've got like a circuit breaker up here. Well, an additional sort of short circuit protection. But if you're working with an MPCB, then you've kind of got you've got the circuit breaker or MCB and the overload built into that one device. But we're not focusing on that. But you can do what we're talking about. You can do in a similar way using an MPCB.
All right, understood. Thanks,
man.
Chris, can I make a comment, please?
Sure.
Okay, so I don't know if I don't think I've ever seen a single phase contactor. So I'm thinking, I'm glad that he asked the question about the wiring of the contactor. So I've only seen a 3-phase contactor for red, yellow, and blue.
I've never seen a single phase contactor either.
I'm glad I saw this. I'm glad I saw this because it's in the wiring of actually rerouting the middle line through to the very beginning line that helps us truly complete the 3-phase of the contactor. So I'm glad he asked the question because it just helped me as I think if I've actually seen a single phase contactor in my life, and I haven't. So it makes really good sense that the only way you can complete the connections of the contactor, because it's three phases, is to actually do this looping. So I appreciate the question, and then I appreciate the explanation.
And you might be asking, well, why are we using a contactor? Like if it's a single phase motor pump, why are we using a contactor? Like why don't we just use a relay? Well, because the relay, you can't chuck a overload relay onto a contactor. So it just makes sense. It's just like the standard really, that if you're using if you're switching on and off, controlling a pump or a motor, a dumb pump or motor, then and it is single phase, you just use a contactor, which are designed for 3-phase, but you just wire it in that way, and you've still got that overload functionality.
Can I jump in, Chris, at all? Can I ask a question? It's me and Michael. Hiya.
Hi, mate.
Yeah. So as I'm looking at the drawing, you've got C1 and your overload, but physically, when you actually go to a panel, that whole unit, rather than it being drawn like that, would it be one fixed block rather than having
this here?
That and the actual overload, it would be in one block, wouldn't it? Usually,
these that's all the same thing.
One block, The second question,
because if you look here, right, we zoom in, overload one, and if you look here, we've got 95, 96, 95, 96.
Perfect. The second question, if you don't mind me asking, your control circuit is all 24. I know you got the line coming from safety, but this is the actual control, the selector switches and everything else is controlling the C1, but that's 24 volt. So is the contactor that you're using not the voltage supplying the pump, but the contactor C1 is a 24 volt contactor?
Yeah, it's just exactly the same as a relay. You've got to make sure that the coil voltage on your contactor or relay matches your control voltage.
Thank you. Cheers.
No worries, man. Right, so let's move on, and we'll do some more questions at the end. So we've got the power and the operation of the pump there now. Let's now have a look at what's happening when that overload trips and when it doesn't trip. So healthy condition, we're still in the hand position. Let's just stay there for now. Healthy condition, overload is good. That means that we can bring on the contactor. So great, we got power going to the pump. Okay. Which means, so we've also got, if we look here on the actual contactor, that's got a normally open contact on the contactor. So that we can then use that 13 and 14. We can then put our 24 volts in there and then do something on the other end. So we can then know if that contactor is powered up or not powered up. So that's exactly what we're doing. So over here, again, 13, 14, C1, which is coming from over here. When that contact is energized and the contacts are pulled in when everything's healthy, that contact will pull in and we can energize this relay here. R13/2. What does /2 mean, Mark, with the headphones?
Sorry?
What does this /2 indicate on
the number of the contactor? Number of the contact.
Yeah, well, yeah, it's the same thing.
The second contact and the first at the top of the page.
You're kind of on the right lines there, mate. So the /2 is how many poles the relay has.
Yeah.
Or contacts, you could say, like you said.
Okay.
So just as a little refresher there. So R13/2, two poles on that relay, and like we said yesterday, every or pole 1 for every relay is for the mechanical electrical stuff. Pole 2 we're using with the PLC. So here we go, pole 1 for relay 3. So because that's now energized, we're now this is now closed. So now power's going down here and it's powering on that enabled light. So someone just give me a quick recap of what I've just been through. Lawrence Phillips, how you doing, mate?
How you going, bud?
All good, mate. So yeah, just do a quick recap. So healthy condition, pumps on.
So healthy condition, we've got the pump on. Where are we? Healthy condition, pump on. So that's going to pass down through the 95, or normally closed, 96. It's going to bring in your A1, A2, pump's going to run.
Yeah.
And then we're going to go up here to R1, R13/2, so the C1, the 13, 14.
Yeah. I was going to say you skipped ahead then, but yeah, so C1, we're starting there. So carry on, mate.
So yeah, the C1, 13, 14, that would then go to normally closed.
Yeah.
Then it would go through, energizing your A1, your A2 has got your common voltage, and then on the R13/1, that then becomes closed and you get your healthy enable light.
Spot on, mate. Good job. Yeah. So that's in the healthy condition. Now let's look at what happens in an unhealthy condition when there is a overload, and what happens sort of on the lights on over here. So again, same thing. We've got in hand, but now there's a fault. So that's tripped out. At the same time, it's tripped out the contactor because we've wired it correctly in series with the coil. So yeah, so that's good. That's tripped out. Now there's no longer power going to the pump. But over here, so as you can see, we got OL1, overload 1. We've also got overload 1 here. So as that trips out, this contact closes because they're just working the opposite way around. And we've got that coming down here, energizing relay 12, and then relay 12 contacts over here. And then we're coming down here and we're bringing on that tripped light. So now we've got that visual representation on the front of the panel that it's tripped out. So that's helpful for an engineer on site, a facilities manager to see, oh shit, there we got a red light. Let's have a look at that. Oh, boiler 1 pump has tripped out, and then they can go and investigate. So that's basically what's happening on the sort of the controls side. So now let's have a look at that operation through the PLC. So what we're doing now, so we're going from hand, and then we're switching through to off and then to auto. So now we're using the PLC. Whoops. So now we're using the PLC to control it. So what we're doing is we're passing that safety circuit through that auto, or the auto side of the 3-position switch, and then that's going off to page 10, B10, 02, sorry, B102. So if it will allow me to actually move the page, which it doesn't seem to want to. So what did I say? What was it? B, there we go. So what does that look like? So B and then 102. So that's taking us to there on the drawing. Now what, someone tell me, is Marceline here? Oh, I saw her. Oh, she switched her camera off. She's left us.
No, I'm here. Sorry.
Oh, you're here. Cool. So
Yeah.
what are we looking at here then, Marceline? What is this that we're going into now when we switch it to auto?
Isn't it the same as the KNX Plus, that when we get a feedback of it?
So this KNX module.
Yeah.
This KNX module, so the Zenio all-in-one box is like a PLC, right? It's a PLC. Now, what is A1 on this PLC? Like, we've got inputs, we've got outputs. What is the A1, do you think?
Is it the heat emitter?
In terms of control and output, because this is going to pump 1 here. So let's just recap. So we're going, so we're in auto. We switched it to auto, and that safety circuit power is now going off to page 10, which has that PLC on it. So we're going.
Okay, so we're getting a digital signal, something like that.
Yeah, so digital signal, so only ever on or off. So we got our on signal going into one side of A1, and then so what is A1? Can anyone help?
An input.
Digital output.
Digital output.
Input.
Input.
It's not an input, guys. No.
An output. So it's like a little relay contact.
Yeah.
Changing.
Yeah, exactly that. So now, because now we're using the PLC for the control. So this is a volt-free relay contact, and we're using the intelligence of the PLC and how we've programmed it to then switch that digital output, which is a relay. So we're now using the programming to switch that on and off. And this is ultimately what's going to switch the pump on and off, providing we haven't got issues downstream with like the overload and other stuff. So this is now how we're using the PLC to control it, rather than just having the 3-position cam switch on hand. So I'll just go through that again. So we've got our controls, and then we're going through the auto side now. And this is 24 volts going off to page 10. Okay, so page 10, and basically that's continuing. We've got to just imagine it's only one bit of cable, and now we're feeding into here. Okay, and this is the 24 volts is here now. And actually what we've got, let's just draw it in internally. This is what's happening inside the PLC. It's just the contact of a relay and what's known as a volt-free contact. So that means that there's no voltage there. It's just closing a dry contact, and we can put any voltage we like into it, pretty much. You probably wouldn't put like 1,000 volts into it, but sort of 240, that's probably as far as we could go with that. But yeah, certainly 24 volts. Obviously, you'd have to read the manual, check what voltage you can put through it. But so we got our 24 volts here, and now it's just waiting to see, or for that voltage to then go back. It's just down to the programming of the PLC. which is just going to determine whether that's open or closed. So if it's open like it is at the moment, nothing happens. But then it closes, so it closes, that contact closes, so that 24 volts is now able to go through that, and then it goes back. So let's go back. So now it's coming back this way. And it's exactly the same operation, guys. Ultimately, what we're doing is we're bypassing, if you look at it closely, all we're doing is we're just bypassing this bit, the hand bit. We're bypassing that, going through an additional contact, which is controlled by the PLC, and then it's exactly the same operation as what we've just been through. So that's how we can decide with the position switch whether it's running constantly and the user is controlling it, so off, on, user control, or we just switch it into auto, and then it's the PLC that's determining whether that pump is coming on or not.
Thanks. You know what it is? Because for many moons, I was looking at the part where the supply goes to the PLC. Initially, I thought that as soon as the supply goes to the PLC, it switches without the PLC doing anything. But now you're saying that the voltage rests at, say, A1 until the PLC tells it to close.
Yeah, it's just exactly like the relays that we've been looking at on all the other pages, you know?
Yeah. Because in my head, when you get to the A1 of it, you think that it's made straight away. I used to think that it was, as soon as it hits that, it's made, right? But obviously now you're telling us, which is brilliant, that you're waiting for the PLC program to close that. That's brilliant. Thanks a lot. Cheers.
And guys, that's pretty much it for the dumb pumps. So yeah, any questions on what we've just been through, guys? Is that all?
I have some more, if that's all right.
yeah, guys, and don't, like, if there isn't something that, you know, if it's not 100%, don't hesitate. Like, let's go through it. Let's work through it. So you are, you know, you do understand it. Like, don't be shy. Yeah, sorry.
Yeah, so if you could go to page 5 again with the pumps.
Yeah.
So we have a double layered system in here. So essentially, when with the lights, with operating the lights, so we have let's just look at the trip light for an example. So if an overload trips out, the overload switch 1 trips in, the one that's bridging the 97 and 98.
Sorry, mate. My locks on circadian lighting has just dropped the lighting.
Yeah. Should I give you a sec?
I'm just there we go. Apologies, mate. Sorry.
No worries. So why can't we have the overload switch just power the lamp straight away? Why do we need relay 12 in the first place?
Yeah, so why are we basically adding a relay there when
we already have one, essentially?
You're asking, why don't we don't need that there. Why don't we just put this light over here?
Yes.
Yeah. I'll let you answer that. Why do you think?
Well,
with the relays.
Well, the only reason I can think about is that the lamp might draw too much power for the relay inside the overload.
No.
Extra protection, I guess. It's just as with the overload stuff.
It's a good question. It's a really good question. That's not the answer either. Who can help Ivan out? Why?
I'm lost.
Why aren't we just putting the light here and doing away with that?
The answer is to do with a second pole on the relay, I believe, that goes into the PLC. So you've got by the PLC.
Spot on, Paul. That's exactly
because 24 volt.
So let's just look at it. So if I just have that light there and no relay, so that's not there. That's great. I can switch the light on and off, so we can give a visual representation. And this will be more clear when we go through the PLC and the details on the PLC. But Which one is it?
Well, yeah, so on the bottom right there of the ACT5.
So boiler, here we go. Boiler 1. Let's just work with boiler 2 pump trips. I can't find boiler 1. Because look, pole 2, we need pole 2. We need if we're doing things properly, and you know, we're 21st century, we can do this now. We've got PLCs. We need to also tell the PLC that that's tripped out. And this PLC, this is firing out a different voltage to that 24 volt AC. So on one pole, we're using the 24 volt AC to bring on the light. And then this PLC here, this is firing out 3.3 volts. It's like a little closed loop system. So we're firing out of the PLC 3.3 volts and then into pole 2, different voltage. That's what we're using then when that trips out to tell our PLC.
So essentially all the second poles here are just feeding the PLC data at this point.
Pretty much. There's a couple that there's an exception with a couple, like with the switch over relay for the 0 to 10 volts that we looked at yesterday for the boiler control. But pretty much, yeah, every pole 2 of each relay is feeding the PLC.
Understood. Thanks.
Good question though, mate. Really good question. Any other questions, guys? I'm gonna start testing you. Who thinks they're 100% confident in what we just went through? Who can talk me through it and talk everyone else through it?
If you don't mind me, I have a question.
Yeah, go for it.
The first model we have APB, and the second one we have MPCB model. Is that just a different model of relay and contact, or like there is a different mechanism actually going on?
Sorry, is the question what's the difference between the MPCB and what we got over here? Was that the question, Marceline?
In the first motor we have ABP, in the C1, but like in the second one we have MPCB. Yeah. So is it going the same mechanism, or there's some different one here?
Yeah, so I mentioned at the start, basically it's the same kind of operation, but when I was doing the designs, I wanted to have like one motor controlled with a contactor and overload relay, and then one motor being controlled with a MPCB, just to sort of demonstrate the different controls. I won't go into all the details, long story, but I decided to just go with 2 times this style control in the end. So when I actually came to build the panel, I didn't bother with the MPCB for multiple reasons. So if you look at the images within the image folder, you'll see that it's actually two of these contactors. So basically what I'm saying, guys, is ignore this side and just imagine that there's 2 of these, and I've modified the drawing in the drive, or there's a page 5. This page here has been modified so you can see what it looks like now to match the images of the panel. But to answer your question, Marceline, it's the same principles. It's the same type of operation. An MPCB works in the same way, pretty much.
Okay, thanks.
All good, guys? Any questions? What we'll do is we'll Monday I'll do a little recap on that. So I think that'll be helpful. We'll just run through that quickly again. That's pretty much it for today. What I'm going to do, if you guys want to stay for like 10 minutes, I'm just going to go over what Mike was. It was Mike, wasn't it, that asked about the programming and the software?
Oh yeah.
So yeah, I'm just going to quickly show people. I'm not going to go into any detail. I'm just going to show you what it looks like the programming software, what it looks like in Loxon, and what it looks like in KNX, just so you can see. We're not going to go into any detail, but you can just see like visually what it looks like. So anyone that wants to stay and have a look at that, please do. Anyone else or anyone that needs to shoot off, please do. Thanks for joining us. See you next week.
Thanks, Chris. Enjoy your weekend.
And you, mate. Thank you.
Thanks, Chris. Have a good weekend, mate.
Cheers, buddy. Cheers, Danny. Hey guys, me again, and this is just a reminder to actually download those schematics for this project so you're able to learn on a much deeper level. As mentioned at the start of the video, they can be found in the description, so click that link, you'll be taken to our free community where the first thing you'll see will be those schematics. So download them, come back to this video after you've downloaded them so you can actually get to where you want to go, so you can actually understand schematics, so you can become a better engineer, progress your career, progress your business, whatever it might be. Download those schematics. It will seriously help with all of this. So I'll just quickly give a quick overview of the pumps that we're looking at today. So this is the heating schematic, and the pump sets that we're looking at today is this pump set here. You can see there's two pumps on top of each other, so they're going to be working in parallel. Duty standby is most likely, I think, from remembering the spec, I think, yeah, duty standby. One will run for a week and then it will switch over and the other one will run for a week. So sort of evenly wear them. But if one of them does fail and goes into fault, it automatically knows, the pump setup automatically knows that it then needs to switch over to the other pump until we can fix it or clear the fault on that pump that went into fault. So yeah, pump set for the kitchen vent heater circuit up here, and then we've also got another pump set feeding basically all the rooms in the school. So yeah, radiators mostly. We've got a heat coil in the toilets, in the toilets. And we've got some overhead heaters, which are similar, sort of fan coil units in a couple of areas over here as well. So that's what these pumps that we're going to look at are doing within the project. I was just brushing up on, so there's two tech manuals. There's like a condensed, simplified version, which I went through in the tech video. And then there's this sort of larger manual, sort of more like a brochure. So I was just having a look at this earlier today, and yeah, who else has read through this manual? Anyone? So yeah, so when you get like presented with documents and manuals like this, like I never read the whole thing. Like it's just a complete waste of time. What I tend to do is I'll just open up the manual, and then obviously I'm looking at the spec as well. So the spec is telling me things that I need to know and look out for. So for example, like electrical, like there's all sorts of data in these brochures, but electrical is obviously something that I'm interested in as an electrical controls engineer. So what I do is I just do Control F and then just type in, I can spell it, electrical. So I just type in keywords, you know, whether it's electrical, whether it's fault output, run output, etc. And this is kind of how I navigate tech manuals and brochures quickly, and it will just take me straight to, you know, where those keywords are. So that's just a little tip for you if you are ever reading through tech manuals. I noted down page 30 and page 31. Yeah, so it will be more obvious when we get into the schematics, but we've got different inputs. We got digital inputs and we got analog inputs that we can use if we choose to. And we've got relay outputs as well. So can someone tell me, oh, and before we get into that, this is something that I hadn't read, but I probably should have read. And again, it's just shows how important it is to read manuals. So this I thought was quite interesting. So relay recommendations for the start and stop. So to ensure trouble-free operation, Grundfos recommends using a solid-state relay with a minimum load current below 1 milliamp. These relays typically have a MOSFET transistor as output drive. Relays with gold contacts for small signal operation can also be used. No, relays with thyristor output drive cannot be used, which I thought was interesting because, well, firstly, I haven't checked to see if the relays within, or the relays that I'm using, are gold plated. They might be, but if I was doing this belts and braces, as as the tech manual has told me to, really I should be using solid state relays as it's said here. Now, I've been using these pumps for a long time, using just standard relays, and no issues come of it. You know, it's not a problem. But these are just little things that you need to be aware of. And it might be that if there ever is a problem down the line and I need to speak to the manufacturer, or maybe I want to return a pump or whatever, the manufacturer might say, well, what relays are you using to control it? And then if I tell him that, well, we're not using solid state relays and they're not gold plated, etc., then it might void warranty or, you know, stop us being able to return bits of hardware. So basically my message is just what you should really do is just follow things to a T, really. Just do exactly what the manufacturer's recommendations are, but it's not always practical. So, you know, it's getting that balance, really. Cool. Well, let's I'll stop rambling and let's get into the schematics. Can everyone see my schematics? Great stuff. Right then. So what we're going to look at is there's 4 pages with this smart pump that we're going to be looking at today, but it's all pretty much the same. It's the same thing. So we're just really going to be focusing on page 6. Page 6, a little bit of 7, but mostly page 6. So who can tell me, Tom G, I don't think I spoke to you, mate. Tom G, can you tell me what inputs on these pumps we're using and what outputs we're using on these pumps in terms of controls? You look nervous, Tom, and I can't hear you, mate. You're muted. Actually, I'll tell you what, Tom, I'll let you off for the time being. Does anyone have any, before we get into this, does anyone have any questions from the session that we had Friday, or just any questions in general? 5 minutes covering questions, if anyone has them.
I do have some question, if possible.
Yeah.
To go back to previous session, which I had to watch because I wasn't available at 4 p.m. on Friday. Okay. So the first question is just confirmation, really. If we swapped OL1 and C1 coil, this protection circuit it would still work, because even though if we had voltage on the coil C1, we need current to drive the coil. My understanding is, and simple confirmation that my line of thought is correct.
Sorry, mate. Just say that again, slightly differently.
Yeah, if we swapped C1 and L1, would it still be protected from overload?
Sorry, mate. I don't understand the question.
Let's
come back to that at the end, mate. We can go into that at the end. Did you say you got another question on this?
Yes. When we have this contactor, it was said during the recording that we have to loop back from second contact at the bottom back to the beginning.
Yeah.
Otherwise, it wouldn't work. But
no, didn't say that.
Right.
Okay. It will still work.
Yeah.
And you can do it one of 3 different ways.
Okay. So that matches my understanding, because I thought that is not necessary, and this brings me to the question or confirmation: do one-pole contactors exist? Because I've never seen one. I always saw three-pole contactors, but just to be sure,
They do, but you never see them. They do exist, but you never see them, because most stuff, if you're doing single pole switching control, it's done with a relay mostly. But there are such things as single pole contactors. You just never see them used. Does anyone else here use single pole contactors for anything?
So that wraps up things. Just tiny thing on this contactor. On the contactor right hand side, there is normally open and normally closed. And are these additional contacts? Because I believe we're using normally open 13 and 14, but there's also normally closed. And if we don't have any numbers next to it, I assume we just don't use it, even though it does exist.
This contact here, if you look at the images, this is why it's important, guys, to actually look at the images, because it will tell you and it will answer a lot of your questions. This contact only has 13 and 14 normally open contacts. So it doesn't have normally closed. You can get them, like if you need a normally closed contact with this contactor, then you can get them, but a normally open is fine for me for what I'm doing.
So my confusion was that I thought if there are no numbers, we're just not using the existing contacts. But I'm glad you clarified that these contacts, normally closed contact, doesn't exist as an additional one.
Yeah, it doesn't exist, mate. Doesn't exist.
Right. So that's pretty much wrap up recorded sessions. So yeah, thank you. I'm I'm following now, and if we could come back to that final question.
Stay at the end, mate. We'll come back to that.
No problem.
Any other questions, guys, before we move on? Cool. All right then. Right, so let's get into these. Yeah, let's get into these smart pumps. So these are what's known as smart pumps. So straight away, we just got our feeds. So our 230 volt feeds, L1 and neutral, just standard. When the panel is on and providing our local isolator is in the right position, then power is going to these pumps. And obviously we've got so there's actually, even though it's a twin pump set, we're still powering both. They're kind of individual pumps, but they're sort of plumbed in the same, and they are able to communicate to each other. But ultimately, like, the controls and power is separate for each pump, even though they're set. So yeah, standard 230 volt supply via an MCB. And then let's just jump straight into the controls. So we've got our 24 volt AC supply, and this is feeding into our common of the, and we've configured these relays because we can choose how we have these configured. There's, I think, 3 different ways we can have them set up. And again, the spec has told me what it wants, or what the M&E designer wants. So I'm using it for a running signal and a fault signal. So we've got 24 volts AC going to the common of relay 1. We've got set up for the running signal, and then in the panel I've chosen to just bus this, send this same voltage over to the fault common in the panel. Thinking about this now, doesn't really matter, guys, but I could have just not done that, and the person in the field, the commissioning engineer, could have just passed over that 24 volts at the pump side, but doesn't really matter. So anyway, yeah, I'm tapping off that supply and doing the same thing, feeding the common on the fault side as well. So healthy condition, and we get to the power and the switching on and off in a second. So let's just say that it is powered on and it's running. So let's draw those contacts as well. So this is an internal relay within the pump. So we got normally open on the running side, and we got normally closed on the fault side. If you look at the manual, it really doesn't matter whether we have these wired normally open or normally closed. It really doesn't matter. I've just done this because out of habit, this is how I kind of do things. But the operation is the same either way. We just need to be aware of how we're using the normally open and normally closed on the contact side of the relays that are getting energized from those signals. So again, let's not get caught up in whether it's normally open or normally closed. It really doesn't matter. So running, that contact then closes when it's running, which then sends the 24 volts to relay 16. And Tom, I'll come back to you. Where have you gone, mate? Are you still there, or have you run away? I can't see you. Ivan, can you tell me what that /2 stands for, mate? Just as a reminder to everyone.
The number of poles on the relay.
Yeah, great stuff. So yeah, 2 poles on that relay. So the first pole is over here, and this should be pretty Yeah, we've been through this a few times now, so hopefully you guys are sort of starting to understand the concepts here. So that's been energized. Relay 16 has been energized. Which closes that contact there. So that means that we've got that 24 volts that's up here, going down here, and bringing on that run light. And in its normal state of running, this is normally closed. So we've got exactly the same thing happening on the fault output. So going to relay 17, so it energizes relay 17, which now, because this is normally closed, this actually now goes open circuit, which, if we follow this down here, that actually switches off that fault light. So, and let's just go back. If it is in fault, then this contact opens. Which means that isn't energized, which means that this stays in its normally closed state and allows power to flow down, and it does light up that fault light. So what we're doing is we're just using relays in the same way, but they're just inverted. So with the running signal, we're doing it all normally open, and with the fault signal, we're doing them all normally closed. And we've got the same operation, it's just sort of switched around the other way.
That is for safety, I guess.
We do questions in a bit, mate. I'll just carry on explaining this, and then we'll come back to questions. And yes, it's safety. Like normally closed is like a fail-safe condition. That's typically how most things sort of with certainly failed lights and failed statuses, or fault statuses. Yeah, they're normally closed. But like I said, checking the manual, if you actually check the manual, it doesn't matter. It really doesn't matter. Some things it does though. So yeah, so we've either got run light on or fault light off, or they're switched around the other way. We're not gonna have, I don't think we'd ever have both of those lights on at the same time. I think it will be either or. So let's have a look at like the controls and the operation now. So we've got our 3-position cam switch here, and we've also got another cam switch over here. So we got our 3-position cam switch here, and we got a 2-position cam switch here. And we'll come back to that 2-position cam switch in a minute. So again, we're tapping off the safety circuit supply. I was thinking about this the other day. Like the best way to think about these circuits, like if you're an electrician and you're used to sort of power, just think of it as like supplies. You know, they're just different supplies based on conditions. So like the safety supply, which is a 400 circuit, I think, or 200 circuit. Doesn't matter, but the safety supply, that's supplied constantly, providing what we talked about earlier on, you know, all that safety stuff is okay and it's in a healthy condition. So if all that safety stuff is okay and it's in a healthy condition, then we're also able to use that supply, and then we can actually control things using this 3-position switch. So let's start off in hand because it's the easiest one to understand. So safety is going through the hand switch, and then it's going down to relay 18. So that's now energized. Now, what's happening here? Jonathan Harvey, now that R18 is energized, what is that now enabling us to do? Jonathan Harvey, mate, you're muted, buddy.
That's allowing us to run it.
Have a look at where the contacts of R18 are.
Yeah, so that's up at the top with between pump 1 and pump 2.
This here.
Yeah, that bit there. Yeah.
Yeah.
So that's closing that, allowing the safety circuit to go down either or.
Yeah.
Or pump 1 rather.
Yeah, so exactly right. So that's energized R18. Let's close that contact. And now what can we do? I mean, Do you know what this is here?
I think, is it one of those pump changeover switches?
It's a switch, yeah. It's a two-position switch.
Yeah. So that allows you to go between each pump.
Yeah, exactly. So now that's closed, we can now decide which pump we want running. We're in manual mode here, hand mode, same thing. Hand manual mode, same thing. And it's a two-position switch, so it can only ever be in this position or this position. There's no middle off position.
Yeah.
So as it is at the moment, and it's doesn't matter how you draw it, whether it's to pump 1 or pump 2, doesn't matter. But now that's continuing the circuit down to R19. So
yeah,
John, again, mate, what does that now do now that R19 is energized?
Well, then that allows R19 is the enable to the bottom right hand side. So that then pulls in that contact that allows the pump to run, I think. The 24 volt thing, isn't it?
Yeah, it allows the pump to run. So, yeah, spot on, John. So someone else now, Max Robbins, what is happening on the pump side? So now this is closed. This is a closed circuit now. That's quite a shit question, actually. Don't worry, mate. I'll come back to you in a sec. What we've got, so now that's closed, we've now got a complete circuit over here. And so what this is how this is working. This is most likely, or it is, I don't know the exact way that it's working, but I imagine you got a positive there. Again, it's like a relay. It's sending it out there. So it's always at this point, you know, whatever that is, that might be 12 volts, 10 volts, 5 volts, doesn't matter. And it's just looking for that contact to close. So volt-free contact. And then once that closes, it can send that positive back to the probably now to a relay. Again, this is all internal PCB. Like, don't overthink this too much, but I'm just trying to visualize what's actually happening on the pump side. So that energizes a little relay on the PCB there, which then basically sends a signal to switch on that pump and it starts running. That's what's happening on the pump side. So yeah, we're basically, what we're doing here is we're just with that now, so R18 is closed, and then we're just going from, and if we're on pump 1, we're just closing this contact here, and that's just completing this circuit, which is the signal, it's the enable signal to bring on that pump. And it's as simple as that. And it's just exactly the same thing for running the second pump, the second pump in that set. So let's do the same thing, but for pump 2. Let's just go through it again because. So yeah, we're tapping off that safety circuit. We've switched it to hand. So it's in hand. We're powering up R18, which closes this contact over here. But now this time we're just switching to pump. We're switching from pump 1 to pump 2. We're going to let pump 2 run for a bit now. So that just switches the power or supply down this route. And then it gets to R20, closes that, which, as you can see here, it closes that contact, and it's exactly the same thing on pump 2 of that set. And if you remember what we were saying earlier on, that if you see a tear like that, you don't see this on every schematic, but how I've designed it, and I've seen this on a few other ones, like this tear is sort of pointing to another page. So if we just scroll to the next page, you can see the tear sort of completes over here. And yeah, ultimately that just brings on the second pump. So exactly the same principles. You'll notice though, like you're only having this control between like pump 1 and pump 2 if it's in hand. if it's set to hand, sorry, if it's not set to hand, then if it's in the off position, obviously, or auto position, this contact here doesn't close. So it might be a little bit confusing, like if you're looking at the front of the panel and you're seeing that the second switch, the 2-position switch, is set to pump 1, but you might see pump 2 running. But that's because it's probably being controlled in auto, if that's the case. So this 2-position switch, it only works, it's only operational when it's in hand. When it's in hand over here, which energizes R18, which closes that. So if it's not in hand, then all of this, or sorry, that 2-position switch is not doing anything. Even though it may look like it's doing something, it's not. I've actually written a little note in brackets on the front of the panel. Again, you can see this in the images, that says something along the lines of only operational in hand, above like pump 1 and pump 2. So yeah, again, if you're doing the design, it's worth doing something like that, just to just trying to avoid confusion, doing your best to try and avoid people's confusion. Right, so now let's go and switch it to auto. So it was in hand, and now we're switching it. To get to auto, we need to switch it through the off position. So it goes off, and then we go to auto. So we're going to auto, that supply is going off, and then we're going off to page 10, B104. So let's find that on our schematics. Page 10, B104. So page 10, which we're on, B over here, and 104 over here. So there we go. So that's now where that supply is going to. So someone that was here Friday, someone that was here Friday, who can tell me what we're now doing here at this all-in box, this Zenio PLC?
Well, you're controlling the pump, aren't you?
Yeah. So we're controlling the pump, and what are we using on this PLC? What output, input, what are we using now to control that pump?
A voltage, I presume?
Yeah. Output. What specific type of output are we using?
A volt-free output.
Yeah, volt-free output. So explain that in a bit more detail, Powell. What do you mean by a volt-free contact?
It means that that unit itself doesn't supply power. It only closes and allows the voltage to flow through.
Yeah.
So it just closes internally and allows control to happen.
And what is a volt-free contact? Like, what is it on a bigger scale? Let's say.
Volt-free means we don't
what
provide
is it? What
power.
sort of component is it? Is probably a better question.
It's a relay.
Yeah, it's a relay. It's a relay, guys. So let's go a bit deeper here. Yeah, nice one. Cheers, pal. So yeah, we're coming in now. We're coming in on this one from that page, and we're feeding this input here on B1. And what I've done wiring wise, I've just done a little link over to this other bit on the PLC, and this bit is a volt-free relay. So like Powell said, so what we've got here, we should all be familiar with what a relay and the contact looks like now, but this is what's happening internally. Again, internally on the PCB, the electronics of the PLC, we've got two contacts which are volt-free. So it doesn't matter. It's also known as a dry contact. So whatever we put in, we're getting out. We're supplying that voltage. It's not providing its own voltage. So we'd have to look at the tech manual, but it doesn't matter if we put in 12 volts, 10 volts, 24 volts, 230 volts AC. It shouldn't matter. So we're feeding it with 24 volts AC from that page. It's going in, and now we're using the PLC now and the programming to then determine, firstly, which pump is being switched on, but also when. So we might, if we're doing all the PLC, if we're doing all the controls and logic and programming using the PLC, let's just say we are for now, because there's a couple of other ways we could do it. But the PLC and the programming is now deciding when to switch those pumps on. So we might have pump 1 running for a week, and then after a week, and this is where the duty standby, this is a duty standby configuration. So this one's in duty, that's running for a week. And then after a week, the timer is up and it switches over. So this one then stops and this one then runs. And then it's the same thing. After a week, it will switch over. But also we'll program the PLC. If one of them goes into fault, then, before that week is up, like pump 1 goes into fault when it's in its week of running, we can detect that and then straight away just switch over to this other pump. And obviously we can be notified as tech support or facilities managers or whoever. So yeah, that's what's happening there. So either we're running pump 1 and that's completing that circuit through the volt-free contact of the PLC, or we're doing it or doing the same thing on the second volt-free relay or contact, and then that's sending the signal, the power, the 24 volts, whatever you want to call it, back to that page. So let's go back to that page, and now this should look familiar, guys. We're going back. So this is the signal coming for pump 1, and then this is the signal coming back for pump 2. So what's happening now in terms of operation of pumps and contacts closing? Joseph Dalton, can you tell me, mate?
Yeah, the pumps should be running.
Yeah, and what's happening in terms of the contacts? What's just one step before that?
The same earlier, they're switching over.
Yeah, it's exactly the same as earlier. So 19, as we got over here, that closes, enables pump 1, and 20 over here, that's pump 2. So again, like we talked about Friday, we're just bypassing. That's kind of all we're doing, is we're just bypassing. It's not quite as obvious as what we covered on Friday, but yeah, well, I suppose, yeah, we're just bypassing. We're bypassing a little bit more than what we were bypassing on Friday, but we're bypassing R18 and yeah, this 2-position switch. That's really what we're doing. But ultimately, it just both manual and auto, or hand and auto, they both come back to these relays, and then it's exactly the same operation over here and over here. Let's go over any questions, guys. Does that make, let me know your thoughts on that. Like, how does that sound? Does that make sense?
Chris?
Yes, mate.
Just a question, just the arrows, you know where it says page 10B 104?
Yeah.
Yeah, I understand why the arrows at the top's going that way, because that to me is going to PLC. The other arrows for me should be the other way around, i.e. they're coming from the PLC. Does that make sense?
Yeah. So this is something that I know what you're saying, mate, and this is something that I thought about. Like, are you going in the direction of like where the page is and where the cables are going, or are you going by the flow of power electrons?
Yeah.
So again, this is this personal preference on the designer, really. My thinking was, well, these are the cables.
Yeah.
These are the cables. So I'm telling people where the cables are going.
Yeah, that's fair enough. It's just in my mind, because they're coming back, it's quite hard to visualize that for me. I get why it's done.
Yeah, and I get what you're saying as well.
Yeah.
So yeah, the cables in my mind, I'm just drawing the cables. So the cables are going off to page 10. And then when we get to page 10, so we're going, the cable's going off to page 10. So we get to page 10. And then in my mind, what's logical for me isn't necessarily logical for everyone else. People's logics are different, but here, I'm saying now that the cables are going off that way on page 10. So doesn't really matter.
We provide only control signal. We don't need to provide common reference like we did in previous session, I believe.
Say that again, mate. Sorry.
We do not need to provide common ground we only provide control from that control unit.
Yeah. So again, we're only, it's the switched, let's say the switch live, the switched control signal. That's all we're using. Yeah. We don't have any 0 volts or grounds. We go back. The 0 volts is over here, at the end of the relay.
I was trying to compare it and with previous scenario where we had to provide common ground to prevent ground loops. Is it something worth mentioning briefly, or that would be too much for the diversion for the subject?
Yeah, we that's something we can look at on Friday, because Friday is going to be like more general Q&A and things like that. So yeah, I'll cover that and I'll talk about that on Friday. Any other questions, guys? Like
Chris?
Yes, mate. Yeah.
Yeah. Just a couple quick ones. So the main use of the hand sort of off auto selector switch, is the hand function generally for a manual override / sort of maintenance reasons?
Yeah,
purely.
Pretty much.
Yeah. And then obviously the PLC, does it itself recognize a fault on the pumps?
Yes, yeah. So if you remember, we got 2 poles on each relay.
Yeah.
Pole 1 we're always using as the mechanical electrical stuff, but can you remember what we're doing with pole 2?
Okay, yeah. So that's gonna tell it.
Yeah. What? Remind me. What's it doing?
So pole 2 is being used to run via the PLC to allow it to know what state that it's in.
Yeah, exactly. Yeah. So let's have a look at R16, R17. Let's go to let's look at, so not R16, R17, because I'm actually missing R17, which is a mistake on my part. But what we've got here, let's look at the other pumps. We have.
Yeah.
Yeah, so we've got, basically we've got our run signal and we've got our fault signals over here. So yeah. So then, again, going back to if we're using the PLC for all of this intelligent duty standby and rotation and all of that, then we now know, say pump 1's in fault, and we've written something in our program that says if we see pump 1 in fault, then switch over to pump 2.
Yeah. And obviously, if it was a big issue being absent from site, then the option is to turn it to hand.
Yeah.
Potentially.
Yeah. But then that requires obviously human interaction.
Yeah. Worst case.
Yeah. But yeah, typically you won't see many systems if they're running correctly. You won't see any systems in hand. Everything will be in auto. Any other questions, guys? Because there's not really too much more to it than that. Obviously, there's a couple of pages with these smart pumps, but they're all doing the same thing. The controls is the same thing. One additional thing I can just mention, it's not important, but if we go on to page 7, you'll see that each pump set has a DPS. So who can tell me what DPS stands for?
Differential pressure switch, isn't it?
Yes, mate. Yeah, differential pressure switch. And what do you think that's doing in terms of the system, Max?
Now you got me.
So what this is, we come back to it in a sec. Actually, I'll show you on the big hydraulic schematic, and it will make more sense. But each pump set. So if you look on page 7 and page 9, we've got a DPS on page 9 for the kitchen vent pump set. And on 7, it's for the heat emitter pump set. And this is, a differential pressure switch. So this is basically set if the flow and the pressure, actually, I think I've renamed it to flow established light or flow okay, doesn't matter. But yeah, basically, what that is there for is just not only a visual representation, but to tell the PLC that we've got the right amount of flow, pressure going through those pump circuits. So it's just sort of
does it increase the pump rotation, the speed of the rotation, so you increase the flow?
No, it's just literally feedback. It's just feedback. So obviously, if that isn't on, let's just go through the operation quickly, and then I'll go through it. So very simple, guys. We've got 24 volts. Hang on. Yeah. So page 7. We got 24 volts going out on terminal 49, and then it's going to this differential pressure switch, and this is normally open. So what you'll see is when the pressure is established and the flow is established, and in terms of physically what we would do in the field, we've installed this differential pressure switch, and now we've set it to the optimum setting, like the optimum pressure. So when those pumps are running, or when one of those pumps is running, then it meets that right pressure setting, that will then close, and it sends power back into our panel. It energizes R23, which is up here, and yeah, just standard stuff what we've been over. Just sends that 24 volts to the flow OK light. So it brings on that light on the front of the panel. Also, we've got it doubled up, so it will send a signal to the PLC. And what we could, so actually, Ahmed, thinking about it, we would also use this similar to what we're doing with the fault. So if there is a pressure drop, with running pump 1, then we might switch over to pump 2, because it might be an issue with the pump. So we might still be able to get the right pressure in the flow using pump 2. But if that pressure or flow doesn't recover, we might program it to do a couple of cycles back and forth. But if it's still there, then we know there's a bigger problem. So really, it's kind of for monitoring more than anything.
Chris, sorry, can I?
Yes,
is there any way that it can monitor for overpressure, or would you have to have a second one in line with that?
Yeah, to be honest, I'm trying to think. I think like differential pressure switch. I might be wrong. You'll have to Google it, or someone else here might know. It might be that it's just in this range. So you set this differential pressure switch to sort of be okay, in this range here. Like if it's lower, then it doesn't trigger, and if it's higher, it doesn't trigger. So does that answer your question?
Yeah, I think so. But so if it goes over pressure, it will turn off the run emitter light, but
Yes.
it won't be able to bring on a fault light if it goes over pressure. But you could possibly put another one in line that was set to a different.
Well, you could do that. If again, I'm just going by what the spec's telling me. I could go a bit further, and I could just do, like, if you wanted a flow not okay, like a flow fail, then it's just the opposite of what we're doing here. If that's what you're asking.
My understanding of those DP switches is it's like a diaphragm.
Yeah.
And it's like you set either side to the level you want, and then once one side's too much, it pushes it down on the other side, and that's what alerts you. Or, that shows you that there's too much pressure over on one side compared to the other.
Okay. Because I've worked with them for ventilation. I've never had hands-on with the.
I think for sprinkler pump you will see this. To start the sprinkler pump, I think you'll find.
I've seen them on risers and things, and at the top of risers where they have to monitor to see what sort of pressure they're having at the top of, and and then coming into the overpressurization thing. If there's an overpressurizing the system, wouldn't that just shut off the pressurization system right at the start, and then the safety circuit will kill it? And then that's your main thing for that.
Yeah.
Yeah. Sorry, I forgot. That's right at the beginning.
Sorry.
No, you're good. Yeah, I mean, look, we've got a pressurization unit that's looking at the system as a whole. This like that differential pressure switch is probably more like let's go out of here and I'll share my other screen because it'll make more sense then. Probably more for like wear and tear more than anything, is the pump in a good condition?
Assuming that DPS is more of just a physical on-off switch rather than giving a reading.
Yes, it's not an analog signal where there's a range. Yeah, I probably didn't explain that very well. It's an on-off. It's either good or it's bad or it's yes or it's no. But I was thinking there's probably a range in which it works within, or it's like a threshold where, for argument's sake, if it's above 1 bar, then it's okay. If it's below that, then it's not. I'm not talking from experience here, so I can't tell you exactly.
I'm pretty sure it's just the same thing as a flow switch. If the pump runs, there's a differential on the suction and then on the discharge of the pump. And you can read that from the suction side of the pump. You can tell if there's a differential pressure. It just lets you know if the pump is physically running.
Yeah,
same thing as like a flow switch.
Yeah, but if, like, say you set it to 1 bar and it goes up to, I don't know, 3 bar, it won't necessarily switch off. Like, say it, I'm not explaining it very well. I'm trying to
It will, like Jonathan was saying, with the diaphragm inside, if you don't have the pressure that it's set to, it just won't close the circuit.
Yeah, so on the lower end, if it's set to 1 bar and it's half a bar, then it won't switch on.
Correct, because there will be a spring that works in conjunction with the diaphragm. So the water hits the bottom of the diaphragm, and then the spring pressure on top is how you would adjust how many bar you want it to open or close at, essentially.
But let's say then the pressure goes up to 2 bar. Is that still, yes, okay, the flow's good, but actually it's overpressure, like Max was saying?
I think it would just switch it off.
So it would switch off so there is kind of a range then. So between, say, 1 bar and 1.5 bar, we've got a bit of play where, if it's between that, it's good. But if it's over that 1.5 bar, then it switches off again. So flow isn't okay.
Yeah, and I think oftentimes that's used like for if you have like a process chiller or boiler that you're running and you're running out of water, your pressure will change. So It's a good way to notify people.
Cool. All right. Cheers for that, Tom. That's good to know, mate. Yeah, let's just go back to the hydraulic heating layout. Can you guys see my screen? Just double check. Yeah, cool. That's the wrong one. Hydraulic schematic. So what we've got here is the DP. It's looking at the differential in pressure across those pumps. So again, guys, correct me if I'm wrong. I'm not an expert when it comes to sort of hydraulic stuff. I'm more controls based, but to me, that's just monitoring pressure going in and pressure coming out.
This will indicate, I believe this is configuration mechanically will indicate that the strainer, if it is clogged or something clogged in the circuit, you are setting this on the pressure drop according to the pressure loss in the closed circuit. And after this, if you exceed the value, this means that this strainer before the pump must be cleaned.
Yeah. So you're ultimately monitoring the pumps. The set of pumps, the condition of them, if they need servicing. Yeah, that's kind of how I think of this. We've also got these P
manometers. Yeah,
they're pressure sensors. So we're also
it's sensors or mechanical manometers.
Pressure sensors.
Pressure sensors. Okay.
So not only have we got so this is interesting, guys, and this is obviously from the M&E designer. This has been sent to me by the M&E designer. They want a differential pressure switch, and this is like a mechanical electrical signal, like a relay. But we've also got pressure sensors, analog signals, like a range either side as well. So we're basically, again, it's like a redundancy thing. We've got our analog signals, so we can actually monitor these analog signals over time, and we can see what's happening with the flow and the pressure. If things are dropping over time and they get to a threshold, then we can be like, oh, well, we probably have to do some preventative maintenance and then, get it back up to where they should be. So we can monitor things that way. But then I don't know, let's say there's an issue with the electronics or an issue with these sensors, like analog signals are obviously more sensitive, but so that's why I think the M&E designers spec differential pressure switches as well, because we've got that mechanical electrical signal as redundancy, as a backup. So if we are having issues with the pressure sensors, then we've always got that fallback to the digital yes or no signal, whether it's good or bad, from the differential pressure switch as well. Would anyone disagree with me on that? What do you reckon, Ahmed? Does that make sense?
Yeah, it's okay, but I just don't understand how you control the pump, because maybe in this schematic you have to find another pressure sensor between the supply and return. So I will figure out what is the pressure loss in the system, so I will know if I want to increase the flow rate. This is a variable speed pump, yeah?
These are smart pumps, so depending on what setting you've got them set to, they do all of that. They monitor themselves and they adjust themselves. Okay. So these pressure sensors and differential pressure switches, they're not really necessary, I suppose, in terms of controlling the pumps, because the pumps are smart pumps and they've got this kind of, like we were talking about the other day, like variable speed built into them. There's no, I don't think, no, I think there is, we can control the speed. So I think there's 2 additional inputs that we're not using actually in this design, but we can use as like running in low and running in high. So what I'm saying is we could actually use this data from the pressure sensors coming back to the PLC, and then based on that data, then send digital signals back to these pumps, either to run at its fastest speed or its lowest speed. But I don't think we need to do that, because these are these smart pumps that do it already. They monitor their own pressure and flow. And you'd set that within the pumps, and they're kind of separate from the BMS.
Okay.
On a less intelligent pump, then you might do it that way. Again, does anyone, I'm just interested, like Daniel Mason, does that make sense to you? Would you agree that that's how these are sort of meant to be working?
Yeah, I was just more saying that, like the differential, it's not giving us a reading, because obviously we haven't given it a 0 volt. So surely, that's just going to be an on and off, and probably just to give a signal on the front of the panel to say, yeah, flow's okay.
Yeah.
I'm actually having to go into the PLC to read it.
Yeah. Yeah. Again, we'd also double up on that signal in the PLC as well. Like, yes, the differential pressure's okay, because, we might as well. Tom G, what do you think? Is that, would you agree that that's kind of how the operation is? Would you say? Yeah. Okay.
Yeah, it is. And also those pumps. So I think you have like a different setup essentially with the smart pumps. If one of these zone radiator valves closes, then the speed of the pump can slow down a little bit. And also, if you're using an air handler, those pumps, you can plug in another 0 to 10 volts and use like a 10 kilo ohm resistor, and then control the pump speed based on the supply air temperature. And another thing that the DP switch and the gauges across the pump definitely can tell you whether or not, one of your filters or whatever is blocked, but I believe they can also calculate and tell you your GPM as well.
What's that stand for?
Gallons per minute.
Okay, right, gallons per minute.
So, but
yeah, that makes sense. Yeah, I mean, that's a great point. This is kind of, I can't remember who it was, but someone was asking me like the control of these radiators and like thermostats in these rooms. I can't remember the spec, I'll have to double check, but I'm pretty sure it's like teachers just will open the valve on their radiator manually, or they're already open, and that just, everything's running on a timer mostly. If the outside air temperature, for example, like in the summer, is over a certain threshold, then we won't have the heating running. But if it's below that, all of this will be running. And then, like Tom just said, like if through sensing the pressure, these pumps will vary, like the speed based on basically the demand of all of these rooms. So that's kind of how the operation is working.
The control for the radiators is pretty simple. It's just a 24-volt thermostat that connects to an open and close zone valve that closes the supply or the return to the
yeah, but I don't want to confuse things, because I don't think that is actually how these aren't controlled like that. There's nothing in the spec that says that. There's nothing that says anything about room control in the spec, which leads me to believe they're just standard valves on a radiator. There's no smart control of these radiators.
I think they're just standard spring type valves, aren't they? You just wind them open or close.
Yeah, exactly. Yeah, so it's pretty basic stuff over on that side of the system. Guys, that's pretty much it. How does that all make sense? Do we want to go back into the schematic and ask any more questions? How do you feel?
Sorry, can I just ask, going back to my question a while ago about that DPS?
Yeah.
The pressure. So, just to make sure I got it right in my mind, when the pump switch is on, the sensor will detect the flow. If it's in a good state, the light turns on. And if it's in overpressure, like someone else said, the safety circuit dies anyway, and then you get a fault light come on and your pumps turn off, just in general.
Yeah.
And that's kind of what puts it into fault, is more the safety circuit going off because it's overpressurized.
Yeah, so you've got this here is your pressurization unit, which we looked at on the first day, which is monitoring the pressure everywhere, basically. So if there is like this again, it's got a bit of a tolerance, and you can so that tolerance will be looking like, if it's above this threshold, then I will go into overpressure, and then I will cut whatever it is that we've got coming off it. This is actually cutting the boiler interlock controls. So that's actually controlling the boilers, and probably should be controlling the boiler pumps over here. So that's all that's cutting out, actually. It's cutting the primary side of the system. It's not cutting out these pumps. These pumps will only cut out if, like you said, it's a safety issue. So if we go back to the first page, there's an issue with the safety. That's when these pumps will cut out. So what we could do, if there's overpressure here, then we would just program the PLC to cut out, to just stop the operation of that pump. So this is actually separated, like these pumps, their operation is actually separated from the boiler interlock circuit coming off or being controlled by the pressure unit, if I remember correctly. And also, just to add to that, let's go back to the tech manual of that pressurization unit. Because actually, sorry, Max, we've got because we've got two outputs from that boiler. We've got the boiler interlock output, and we've got the general fault as well. So, sorry, mate, what I just said, ignore that. We would see a general fault output from the pressurization unit anyway, which would then stop those pumps, which would be feeding into the PLC, which would then program off the back of that to stop those pumps. Yeah. Sorry to confuse things.
No, got you.
So exactly what you said. You were right. I'm just trying to look for. Yeah. So here we go. Just going back to that tech manual of the pressurization unit. So the interlock circuit, like that safety critical one, high pressure, it switches out, low pressure, it switches out, sensor fault, internal sensor fault, it switches, mains power failure. And also, and then that's the interlock output. And then the general fault output, we've also got, system one, low pressure, high pressure. So it includes those faults as well on this output. So it would be however we program it, and most likely need to remember what I've done with the spec, but yeah, most likely we're telling those pumps to switch off as well. Other than that question from Powell, guys, that's it. That's it for today.
Any chance to go quickly to that my question at the beginning?
Yes, mate. Let's do that now. So yeah, if anyone wants to stick around for that question, I'll go through that quickly, and then we call it a day. You've got to shoot off now, obviously. Feel free to shoot off. Hey guys, me again, and this is just a reminder to actually download those schematics for this project so you're able to learn on a much deeper level. As mentioned at the start of the video, they can be found in the description, so click that link, you'll be taken to our free community where the first thing you'll see will be those schematics. So download them, come back to this video after you've downloaded them so you can actually get to where you want to go, so you can actually understand schematics, so you can become a better engineer, progress your career, progress your business, whatever it might be. Download those schematics. It will seriously, seriously help with all of this.
If we please change to the page number 5.
Yep. You see that, pal?
Yeah.
Yeah, cool. So page 5, mate. Yeah.
Yeah, page 5. So when we are in hand and we have overload tripped.
So let me draw it. So hand. Yeah, and then we got overload that trips out. Yeah.
Yeah, that trips out. Okay, here comes essence of my question. When we trip, obviously coil C1 will be de-energized, which makes contactor
stay in this position. Open.
Open position. Yeah, that's fine. But what would happen if we swapped C1 and OL1 in position? So, for example, we had C1 at the top, still getting voltage. I believe it still would work. Is the same because voltage is not enough. Obviously, we need current flowing.
Let's draw it. It's the same, but I just want to be 100%. So let's draw it. So we're coming down here. We got our coil, and then we've got our normally closed. So powering up that and providing this is in a good condition, yeah, that can power up. But then if this senses over a thermal overload, then that will trip. Yeah, that trips out here, which obviously then trips out there. Yeah, so it's the same thing.
So thank you for confirming that. That's how I thought, but I thought it's worth double checking because I'd rather be sure about that. And this looping back still bugs me a little bit because obviously you did in a way that is like a standard pretty much, but I'm trying to push it to what is possible, still possible. And the simplest version of that, if we kept neutral completely separate outside.
Yeah, you can do that. Yeah.
Yeah. Okay. And let's say we just we don't do that looping round. We just go off one pole of this contactor. Would it still be okay?
No, you got to put the whole load through the contactor / overload.
But what does it? Why does it make a difference if you loop it back? We can put. We've got one phase only, so why do we need to loop back? The load goes.
I don't know the physics behind it, mate. I've never looked into it, but I just know
the overloads part because obviously they're sort of like thermal coils, aren't they? So if you only went through one, you would still have two of the thermal coils connected together, keeping the contactor together.
Oh, okay, makes sense. Okay. If
well, hang on a sec.
Okay, makes sense.
Hang on a sec. So say that again, Daniel, just so I'm 100% sure I understand what you're saying.
So I'm assuming it's because obviously in the overload, they're like thermal coils, like in a thermostat. So if you only went through one pole of the thermal overload,
yeah,
it would only trip that one, like it is there. It only trip that one coil.
Well,
so the other two coils.
So let me just cut in there, mate, just because it's important. I think what you're saying is you're on the right lines there, but I just your terminology, just to be specific for everyone else, like these don't actually trip. Like they don't go open circuit, these here. They are just there to sense. This, let me go back. It's these that actually change and open or close. That's why we've got this. See, 95 and 96, 95, 96 normally closed in series with the contactor C1 here. That's whether you meant that or not, mate. Just to reiterate, like these here. And it might have been how I've explained it previously, which have confused things. Yeah, made things harder to understand. But yeah, these things here don't ever go open circuit.
Can I make a comment?
Hang on a sec. So Daniel, were you?
Yeah, kind of. I understand that they're not the contacts, but from the way I understand that a thermal overload works is that they do physically part, which then would stop the. Obviously, they're there to pull the contactor in and out. So if all of those three thermal coils were parted, then obviously it's not allowing the contact side of that overload to open or close, or it's pulling it in its non-energized state.
So what you're saying is, just to confirm, what you're saying is you think when there's an overload that these that these go like open circuit. Is that what you're saying?
I believe once they get to a certain temperature, they part.
Please, can I make a clarification on what Daniel?
Hang on, mate. Is it to do with what we're talking about right now? Because I just want to get to the bottom of this first.
Yes, it's what Daniel is talking about.
Okay. Crack on, mate.
So the overload is actually just a bimetallic strip.
Yeah.
So it's when as soon as the current that is drawn, as the current increases.
Sorry, James, to interrupt. What you're about to say, are you 100% sure with what you're saying?
Yes, I'm very sure.
Because I'm starting to doubt myself because I've tested this, with like continuity, and it hasn't gone open circuit here.
So I'm very sure. We only just call it a relay, but it's a bimetallic strip.
So what you're saying is, James, sorry to cut you off, mate. I just want to be very clear here. What you're saying is what's happening here is that's going open circuit, similar to what Daniel's saying.
Yeah, so it's the bimetallic strip.
Right.
But as soon as it increases, when there's an increase in current,
you're making me doubt myself now.
It curves the strip because of differential metal. It curves and then separates. Are
you sure? Because I've tested this and it hasn't done that. So
the basic concept of overload is just a heating sensing metal, and their elongation differs. So once it senses the increase,
but hang on. But that doesn't necessarily. I know what you're saying, but that doesn't mean. That doesn't mean that it trips here. It doesn't mean that these contacts, like it stops those if it's three phase.
Why I'm explaining it is that if you take a normal breaker has an overload and a short circuit mechanism, the thermal side and the electromagnetic side. The thermal side is the bimetallic was making contact, but if the current increases, it would elongate. Once it elongates, it shifts and loses contact.
But I don't think
the normally open and normally closed contact are also tied to that bimetallic.
Yeah, exactly. The normally open, the normally closed is tied to that
movement of the bimetallic. So whichever one is going to do the opposite direction. So the normally closed contact side is tied to the part where the circuit was in good condition, so there was no increase. But as soon as the bimetallic elongates, it opens the normally open. So the normally open only happens when there's an overload situation. So the first explanation you gave on the first day was correct. And then the wiring of the contactor, it is correct that the entire 3 poles must be, I think technically they should be engaged. I don't think it's safe for anyone to be open. So, and the explanation in the first day, I think is consistent with how I've seen it worked. because we've wired, we call this soft starter in my office. And when
we're going off on James, let me stop you, mate. Sorry. We're going off on one. I just want to stick to what we were talking about. What you're saying is when there's a thermal overload, and when there's a thermal overload, you're saying that these here, they go open circuit exactly on these points here. Is that what you're saying?
Yes, they kind of shift. What they really do is to shift your normally open and normally closed contact.
Yeah, but they don't go open circuit here. This is what I'm saying. They don't like that. That still continues to happen, even if it's sensed an overload.
Yes,
it's these that change.
Yes, the contacts are tied to the bimetallic.
We're on the right page. We agree with each other.
Yes. Please, can I make my comment, an additional comment too?
Because this is important. So, Daniel, did you think that was the way that they operated as well? Like, did you think, that these bits here go open circuit?
Daniel is on mute.
You're on mute, buddy.
Sorry, muting. They not so much that they would break the supply, but all three of them would need to break in order to change the contactor.
Yes. So this is why I'm cutting you off, James. Sorry, because we need to come back to the original point. So what I think you're saying, Daniel, is sort of the same as me. So they're not. It's not breaking the supply, but that's why, coming back to Pal's original question, if he's still here, that's why they wrap around, and like the whole load has to go through all three of these for it to work properly. It needs to see the whole draw, because you set it. It's a setting, a little dial that you set. So that little dial needs to see the full load going through all of those poles, all three poles. So yeah, that's how I believe the physics works behind it, which I wasn't sure 100%, but Daniel, that's how you understand it as well then?
Yeah, I believe they're just on there, just measuring the temperature as such.
Yeah.
And it passes through the contactor as normal.
Yeah.
It would need to break all three of those metallic strips in order to change the state of the relay on the overload.
Yeah, and that's the important thing. That's why I was being like a bit of a dick about this, is because it's so important to not think that just because you've had a thermal overload that these bits break open here. Like, that's not how it works. They're just for sensing. They're closed circuit all the time, but they need, like we just said, the whole draw of the circuit going through them to then affect those contacts over here, which are a part of that bimetallic strip that we were talking about, which is why it's wired like that, which is why the normally closed is wired in series with the C1 contact, which will, if there is a problem here, it pulls out that contactor. It stops it energizing. So that's what I just want to be really clear on that, guys, because there's lots of confusion around this. I've been confused about it myself, and that threw some more confusion my way. But unless someone's 100% confident that it works differently to that, please tell me, because it will make me go and test it again. But I have tested this many times.
Quick comment, Chris. Really glad what we discussed so far. Only one thing bugs me with this neutral, because if we want to have full load through all poles going through, in that case, we cannot leave the neutral out unless we loop twice through each pole. Does it make sense?
Well, we still got the same load going through. So even if sorry, mate, just say that again. My brain has just gone elsewhere.
Right. We have three poles on this contactor. And what was said before in that discussion, which I really liked, we said we need to have all poles, and to work it properly, we need to have all poles current, seeing the load.
Yeah.
If this statement is true, it means we don't want to leave neutral out.
Right, cool. I'm with you. Let me show you. it's still the full load. So with the neutral going in there, because we got the load going through here, through here, through here, and then it's going back on the neutral, remember? So that full load is still going through it.
It's all good on the picture, but what we said at the very beginning, it's getting a long story now. At the very beginning, we said we can leave that neutral outside of contactor, which is.
Let me show you. So say we didn't have the neutral, that's just over there, we'd wire it slightly differently. So we'd go into pole 1, and then we'd loop there, and then we'd loop like this, and then we go like that. Or sorry, like that. That's still the full load going through it.
Makes sense. Yeah, perfect. Okay, I think I'm satisfied with his answer. Yeah, fantastic. Good job.
Cool, man.
Please, I wanted to make a comment. Sorry.
Yeah, James, sorry. I didn't mean to be cutting you off and stuff a minute ago. It's really important, that bit, that everyone is crystal clear on that operation, because it can cause major issues, obviously, if it's not understood properly. So sorry for cutting you off. So yeah, please go ahead.
I'm very fine. I'm very fine with the explanation. So, with regards to Powell's question concerning switching the normally close contact with the coil of the contactor. So I'm just going to speak from a physics standpoint. Yeah. So since they are connected in series, so current for loads connected in series is the same. So irrespective of their current.
Yeah.
Current is the same for loads connected in series. So irrespective of their position, whoever comes first, provided the return leg is active, whether we put the contactor in front or we put the overload in front, whichever way, is the same current that flows through them. So it will still act the same way, which was your explanation, and you're very correct. Provided the return leg is actually in place. If there's no return leg, that's when it's an open circuit. So that's consistent with the electron flow.
Cool.
So it doesn't matter which one comes first.
No, it doesn't, because they're in series together.
Yes, sir. Yes, sir.
Cool. I'm going to call it a day, guys. Good to have you all live, and that was a good little final debate that we just had. So yeah, thanks for sticking around for that and contributing. Appreciate it. Cool. So yeah, let's just start with Q&A. So any Q&As from previous lessons, or just anything in general before we get going, guys? Cool. All right, no worries. You'll have to forgive me as well if my voice starts sounding a bit funny. I've got a cold coming, so I'm trying to fight it off with Lemsip at the moment. So that's why my voice might sound a bit dodgy. Yeah, so it'd be interesting if anyone knows this. So I mentioned this in the sort of initial tech overview video in the drive about the PLC. So can anyone tell me, in terms of PLC physical connections, physical wires, what are really the three main things that we have going in and out of PLCs in terms of cables and wires, category wise? Can anyone tell me?
Are we talking like inputs and outputs?
Yeah, so that's two. Yeah, exactly.
Well,
nice one, Russell.
You've got digital inputs, you can have universal inputs, and you can have analog outputs.
So yeah, you're definitely getting there.
Yeah.
So yeah, that's the first two, inputs and outputs, and then we come back to what you said, Russell, about analog and digital. Can anyone tell me what the third thing is?
Bus.
What was that? Sorry.
Is it a communication bus?
Yeah, exactly, mate. Communication. So in the system that we're working on, we've got two different communication protocols. Can you tell me what they are, Daniel?
PSID.
Sorry?
PSID.
PSID, did you say?
PSID and
someone else. So we've got two different protocols. Mohammed, can you mute yourself? Cheers, mate. Yeah. Mohammed, I'm gonna have to mute you, mate, if you keep interrupting like that. Mercy, have you got your hand raised to ask a question, or? Oh, okay, cool.
Yeah, is it either through Ethernet or IP protocol?
IP protocol. Yeah. What was the other thing you said?
And Ethernet.
Yeah.
An Ethernet wire.
Okay. Yeah. So we're basically there now, guys. So we've got Ethernet, which is our IP protocol. Exactly that, Merceline. Thank you. And then, yeah, Daniel, you mentioned the KNX protocol. So yeah, we got two different comms. So yeah, three things: communication, inputs, and outputs. And then in terms of the inputs and outputs, they're either digital or they're analog. So what defines a digital input or output? Anthony Ibarra. Can you tell me, mate?
Hi. What defines the digital or analog input or output is the type of signal that comes out, if it's on and off, if it's digital, or if it's analog, it's an increase in value. So like, let's say a potentiometer or something, like something that you be increasing the value, like a knob or something.
Exactly that, mate. Yeah, nice one. So
like temperature, the output might be temperature, but that's an analog output.
Yeah, exactly. So digital, whether it's input or output, is on or off, it's true or false, it's open, close, it's one of two states. And then analog is a range. So like that temperature example, it's a range of, and it's sort of determined by the PLC or the sensor. It could be, in terms of temperature, it might be like minus 20 degrees up to 80 degrees positive, something like that. So yeah, spot on. So those are the sort of three things to remember when it comes to physical wiring. Comms, inputs, outputs, and then inputs and outputs also are split into analog and digital. So if we go to page 10, and with that being said, guys, this first module, this first Zenio module, all in box, this is basically kind of clues in the name. It's like an all-in box, so it has various different inputs and outputs. And we can see over here on the right our comms. So we got our Ethernet connection, and this is, we're running IP protocol on this Ethernet. So it's just like an internet connection cable, pretty much, guys. That's the easiest way to think of that, what you stick in the back of a computer. And we've got our KNX bus as well. So KNX bus, I'll tell you, that just is a bus. It's a twisted pair. And that just links all the different KNX modules together within the panel. So you can have a look at this on the images as well. And it just basically links all of them together. And then also it goes off to the terminal blocks in the panel to then also go off to anything in the field if we've got any KNX devices out in the field. I don't think on this project we do. No, actually, no, I don't think we do. But in other projects, like we might have switches. If it's like a residential project, we might have like switches on the wall. We might have motion sensors, etc. So yeah, that's our twisted pair communication using the KNX protocol. And then our Ethernet connection. Can someone tell me what this Ethernet connection, what this connection to the internet is actually doing in terms of like the system as a whole? Agron Nur-Adeli. Sorry, I can't pronounce your name, mate. Agron.
Fine. Agron Nur-Adeli is fine. I believe through internet, as you say, through IP addresses, they do communicate with each other, so we can give commands and stuff if they have the same IP address, if I'm not wrong.
So we're not communicating between devices or modules with this Ethernet IP connection. That we're doing that through the KNX bus.
Sure, okay. So this one, well, I'm not very sure, to be honest, but if we have an internet connection there, is it just to make it easy to communicate the bus?
Yeah, you're on the right lines. Could someone help him out?
Is it so you can view the state of what the equipment's doing from a different screen?
I just lost that last bit. From what, mate?
So see the state of the PLC and what it's doing in like an office, for example, without having to physically go and check the panel.
Yeah, exactly that. It's so we've got It's connected to the internet. That gives us our connection to the internet. So yeah, bang on. And then we can monitor, control, get feedback, get notifications from that connection there. Obviously, we need to program things and we need to set up the network in the right way. But this gives us access to the system from the internet, basically, and allows the system to communicate out of this school to anyone else who's sort of monitoring it. So that's what that's there for. There we go. So that's our comms. Now, this first, well, obviously we got our power, that's standard stuff going through an MCB, so we should all be familiar with that now. This lot of inputs, outputs here, Antonio, tell me what they're doing and what input or output they are. You've disappeared. Someone else, Savvy, how you doing, mate? Also, I think if you want to unmute yourself quickly, guys, I think the space bar, if you just hold the space bar, I think that just takes you off mute whilst you've got the space bar held, I think. That might be a quicker, easy way to do that. Yeah, Savvy, sorry, mate. What are they doing?
Basically that's what we covered in the previous ones where the PLC takes over automatically as opposed to doing it manually. So this controls all the the boilers, everything else automatically, whatever is programmed.
Yep, so it controls the pumps automatically.
Yeah, heaters, meters, whatever, kitchen pumps, yeah.
What are these though? Are they inputs? Are they outputs? Are they analog? Are they digital?
The 24, they're on off, so it must be digital, wouldn't it?
Yeah, they're on off, so they're digital. And are they inputs or are they outputs?
They're got to be outputs because this is what's controlling it, isn't it?
Exactly, mate. Yeah, well done. Yeah, spot on. So these are digital outputs in the form of what? Anyone?
Relays.
Relays, yeah, exactly. These are relays. Pretty standard stuff for digital outputs, relays. You might get like a solid state output, but most common is just a relay, on or off. So yeah, that's what those are. So they're digital outputs in the form of a relay going out to control our pumps when we've got our cam switch set to auto. So that's what they're doing. Now we've got these, if we look down here, we've got temperature sensors. We've got a whole load of temperature sensors. So before we get into the details of sort of how they're working and how they work and how they're wired, someone tell me, Stephen Parr, tell me again, what are they? Digital, analog, inputs, outputs? Danny Gray, can you tell me? All right, I'll tell you guys. So these are analog because they're temperatures. So there's a range. So they're temperatures. Analog inputs. And yeah, I just said it, they're inputs. So they're analog because they're a temperature, and they're inputs because they're feeding data and information into our system. They're not controlling anything. They're just feeding data in, so then we can program off them and control something. Or maybe we're not even controlling anything off the back of it. We're just monitoring. And if something gets to a certain temperature, maybe we program it to send us a notification or an email or something like that. I'm not going to go through the control and the wiring of the pump control up here because we've done that already in previous sessions. But in terms of the temperature sensors and the wiring, so what we've got is like a common, as you can see here, C1, and that's basically sending out a voltage. I can't remember off the top of my head what voltage it is. Could be 3.3, might be 3.3 volts. But that's sending a voltage out. And you can see here what I've done with the wiring is within the panel, I'm just sort of looping to each of these terminal blocks. Okay, so that's the voltage going out to our temperature sensors. So they're going out, and then pretty simple, guys. They're just going through the sensor and then back in via the terminal block into the PLC. So this is like what's this leg here is what's actually, depends on what sensor it is, whether it's like a passive sensor, an active sensor. but this is going to be a variable signal back, variable voltage, let's just say. Similar to let's just say for this, it's voltage because it's easier to understand. So this might be saying, let's just say that this temperature here of this flow temperature, let's just say it's 50 volts. 50 degrees. And just for simplicity's sake, just so we can all understand it, this is a 10 volt, or this is an active sensor, and we're sending it 10 volts. And the range of this sensor, again, I'm just doing this for illustration purposes. It's not actually doing this, but just paints a picture. This sensor is it's got a range of 0 degrees to 100 degrees. That's the range it can measure. If it goes over that, then we don't get a reading. If it goes under that, we don't get a reading. And we're tying this because, as I mentioned, we're pretending that this is a 0 to 10 volt signal, this sensor. So if that's in the field and there's a temperature of 50 degrees, Danny Gray, what voltage are we getting back here into the PLC?
Is it 25?
It's not, mate, no. So we got, it's a 0 to 10 volt.
Sorry, 5.
5, mate, yeah. Exactly.
Sorry.
Yeah. If we get 20 degrees, like it's measuring 20 degrees, Merceline, what would we see then in terms of voltage?
Sorry, the sound cut off a little bit. Can you repeat the question?
Yeah, so if we're seeing 20 degrees on this temperature sensor, and it's a 0 to 10 volt sort of control signal or feedback signal, what voltage are we getting back if the temperature's 20?
2.
2, did you say?
Yeah.
Yeah, exactly. So does that sort of illustrate, guys, sort of how that is split, like how it's sort of determined? So the voltage sort of correlates to the temperature. So that's like an analog signal. That's how an analog signal is put in simple terms, or how you understand it in simple terms. And then obviously off that voltage, that the PLC is seeing a voltage, but then it then converts that into something that makes sense to us as humans. So temperature in this case. And then we can obviously do things off the back of that temperature. So that's happening on all of these temperature sensors, guys. So going out, going through the temperature sensor, and whatever that temperature is, maybe it's 50, maybe it's 100, 20, 10, whatever. And then it's feeding that back into the PLC, and then we're doing whatever we need to do in terms of the programming off those. Who can tell me, and I'll be very impressed if anyone can tell me what this, hang on a second, what this is doing and this is doing, and what it indicates. Can someone tell me?
Shielded.
Shielding, yeah. So and talk to me. So this is shielding, Michael. Like, explain that in sort of physical terms, like that we can all relate to.
A Faraday cage. It removes any background noise. Basically, you just do it to one end, do it to both ends. It defeats the object.
What do you do?
So you make off the shielding, twist it, and then you tuck it in the earth, and then that will protect any noise from any other voltages, any other cables, to protect the signal what's coming back, basically.
Yeah, you're bang on, mate. So this is indicating an earth point. So all these first terminals here are earth. We're connecting them to earth. There's no cable. These terminal blocks, they connect to the DIN rail. The earth point connects to the DIN rail, so it sort of automatically earths itself. But yeah, the shielding, so this is indicating shielding. And yeah, like Michael said, either you use the sort of the shielding, the film, the sort of like tin foily like stuff around the inside of the cable, so it's sort of just sort of one layer into the plastic. So you remove the plastic, the next layer, you've got like this film that sort of wraps around it. So you can earth that again, one end, normally on the panel end. And what you do get, certainly in K&X cable, you also get it in Belden cable, which is another sort of common control cable, is you get what's called a drain wire. And this is basically doing exactly the same thing. It's like a little, very thin piece of sort of metal cable, like bare cable, that's in there that you also earth, or you just earth that, or you earth both, doesn't matter. And that does exactly the same thing. So it takes the noise out of the cable, or potential noise, potential interference out of cable. And certainly when we've got analog signals, like temperatures, like pressures and stuff, that those signals are sensitive, and they can be like, they're very sensitive to inductance and like other cables running near them. Like if we've got, like, let's just imagine we've got, we've got this cable here is our sensitive analog temperature cable, right? And we've got like a temperature running on this one, just like we've got here in the schematic. But running alongside that, we've got a high power variable frequency drive cable, right? Now we shouldn't ever have this. We should hopefully have designed things in a way where this is never happening. And if they do need to cross, they're crossing like that. They should never run like that. But, you know, just to be on the safe side, like, that's why these cables have drain wires in. So if that does ever happen, and I'm not saying that this, what we're talking about here, will actually prevent and remove all the interference, but it will at least mitigate some of it, if not all of it. But if this is a variable frequency drive cable running next to this sensitive analog cable, and it's like, you know, the power's going up and down, that's creating a lot of noise and interference right next to this very sensitive analog cable. So that's why these have drain wires, shielding, film, whatever you want to call it, in them, and why we should earth them as well. Because if you don't, I mean, I've seen it before, certainly on industrial sites, where you get like intermittent problems, and they're just an absolute bastard to fault find. So just a simple thing to start off with, something that you can rule out straight away is, you know, interference, and to make sure that you have sort of earthed all your analog signals. And actually, if you look in the tech manual, it says to earth the digital signals as well. So if you want to do belts and braces and be, you know, 100%, then it's worth earthing digital signals as well, because again, they can be interrupted and issues can happen on those as well. So that is the analog inputs, and it's all the same. We come back to these if we got time. So those are the analog input signals. So let's go to the next page. Actually, let's do questions. We're halfway through. So based on what we've been through so far, guys, does anyone have any questions on that?
Yes, I got a question.
Go for it, mate.
All right. Right there, when we just saw the temperature sensors, the cables going in and out, there's 8 of them. Well, how come there's 2 connections, like 4 connected to in series with each of them?
This one.
Why do you got 4 and 4? Yes. Why you got two of those? Like, yeah. One, so that's 1 through 4, and the other one 5 through 8.
Yeah. So again, it's kind of determined by the module that you're using. Again, this is why we all need to read tech manuals to understand how to wire things. But with these Zenio modules, this is basically, think of this as like a supply voltage. So it's sending out a supply voltage. And so I'm using that one C1 output, because there's only one of them. Actually, I think there's 2, but in terms of drawing, it doesn't matter. There's one output. So then I'm distributing that supply to all the analog sensors. So I'm just doing it. This is just a cable, or actually it's not a cable. If you look at the images, and you'll have to look closely, it's just a little bus plastic bus connection that you can stick into the terminal blocks, like one, two, three, four-way sort of bus connection, Wago connector, and that basically bridges that supply across. So to answer your question, mate, it's a voltage supply going out to all of these temperature sensors. So it's basically the same thing as just doing that. But because we've only got one point of supplying that voltage, I'm distributing it, as you can see there. Does that answer your question, Anthony? Cool. Any other questions, guys? Cool. Okay, let's go. Let's move on. So the next modules on page 11, we've got a mini box. We got 3 mini boxes. So someone tell me what these mini boxes are doing. Inputs, outputs, analog, digital.
They're inputs.
They're what, mate?
Inputs.
All of them?
Well, you've got 4 to 20 milliamp inputs.
Yep.
Obviously, you've got 0 to 10 volt outputs, analog outputs on your third module.
Yeah, exactly. So we've got our 4 to 20 milliamp inputs on actuator 2 and 3. That's just how I've named them. It's not important. And then over here on actuator 4, we've got analog outputs. So we should be fairly familiar, relatively familiar, if anyone can remember back to the boilers. And as Russell just mentioned, these are 0 to 10 volts, volt outputs, analog outputs. So yeah, 0, it will vary 0 to 10 volts. And so anything from 0 to 10 and then anything in the middle. And these are going off to our boiler 1 and our boiler 2. Someone explain to me what they're doing and how it's all working at 0 to 10 volts going out and to the boilers. Yeah, what's happening?
That's your enable signal.
Yeah, so it tells the boilers to enable. What else does it do other than just enabling?
How much to enable?
Is it just enable though? Because with enable, it's just enable or not enable.
No, an analog signal to tell them how much power to produce.
Yeah.
Modulation.
Yeah, it changes it modulates, it changes the output or the power of those boilers. So yeah, spot on, mate. So what's happening here is the 0 to 10 volts, whatever that is, however that's been programmed, and this will change based on data and information that we're getting back into the system from those temperature sensors that we've just looked at, if I remember correctly. So based on those temperatures coming in, that then determines the output of those boilers. So then the PLC will decide, whether it's 1 volt, whether it's 2 volts, 3 volts, 4.5 volts, whatever it might be, is getting sent out to the boilers. So someone else, if let's say we send out 5, the PLC is sending out 5 volts, what is that in terms of the boiler?
Running at half capacity.
50%.
Yeah, it's at half capacity. What about temperature wise? To be a bit more specific.
How many degrees you want it to run? Temperature degrees.
How much, mate?
In degrees.
Yeah.
Give you the temperature set point, whatever you want it to be.
Well, what will it be?
50 degrees?
Did you look at the tech manual, Mike?
No, I didn't, sir.
To be fair, I didn't either, mate. So, but yeah, let's say it's the system has decided to send out 5 volts. Off the top of my head, that's going to be sending probably like a 60. That's going to translate on the boiler to, I think, like 60 degrees C, something like that. It's going to be in the range of like 10 volts is going to be on the upper side of 90 degrees, and I think the lower side is 30 or something. 30, can't remember, but yeah. So yeah, 10 volts will be over here, 90, and probably 1 volt over here would be 30, and somewhere in the middle, 5 volts is going to be 60-ish, something like that, guys.
So that's basically like monitoring the state of the boiler in terms of temperature, and depending how much, like the conversion from voltage to temperature.
This here isn't. No, this is what's sending the voltage to the boiler. So this is the output side. What's monitoring what's determining that and what that sends out is most likely, trying to remember off the top of my head, is one of these temperatures on the flow and return, and it's just looking at it basically and determining, do we need to increase the heat of the boilers or do we need to decrease it, and then it's going out to the boilers from this module here. What we've also got, so over, I can't remember without looking at the data sheet or tech manual, what type of sensors these temperature sensors are. I think they're passive sensors. These ones over here, though, however, these are active 0 to 20 milliamp signals. So on a bit of a side note, guys, when we talk about analog signals, generally speaking, and if anyone can add to this, please do. But generally speaking, analog signals, they come 0 to 10 volts. They go 0 to 20 milliamp, or it's 4 to 20 milliamp. So analog signals are one of those three types of signal. And I'm not going to tell you, but I encourage you, if you're interested, to Google and understand what the difference is between these three types of signals, why some are used for some applications and why some are used for other applications, because it's really interesting if you're into that sort of thing. And actually, someone can tell me Friday.
Chris,
so yeah.
Sorry, Chris, it's Russell. You know your 4 to 20 milliamp controllers, them modules, do they give out 24 volts for them to work like, or do you have to get the 24 volts from somewhere else?
I don't know what they're throwing out, mate. I can't remember off the top of my head. I haven't read the tech manual in detail for a while, but yeah, it's getting sent out. It's being sent out from that module. It's not getting it elsewhere. Guys, just with questions, I'm not having a go or anything, but let's just wait for like specific times to ask questions, just because it can distract people from what we're talking about. So yeah, 4 to 20 milliamp. So this is one of those three signals, and it's a 4 to 20 milliamp signal that we're using. These are actually pretty cool modules. If you look at the tech manual, you can choose whether they're 0 to 10 volts or 4 to 20 milliamps. So you can use them for different applications. Whereas a lot of other analog modules, they're either be one or the other. So they're flexible in that regard. But it's very similar stuff to what we were just talking about with the temperature sensor. We've got supply going out, going through the pressure sensor, and then back to the module. And it's an analog signal. And in this case, we're looking at 4 to 20 milliamps rather than 0 to 10 volts. And when it comes to pressures and stuff, I'm pretty bad. So let's just say, let's go just 5 bar on the high end. And yeah, and then let's just, for simplicity's sake, 0 bar on the low end. So yeah, if we're seeing a signal, if this pressure sensor is seeing 2.5 bar, what does the PLC see? Paul Spearman, mate, can you tell me? You there, Paul? I'll ask someone else. Max Robbins. Yeah.
Sorry, Chris, I missed the question.
So if this is a pressure sensor out in the field, right, and I want to know what the PLC is seeing in terms of this signal, if this pressure sensor out in the field is seeing 2.5 bar. What is the PLC seeing?
I'll be honest, I don't know.
Can anyone tell me? And don't worry, mate, it's all good.
Maybe 12.
8 milliamps.
Put it in the chat, guys. Chuck your answers in the chat. 8 milliamps, 12 milliamps. 8, 12, 8, 12. Okay. So how would I do this? So calculator. So actually, I'm not even going to attempt to do the maths live because there's too much pressure. So yeah, so you're probably right, one of you. But basically, that's in the middle. That's in the middle of that.
12 milliamps.
12 milliamps, yeah.
Or is it 14 milliamps?
So there's too much pressure for me to work it out live, guys.
Definitely 12.
It's definitely 12. Okay, thanks. It's probably quite a simple calculation, but I won't even attempt it because I know I'll just make myself look like an idiot trying to work it out. Yeah.
No, it is
16 milliamps between the two. So split up.
Yeah. So we're getting 12 milliamps back, which is basically, I don't know why I just rubbed that out, but yeah, that is sort of the mid range between that 4 to 20 milliamp signal. If you work it out, what happens? What do we see? Let me just write it again. 4 to 20 milliamp. Okay, what if we've got 0 bar? Here's a question for you. If we've got 0 bar, what do we see? 0 bar, no pressure. What do we see up here? Someone tell me.
4.
Yep, we see 4. And this is where a 4 to 20 milliamp signal is. I said I wasn't going to tell you actually. So I'm not going to tell you. We come back to this Friday. I'll give you a little clue. That's 0 bar, but if the cable, there's damage to the cable, damage to the sensor, and we were getting nothing, like there was nothing, we were getting sort of nothing back here, just think about that when we're thinking about different uses of analog signals. I'll leave it there because I'll give too much away otherwise. But yeah, so anyway, pressure sensors, very similar to temperatures, but we're just using a different signal. Let's now go what's the time? Yeah. So we should be fairly familiar with page 12 and 13 as well. So, and we've been talking about this most of the week. So what's happening on page 12 and 13 in terms of these PLC modules? Sammy Wade, how you doing, mate? Can you tell me?
Yeah, hi. So are these are all the second contacts of the relays that link to sort of all the lights within the system?
Yeah, exactly, mate. Yeah. So what signals are these? What type of signals are these?
So these would be, hang on, let me just check my notes because I did write it down.
Well, you got a little clue right here.
Yeah, so they're digital signals.
Yeah. And why is it digital? Just remind me.
So I would have said majority of them are running off the relays, which are the safety circuit or the interlock circuit, which are all 24 volt, but on and off via the contacts.
That's the key word there. On or off. So as we can see here, this is off. This is off at the moment. And as we know from earlier sessions, it's either off like that or it's on. So yeah, it's either off or it's on. And on obviously looks like that. So yeah, digital inputs. And as you rightly said, Sam, they're the second pole of all those 2-pole relays that we've been talking about all week for the lights on the front of the panel. So this is where we've doubled things up. Whenever we see something happen, like the boiler goes into fault or the safety circuit triggers like we've got here, we can also see that in the PLC, and then we can do whatever we need to do off that in terms of intelligence and programming and stuff. So wiring, similar to what we saw on that previous module. So we've got a common output voltage, and this is 3.3 volts, and it's like a little closed loop system. So it's sending out 3.3 volts, and I'm just distributing that across the common of all of the second pole of each relay. I'll say that again. So I'm distributing that 3.3 volts to the common of the second pole of the relay. And then as you can see, we've got these configured. They're all normally open. We're not using any normally closed. They're all normally open over here and on the other page as well. So let's just talk through that. So yeah, we've got our 3.3 volts going out, and it's going to the first relay, pole 2, relay 1, the common. And then we're also distributing that with, you can either use a cable. I'm using these little Wago bridges because it's quicker and neater and less wiring. And that's bridging to the next relay, pole 2, common input. This is the common, and so on and so on. So that 3.3 volts is getting distributed across all those commons on the second pole of all the relays. And then as soon as we've got a safety circuit issue, and we should all be pretty familiar with how these work now, we've got a safety issue, that then closes, and then it sends that signal back to the PLC, and then the PLC sees that signal. It's come back, and it's exactly the same. It's exactly the same principles for all of them. So the pressurization unit, that's all good. It's in a healthy condition, and then it goes into fault. So that energizes that relay, closes that, and it sends that signal at 3.3 volts back to the PLC, and then we can see that, and then we can program off the back of that. And it's exactly the same principle, guys. As you can see, it's drawn in exactly the same way across page 12 and 13. We haven't talked, actually, what would you prefer to do? Actually, I think what's going to be more valuable to you guys is probably if we just talk about the spec briefly. I don't want to go into all the details of the spec. I've only cut out some of the parts, but it will just give you an idea of the programming side and how we're using the PLC. So I'll talk you through the spec, or a few of the things from the spec, in a minute. These here that I said that I'd come back to, these are basically just relay outputs, so more relay outputs, exactly like what we've got over here. These are just relay outputs, controlling over door heaters out in the field that just have an on and off signal. So like just switching them on and off, like an electric heater above a door. That's all they are. So nothing special there. Hey guys, me again. And this is just a reminder to actually download those schematics for this project, so you're able to learn on a much deeper level. As mentioned at the start of the video, they can be found in the description. So click that link, you'll be taken to our free community, where the first thing you'll see will be those schematics. So download them, come back to this video after you've downloaded them, so you can actually get to where you want to go, so you can actually understand schematics, so you can become a better engineer, progress your career, progress your business, whatever it might be. Download those schematics. It will seriously, seriously help with all of this. Sorry, before we go and have a look at the spec for like 10 minutes, has anyone got any questions before we move away from the schematic today?
So that main all-in box,
yeah,
is that then feeding the power through the KNX to the other units?
That's a good question, mate. Yeah, so this is the only module that actually needs like a 230 volt power supply, and then this is the module that then you've got to understand a little bit about KNX and the KNX bus and how that works. But just briefly speaking, this module does everything. It's kind of like your power supply for the KNX bus as well. So yeah, basically the KNX bus starts from this module here, and then it goes off and then powers all of these modules. So all of these modules are just powered off the KNX bus. They don't need any other external sort of supply or voltage.
So then from the photos of the panels, you've got your red and black is your KNX bus.
Yep.
Is the white and yellow cores doing? Because I can't see them on the drawing.
In yellow. Yeah, so guys, if you're not familiar, KNX has two twisted pair. The first pair is black and red. That's like the main one that's used, and that has power and comms going through it. Now there's also within the KNX cable, there's another twisted pair which is yellow and white or yellow and grey, which most of the time isn't needed, isn't used, but is there for devices, KNX devices that require a higher power input output, like more power. They require more power. Can't think of a good example because I've never really used it. But yeah, that it's just like extra copper to supply more power basically. But we're not using them in this project, and I've never used them. All good, Daniel? Cool. Any other questions before we move off the schematics, guys?
What do you mean by passive and active sensors?
That's a bit too much to get into right now, and if you Google it, you'll find out straight away. Marco, what were you going to say, mate?
Rail Quad 8. You say that this is digital inputs.
Yes.
But in manual, this is analog and digital inputs in manual.
Say that again, mate.
I see in manual that it is analog and digital input.
Yeah, they can be both. You can program it. This is the beauty of these Zenio modules. You can program it to be either digital or analog.
Okay.
Is that what you're saying, Marco?
Thank you.
Yeah. If you look in the tech manual, guys, it tells you that. It's it's what I love about these modules. Yeah, so this isn't the full spec, and this isn't the full bit. This isn't the whole bit when it comes to like control of like the boilers and the secondary circuit. I've just pulled out bits that might be interesting and are a little bit easier to get your head around than some of the other stuff. So the frost protection, let's start with that. So the spec, the M&E designer sort of gives you indication of how they want it to be programmed based on how they've designed things. You don't always get this. Sometimes you just got to use, your own experience and, what you think is the right way to go about things. But yeah, plant operation, frost protection. So it says here, ensure that when the outside temperature falls to the operator set minimum frost protection temperature, the selected pump starts and circulation is established through the pipework and their components. So the first question, guys, to ask yourselves is, well, frost protection. What is frost protection and what purpose does it serve? So frost protection, clues in the name, it kind of protects things against frost. So if the temperature, as it says outside, falls below what the operator puts into the system, and we get back to the operator in a second, if the temperature outside drops below that threshold, then the pumps, they kick into action automatically and they start circulating through the pipework. So why is that spec? Why is that part of the spec? Why is that important in a project like this?
So the pipes don't freeze in the building.
Yeah, exactly. So just imagine a half term, whatever, like 2 weeks off in winter that the kids have. I don't have kids, so I don't know sort of the period of time. But let's say through winter, the kids have got 2 weeks off school. The school is closed, and the temperatures outside are getting really, really low. We don't want the pipe work, the water in the pipe work, to get to that temperature and freeze over, because then that's expanding and contracting in the pipes and damaging them basically. So this is like a preventative measure, an automatic sort of preventative measure to stop that happening, and basically protect the fabric. If you'll see this, that they talk about protecting the fabric of the building, and this is sort of like the fabric of the building is the pipe work. So this is what frost protection is all about. Let's just touch on this, where it says like the temperature falls to the operator set minimum frost protection temperature. So that's saying that the operator or facilities manager, whoever looks after like this, the the equipment within the school, they're able to determine that temperature. Now, we haven't gone over any of this, so I don't expect you guys to know, but can anyone tell me or hazard a guess how the operator would set that temperature?
On the BMS?
Yeah.
Some sort of analog dial that then refers that data to the PLC in the variable.
Yeah, so that's probably a more traditional way of doing it. What would be a more modern way to do that?
The PLC.
But PLC, so the operator doesn't have access to the PLC. They've got to just be able to sort of like on a whim, as they like, just be able to.
Is it app control?
Yeah, you're basically there, mate. Yeah. So it would be more like an app-based thing. So I might have mentioned it earlier on one of the first sessions. I think I mentioned HMI. Does that ring a bell with anyone? HMI.
Yes, it does. Human machine interface.
Yeah. Human machine interface. And you'll see this on most BMS panels is it will have basically a tablet. Yeah, I definitely did talk about it. Like a tablet like that mounted in the door of the panel. And this is how, in this case that we're talking about here, this is how the operator would interact with the system and set that temperature. Basically for an app, like Sam said. So moving on to the next point. So allow operator to, again, in a similar way, allow the operator to pre-select which plant is to be started. The automatic standby plant is to operate on failure of the duty plant. That's basically saying allow the operator to choose what pump runs first when it does this frost protection cycle. Sure. Let's move on from there. We'll cover one more. Yeah, so I'll just read the 2 points here. So the BMS or BEMS, you'll see that more commonly now. So rather than a BMS, which is a building management system, they're usually referred to now as building energy management systems. The BEMS will start the primary constant speed shunt pump on the cool for heat. And once flow has been established, the lead boiler will be energized. So that's saying that firstly, the shunt pumps for the boilers, this is how it's starting up. They start running, and then once a flow has been established and detected, then the next part of the sequence is the lead boiler, and the lead boiler will be like whatever one is sort of in the duty mode, or is first in the cascading, in the sequencing. That first one will be energized. The time intervals between the stages and boiler switching for both increasing and decreasing load conditions will modulate in unison control. It's a bit wordy, but basically what that means is they're basically, they're fire up. I think it's more clear on this bit here. So once a call for heating has been established, each boiler module shall step on its lowest rate. So the first boiler kicks in, and then the second boiler kicks in, and their lowest output. So let's just say, argument's sake, 30 degrees. So they're both outputting 30 degrees. And then they rise simultaneously together to match the system load. So not one of them going up on its own. They're both rising together until that reaches like the right amount to match the demand of the system, basically. Whatever the demand and all the rooms in the school are demanding, it automatically determines like that temperature that it needs to go up to. And then the BEMS will stop the boiler units sequentially to maintain constant temperature flow set point, blah, 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 as measured on the primary inlet of the low loss header. So then stop start is probably not quite right. This is the problem with these specs. When you get specs from M&E designers, they're basically a copy and paste job. So on some systems, you might have digital control on or off, like it's saying here, start and stop. On this system that we're working on, we've got analog control. We've got that 0 to 10 volt control signal, which is a much more efficient way to control boilers, because you don't have that overshooting of temperature and then like off and then it undershoots. This is like your target temperature, let's say. It doesn't keep overshooting and undershooting because it can only ever be on or off. So you get this sort of waste, basically waste of overheating and then discomfort where it's under. With an analog signal, it's basically a much smoother temperature, basically much more accurate. So yeah, this doesn't necessarily make sense like start and stop, but basically it's saying it will modulate those boilers based on what is measured on the primary inlet to the low loss header. And if you look at the schematics of the hydraulics, you'll see where where the primary temperature, where the temperature flow set point is for the low loss header. That'll be clear there. So it's looking at that and then determining how to modulate the boilers. I'm going to leave it there, guys. Does anyone have any sort of questions before we shoot off?
Can I ask a question, Chris?
Yes, mate.
It's going back to what you were talking about earlier, not related to this, but the 0 to 10 volt output that's on those Zenios that go to the boilers. A couple of sessions ago, you were talking about you restrict a lot of them, say to 80% max demand. Would that mean that's done, I guess, in the programming side, so they'll only ever put out, say, 8 volts on their signal? Is that?
Yeah, you could do that. Yeah, you would program, like if we needed to do that. It depends on the application. But yeah, you would never program it to put out more than that set threshold. Yeah, is that kind of what you mean?
I think so. So that's kind of all done on the programming on that Zenio. You'd say you'd never put out more than 8 volts, 7 volts, whatever the upper limit is. Yeah. But what's most likely, and again, it's checking tech manuals and stuff, but most likely what you'll see is, let's say we put out that max 10 volts from the PLC module. That will then, and I think someone held it up in one of the previous lessons, held up like the tech manual, and it shows you this curve. Here it is again. Nice one, Daniel. What does 10 volts translate to in temperature?
It depends. You can set the boiler to do 3 different top temperatures. So you can either set it to 50, 70 or 90.
Cool. So let's say we set it to, we program the boiler just on the boiler. If you see 10 volts, I want you to output 90 degrees. And then if we're setting it on that setting, Daniel, what is the lower end? What's that saying?
0 degrees.
So 0 volts is 0 degrees.
Yeah.
Cool. So we'd probably do that, Max. We wouldn't necessarily say we need to output less than 90 degrees because it's determined by the boiler. Like we can never go over 90 degrees. Like it's never going to get to 100 degrees where obviously that's a dangerous condition. I would just leave it to the PLC to determine. Yeah, basically.
Yeah. No, okay. So it's sort of something technically you could do, but you would normally set the boiler and then the PLC just gives out full go and the boiler deals with the max set.
It will give out full go if it feels that it needs to get up to temperature quick or meet a demand, like in the school, like loads of rooms need heat immediately. Then it would output there, but then it would probably settle back down once it's met that demand.
Yeah, I'm with you. Thank you.
Cool. I'm going to shoot off, guys. Any burning questions before I do? Cool. Right, so power, we should all be familiar with power. That's just coming in, single phase coming in through the door isolator, and then we're just distributing that 230 volts across the MCBs. That's where it's being distributed. And obviously we've got a neutral bar in there as well that's distributing the neutral. MCBs, those are the first points. So we're going through those MCBs. Actually, you know what, guys? I'm not going to go through the power because it's all pretty self-explanatory. And I want to, conserve time for more important stuff. So power stuff, we're just going to ignore, actually. So other than the power to the transformer, so we're transforming 230 volts AC down to 24 volts AC. So we got the positive side here, which is the 24 volts, and then we got the 0 volts over here. And then we can see that the 0 volts is just going down here, and it's basically being distributed across all the pages on the project. If you look at the images, that's just like a load of Wagos bussed together in the panel. So you can see that on the images. So that 0 volts just goes across all the pages. 24 volts. So we're coming out of the transformer, and then we're going via another MCB, and then this is our 100 circuit. So our 100 circuit is basically, if the transformer's good, if this MCB over here is good, then we get a constant 24 volt AC supply. And that again is being distributed across in the same way as the 0 volts. That's being distributed on Wagos bussed together, and then feeding all the pages in the project. And then the first place that we're tapping off, and again, remember what I said, guys, it doesn't, just because it's drawn in a particular way on the schematics, doesn't necessarily mean that it's physically wired that way. It might not make sense to always wire it exactly how it is in the schematics, but as long as it's doing what the schematics are saying, if you get what I'm saying. So the first thing that we're tapping off, that 24 volts is here, and you can see if you look closely, that's the 100 circuit. So 100 circuit going to this 24 volt AC healthy. So providing all of this stuff over here is good, that light will come on. So yeah, 24 volt AC supply, that light will come on. Next thing is, again, tapping off that 24 volts, is we got the lamp test button. So we push that in, and we can see that that's, if we look closely, there's a little gap there. So that is a normally open push button, and it's a momentary push button. So we push it in, and as long as we hold it in, that allows that power to flow through. And now you can see, because it's going through a different device or different contacts of a device, it's changing the number. So now we're onto the 400 circuit. So this 400 circuit then goes exactly like these other circuits, the LT circuit, so lamp test circuit, and that's just going across all the pages in the project and feeding the third terminal on each lamp, which is our sort of test input. So we got 1, which is our normal switched on and off. We got 2, which is our 0 volts going down here, and then we got our third one, which is our test input, and that's the same for every lamp. And you can see they're 400 circuits, so that's the same on every page. So now let's get into our gas detection system, and let's not focus too much on whether it's normally open, normally closed. Let's just not think about that at the moment. It's just just to understand the sort of concept and the logic. If it's inverted, it doesn't really matter. So we're coming off that constant 24 volt feed, and we're going into this gas detection system, which is in the field. And this is our generic fault output. So this will close or open, depending on whether it's normally open, normally closed. It will send that 24 volts back, or through the gas detection system, back into the panel and energize R1. And then that over here closes, if it's in fault, the power goes down here and energizes this lamp here. If it's in a healthy condition, and we go through that in a second, what makes a healthy condition, then that contact switches this way, and that allows our 24 volts over here to also be switched down the safety circuit. But what makes this gas detection system healthy is, let me just rub these out so they don't get in the way. So what makes that healthy is this circuit here, firstly. So this is a little sort of mini circuit as well. And if we remember, it's got like a little internal relay built into it. So it's sending, and this is the EM stop circuit from the gas detection system. So we're going out of that, and then we're going, this is just how I wired it. You can wire it however you like. But ultimately, we've got the E stop in series with the thermal links above the boiler or boilers, which detect if there's heat, and then it goes back into the panel, distributed across here, back out into the gas detection system, and like would probably energize an internal relay or not energize it, depending whether it's normally open, normally closed. So that's healthy. They're all good. Next page, let's just have a look at the other things that make it healthy. The other thing is providing there's no fire alarm. So we've got like an external fire alarm system, a fire alarm panel where we can basically use like a volt-free output from there, which just basically triggers open or closed, whether it's, you know, there's a fire or there's not, or it's detected or it's in fault basically. So we can tap off that fire alarm signal, and then that also feeds in to our gas detection system here and completes the circuit. So that needs to be there as well. And then the final two things is to make sure that there's no carbon monoxide leaked out anywhere through these or through this sensor here, and also just same thing with regular gas detection. So providing there's no gas leak, no carbon monoxide leak, there's no fire alarm over here, and that our E-stop circuit and our thermal link circuit are in check and they're all healthy, that then allows what we just went over. That allows that contact to close, and then a supply. Remember we talked about best way to think about it is just a supply. Like a supply can now go off down that safety circuit. So that's it in a healthy condition. And then when it's in a healthy condition, this gas valve will open, allowing gas into the plant room, boiler room, and feed the boilers. If it's an unhealthy condition, there's a problem, issues, then that will close and stop that gas feeding into the boiler room. We do lights on the next page, because they're all pretty much the same logic, same control. So onto the pressurization unit now. So power, we're not going to go through that because that's pretty standard stuff. But so we've got no problems on the gas system, and that's all healthy, which allows the power to distribute further down the system. And the first bit that it comes to, or the first rung, if you like, that's tapping off that is this one here, and that's going into the interlock output or fault output relay of the pressurization unit. So it goes in here, and then if everything's good, so there's no issues with the interlock relay, that continues over here back into the panel, and then supplies our boiler interlock circuit. So again, another supply. So providing we've got 24 volts AC, providing we've got the safety circuit and the things that affect that is okay and healthy, and providing this pressurization relay, interlock relay over here is okay, then we also have the boiler interlock circuit healthy. So now we're just tapping off the 24 volt AC. So we're coming off there, and this is feeding into our general fault output on the pressurization unit. Going through here, energizing relay 3, and then what that does, whether it's energized or not energized, just changes that contact from here to here. So energized, it goes here, so allows power to go down here and bring on that green normal light. And if it's not energized, the contacts go down this way and bring on this red fault light. So next page. So onto our first boiler. Yeah. So boiler. So again, we got our power, and then 24 volts. We're feeding our clip-in module that gives us our fault output and our enabled output, because by standard, these boilers don't have those outputs. We have to add in an additional control module that clips in that allows us to have these outputs. So we've clipped that in, and now we're feeding 24 volts into the common. And then if it's in an enabled state, and like we discussed in previous sessions, I think it's just if there's power to the boiler. So if there's power to the boiler, that switches that relay and allows that power at 24 volts to continue and energize R4. So R4 over here, so simple. That closes that contact, and then that flows down here and brings on that light. Also, let's remember, guys, that the majority of these relays, the second pole of all these relays, because they're all 2-pole relays, so the second pole of all of these, or the majority of them, also feed the PLC. So when that's just been enabled there, and that light comes on, we're also sending a signal into the PLC. So the PLC can see as well that boiler 1 has been enabled. And it's exactly the same principles with the fault. So if the boiler goes into fault, that also closes and then energizes R5, which closes this contact here and then brings on that light, and also tells the PLC that boiler 1 is in fault. So now let's move on to that 3-position cam switch on the front of the panel, where we can control whether it's in hand, which is like the manual control, or in auto, which is like PLC control, or it's in an off position, so nothing happens. So off position, obviously nothing happens. Hand, and we're coming off this. So yeah, important now, we're coming off the boiler interlock circuit. So this operation will only happen if, firstly, going back one step, we've got the boiler interlock output on the pressurization unit is okay, and there's no issues, and there's no issues with the safety. So kind of you can think about those two things in series. We need both of those to be good for us to have that sort of supply here at this point. So we put it into hand, and then that sends power down here. It energizes R6, and then R6 over here, those two poles on the relay. So this relay, this 2-pole relay, we're not feeding the second pole into the PLC, because we need the second pole here to switch the 10 volts and the 0 volts from the power supply, from the 10 volt DC power supply. So what happens here is once we've switched it to hand, those contacts close, and that allows the 10 volts to flow, or the positive 10 volts, well, actually it's just 10 volts DC to flow down this route and then into the boiler, into the, here we go, the 0 to 10 volt input. So we've got the 10 volts in there now, and you can see here, ground. So we also need to feed the ground, or the 0 volts, same thing. So we can also, at the same time, obviously, this is happening as well. So that's now feeding whatever we've got that set to now. And if you remember, again, previous session, there's that orange power supply, and we can adjust the output, like it's got a little potentiometer. So most likely we've set this to about 6 volts. So that's sending 6 volts into the boiler, and then that translates to, let's just say 50 degrees, 60 degrees. So the boiler's now getting a signal for 60 degrees C when it sees that 6 volts here. Now let's switch it to auto. So we switch it to auto now. So we're switching it through the off position and then to auto. So here we go. And then it's energizing R7. So now these contacts are closed. So this one and this one. And now we have to go off to page 11, D117, to see what's happening. I'm not going to go over there, but you guys can. So I know that that's now sending a 0 to 10 volt control signal from the PLC. So we're using a 0 to 10 volt output from the PLC now to determine what voltage that's seeing at the boiler. So now it's going to range between 0 and 10 volts. So 10 volts on a high end, that might be 90-degree heat. And then 0 volts on the low end, I think is, I can't remember. Daniel told me the other day. Doesn't matter. But something lower, we got a range between 0 and 10. So now that's what's sending the signal. So, and it's exactly the same, as you can see. It's exactly the same. We're sending the 10 volts or the 1 volt, 2 volt, 5 volt, 8 volt, whatever it might be, to this terminal, and then just the 0 volts to this one. But it's from the PLC this time. And then obviously we've got 2 boilers. So you can see, I know we haven't covered this in the previous sessions because it's exactly the same thing, but you can see here that I'm just tapping off the 10 volts and the 0 volts, going on to the next page, and it's exactly the same operation. So we've got our hand control over here, which is bringing on R10. So R10 closes and does exactly the same thing here for boiler 2. And then if we send that over to auto, it energizes R11. So obviously we've moved away from R10, so that will go open again. And now these will close. And again, it's just sending from the PLC over here the control voltage into boiler 2. So yeah, exactly the same principles as what we've just been through on boiler 1. Next page. So we're just focusing on boiler pump 1. The control for boiler pump 2 is exactly the same in reality. I haven't updated the drawing yet. You can find the updated version in the drive actually if you wanted to reference it. But basically we've got 2 times this over here on the left-hand side of the drawing. So yeah, just ignore it over here and just imagine we've got two of those. So yeah, this is we need to talk about the power here because it's part of the controls and what brings on the boiler pump. So we got our 24 volt, our 230 volts AC going through at MCB, and then we're going into terminal 2 of the contact. So we got contact here and then overload right below it. And we're just screwing the overload straight into the bottom of the contact. And then what that looks like in terms of like the wiring or the flow of electrons, power, voltage, whatever you want to call it, it goes through like this and then back into terminal 1. So this is the live, and then out here, and then obviously to the L, the live connection of that single phase pump. And then with the neutral, we're just going straight through. And like we talked about, guys, it doesn't really matter how you wire these contactors and overloads. You can have the neutral coming out. You can have like the neutral linking into more bits and just have the live going through one terminal, or you can do it like this. It really doesn't matter as long as the full load is being drawn through the overload here, else it won't work properly. So we've got our power, our 230 volt AC here, and then let's switch it to hand. So we're switching it to hand on the front of the panel. So we're going over here. So providing our safety circuit is healthy, we've got power here, and then we're going off down here. And then the first point we're getting to is the normally closed contact of this overload here. 95, 96. So as we can see, 95 and 96. So it's normally closed. So just normal state is closed. So that allows the power to go through there and then energize C1. Just like a relay energizes C1. So energizes C1, And then the contacts that you can see at the moment are open, they go closed. So those go closed like that, which allows us to actually complete this circuit, and then to the pump, and then obviously the neutral just goes straight through like that. Great stuff. That's the pump running. Now, we've got a really old pump in the field. It hasn't been maintained. No one serviced it. It's about 15, 20 years old. Bearings are going, blah, 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 and it's starting to wear. Or maybe, so there's more resistance. Or maybe a phase has been tripped out somehow, or a cable's a bit loose, or there's a cut in a cable, so the phases aren't balanced. So that starts creating this pump to overload, a thermal overload we're referring to here, and it's getting hot. So this is what this overload does here. It senses that. That's all it does, is it senses that. And when it senses it get to a certain point, what it then does, this is what we were debating the other day. This does not trip open. Very important. This does not trip open. It still stays closed, so there can still be power going through it. But what does trip open, or what does change, are these contacts here. So our normally closed contact now, because there's an overload, this now goes open basically. So it goes open, which cuts the power here, which puts this back in this state here. So we cannot get, so basically it cuts the power to the motor or the pump. So very, very important, guys. Said it once and I'll say it again. You need to ensure that you wire the normally closed contact of the overload, which is always 95 and 96. You always need to wire that in series with the coil of the contactor that's powering up the motor or pump or fan or whatever it is. And like we discussed, it doesn't matter if it's in front of the contactor or after it, doesn't matter, they're in series. But that's what trips out. That's what trips out this contactor here. Just because this senses an overload, these coils, just because they sense an overload, it does not create an open circuit here. So you cannot rely on this overload device to trip it out. That's why it has those contacts, those normally open, closed contacts. Anyway, I'll stop going on about that because I'm probably boring you. Right, so now we're switching it to auto. So we switched it off and now we're going to auto and we're going off to the PLC. So page 10, B102. And all that's doing now is I'm just going to draw it right here. Let's imagine we go off to the PLC, but ultimately all that is a normally open contact or relay being controlled by the PLC and the programming, which then determines whether that is open in this position or closed. So obviously if it's open at the moment, then this safety circuit gets nowhere and it just stays at this point on the PLC. But then the programming decides to switch on that pump, so it closes that contact. So it closes that contact, which now goes over here. It's exactly the same operation as we've just been through, guys. So it just bypasses, all it does is it just bypasses, when we're in hand, it just bypasses the PLC. So we're just putting kind of one extra relay in series, or one contact in series with this and this. That's ultimately what we're doing. So we need the PLC contacts to be closed. We need the normally closed contact of the overload to be in a healthy condition, and then that powers the contactor. So we're just adding one more thing in series. When there's been an overload, so if there has been an overload, this obviously closes and then it sends power to here, R12 comes on, closes that contact there, and then brings on that trip light because it's tripped out because we've got it, how we've wired it over here and what we just discussed, it will trip out that motor. So the trip light comes on. Also, we're doubling up that signal into the PLC. So the PLC also knows that that pump has tripped out. And then when it's in its enabled state, so it's running, so the pump's actually running, you can see here on the contactor, we've got normally open, which is 13 and 14. So when that's pulled in and there's power running through it, this closes 13 and 14, which I've drawn over here. 13 and 14 closes, which basically says, or it brings on this relay here, 13, which is over here, 13, and then brings on the running light or enabled light, same thing. And again, we're doubling up, we're sending that same signal to the PL. Next page is, yeah, so those are our dumb pumps, if you remember. Like there's no electronics, no intelligence within those pumps. But now we're coming on to our heating pumps, which are our twin set pumps. And these do have some intelligence. They have electronics on board. So we're supplying power and we're also supplying our 24 volts into the running relay, the common of the running relay, and also the fault relay as well. So pretty self-explanatory, guys. If it's running, then R16 is enabled, which closes this contact here, which brings on that light. And if it's in fault, exactly the same thing happens. R17, again, ignore how it's, if it's normally open, normally closed, but ultimately the same thing happens and it brings on that light, or doesn't bring on that light, depending on how you've got it wired. Now let's have a look at the control of how we're switching these pumps on. So again, it's coming off the safety circuit. So providing we've got safety healthy, like there's no issues, then we can control these pumps. So again, let's go through it in hand first. So it's off, and then we switch it to hand. So hand, and then that 24 volts on the safety circuit goes down to R18, energizes that. R18 is over here, look. So that closes that. And then we've got a 2-position, that feeds into a 2-position switch on the front of the panel. And again, you can see this on the photos, guys. You'll see this, there's a larger plate, and one switch is a 3-position switch, and then the other one is a 2-position switch. So we're now at that 2-position switch, and we can only go one of 2 ways. And doesn't matter how it's drawn, but I've just drawn it going to pump 1 first. So let's go to pump 1, goes down here, over here, and then energizes R19. And then R19 contact is over here. And then this is, again, similar sort of thing. This is our enable signal. So R19 closes, and then you can see here, this is our enable signal. So it's just a little circuit that's sending out a voltage here. And then it's sort of just there waiting until that energizes, R19 energizes, and then that can close and it sends that voltage back. And similar to what we mentioned earlier, it's probably a little relay that then energizes, which then sends a signal on the PCB to bring on the pump, to start running the pump. If we then switch it over to pump 2, so we're now going over and switching to pump 2. Similar thing. We're going down this leg, and then we're energizing 20, and then 20 you can see is mostly on the next page, but we've got the enable bit here. So again, it's just waiting here, then 20 is enabled, so that closes and then sends it back. And then, yeah, basically brings on, allows the second pump to run. So page 6 and 7, that is the control of the first pump set. So there's 2 pumps there. They need their own power supply and controls, but they're sort of built in, they're plumbed into the same pipework, and then you can use them in that duty standby setup. So that is the same setup for the heat emitter circuit set. So pump 1 here of the heat emitter set, and then we got pump 2 over here of the heat emitter set. We've also got this differential pressure switch as well. So this is pretty simple stuff. So we're just coming off that 24 volts, going down here, and then out into the field. And then whatever we set that differential pressure to, providing, so we set it to what it needs to be at, and then providing that it's seeing the right pressure across that pump set, that then closes and then comes back to the panel, energizes relay 23. That closes here, which then brings on that light. And of course, we're doubling that up and sending a signal to the PLC. And this is just basically monitoring the condition of that pump set. You know, filters might be getting blocked over time. And this is just a mechanical electrical way, because if you remember, we've also got analog pressure sensors either side of this pump. But this is like a backup electrical mechanical yes or no, on or off, true or false signal, just to tell us that, you know, there's the right amount of flow or pressure, or there's not. So if that's not there, if that's not on, then there might be a problem. We might, you know, have to investigate. You could also wire this or design this inverted if you wanted to. So rather than having like a flow okay light, you could have, you know, a flow not okay light, and you might have a, rather than a green light, you have a red light that comes on when it's, you know, in a unhealthy condition. So it doesn't really matter. I've done it this way, like flow okay, because that's what the spec told me to do. But I've seen it the other way around as well. And then it's exactly the same for, we look here, the pump ventilation set. So pump 1 here, and then pump 2 over here. Exactly the same thing. PLC, there's not really much to talk through here, guys. Actually, you know what? I'm not, because we did that yesterday, I'm hoping that's pretty fresh with you all, and it's all pretty self-explanatory. But I think let's go to questions based on sort of what I've just been through. Like, has anything come up going through all of that that's not made sense at all? Anyone?
I hear a question.
Yes, mate.
Where are all these relays in cabinet? I don't see on pictures.
Have you got access to the images folder in the drive?
Yes.
Yeah. So
I don't see all these relays.
Okay, let me show you. Oh, no, it's the wrong page. Can you see my screen, guys?
Yeah.
Okay. So new system images, and then I don't know which image it will be. Shit, tell you what. There we go. Those are all the relays. 33 relays. And you can see that they're 2-pole. So this side, actually, I'll try and find a bit of a closer-up picture. I wonder if this is any better. No, not really. Yeah, so you can see this 33. Let's look at 33. You can see it's a 2-pole relay. So we've got A1, A2 over here, and you can't see a cable going into A2 because what I'm using, there's a couple of 0 volts going in, like you'll see a couple of them, but I'm just distributing that 0 volts with little bridge connectors that clip into the relays. So I'm just saving on wiring. But yeah, so we got A1 and A2 this side, and then over on this side, this is pole 2. So we got 1, 2, 3 terminals on pole 2, and then on pole 1, again, we got the same. Terminal 1, 2, 3. So we've got a common. So I think the middle is the common, if I remember correctly. And then we've got the top one that's normally open and the bottom one that's normally closed, just to go into a bit more detail on the relays. Any other questions, guys? Because please tell me if it doesn't. If there's anything that doesn't make sense, guys, let's go through it, and don't worry about looking silly, because we've gone through a lot in 6 days. So if you're not confident with anything, just say, and we go through it again. Like if anything doesn't make sense.
I've got a question, Chris.
Yes, mate.
Is the boilers operate independently? If you want a boiler, both of them to come on, they should come on?
Yeah, so you're controlling them independently. We've got individual control for each boiler. And so we got like, I'll show you. So this is obviously page 1, boiler 1, and then this is, oh sorry, not page 1, but boiler 1 and boiler 2. And you'll see that they've got their individual supply, and also we're looking at the control, the 3 position switch to control. We've got one here for boiler 1 and then one over here for boiler 2. So they can be controlled individually, but when we touched on the spec yesterday and it talked about like the PLC control and the control philosophy, they're actually being controlled pretty much at the same time. So I think if I remember correctly, one triggers and comes on, and then the other one triggers and comes on, and then I think what it said is that this is in automatic control. They sort of rise up and the heat output goes up together. So in answer to your question, Gov, they can be controlled individually, and certainly in manual mode or hand mode, it's individual control. But when they're in auto, it just depends on the PLC programming.
Oh, okay.
Yeah. Any other questions, guys? Don't be shy.
You see on the overload?
Yes.
It actually has to overload before that normally open contact actually closes. You can press the stop button. If you press the stop button, it doesn't actually close the normally open. It actually has to physically overload for that to close. Is that right?
I'll explain this on the images because that'll probably be easier to explain.
Yeah.
Motor control, contacts.
So you see the wee red stop button? If you press that won't actually close the contact, am I right?
So what that does, that just mimics an overload basically. What that does, it only operates this normally closed, it operates the contacts. So
see
it, so it will take this normally closed contact to normally open when you press it, and the normally open to closed when you press it. So ultimately, it's like it's energizing the relay.
Yeah, I think I tried that on an overload, and the normally closed opened 100%, but the normally open didn't close. So I was thinking it maybe actually had to overload for it till physically close.
No, that's how you sort of test the operation. It's like a little test button. So it should so we got the red button up here. So yeah, let's say it's in its normal state. We're not pressing that button.
Yeah.
This is normally open here, and this one's normally closed. And then we press that button, and it just inverts them. So that will then be closed, and this one will go open.
Right.
Sound okay? Or
yeah, no, it sounds all right. It's just whenever I tried it on an overload, it didn't actually work that way. The normally was closed, but the normally open stayed open.
The normally open, so you press that button, and the normally this one, like if you measured, like if you put continuity tester on this pin and this pin,
yeah,
and you then press that red button, you wouldn't get continuity. Is that what you're saying?
No, whenever I went continuity between my normally open, it stayed open, obviously. And then whenever I pressed the red button, it still was open.
Yeah.
So I was thinking it actually had to overload for it to physically change inside. Like it was like a thermal overload as such. It obviously was.
Hang on, you might be onto something here. I'm just trying to remember.
So that's what I think it was like I think there's like a bimetal or like a thermal thing in that. So that normally open didn't actually close. I actually think it has to overload for it to close, if you get me.
There's a reset button and the stop button, two different things. So I've just added in the instruction manual for the overload in the chat.
Yes, yes.
Different states. So if you press the stop button and the reset button at the same time, so if you go down a little bit more, there's 6 different states. There you go.
Right.
If you the stop button and the reset button at the same time, then both contacts will be open.
Perfect.
Right.
100%.
Yeah, that's interesting. Okay, well, thanks.
Just what I call a had one, and I just wanted to, clarify that,
See, mate, it all comes back to reading the fucking manual, RTFM.
Yeah, absolutely.
And as you just seen, I certainly haven't read the manual when it comes to this.
I mean, 8%. No, that's perfect there.
Yeah, nice one. Cheers for that, Daniel. That's taught me something there as well. Appreciate that.
Yeah, same as that there. Cheers.
Cool. Well, there you go. There's the answer to it, guys.
Yeah, perfect. Cheers for that. And cheers for all the 5 days as well. Or 6 days.
That's right, mate. What's your name? I've got P40 Hig at the moment.
Patrick Higgerty, so it is. I think a phone came up there today.
All
But
right,
no, cheers for everything, lad.
Pleasure. Thanks for joining.
Nice.
Any other questions, guys? Are we going to call it a day? Any last debates that we want to have?
Chris, I've just got a basic question. It's just, the numbering for your panel numbers.
Yeah. What numbers? Which ones?
Well, like, your wiring numbers. Like,
okay, yeah. Yep.
How would you determine that number? Is it just down to the designer, or you know what I mean?
Yeah, there's no set way really how to do it. Let me get something up. I'll show you. Yeah, so some if there's some designers are using like a software like ePlan or SolidWorks, like it's all like an automated CAD design system that sort of chooses the numbering for you, and I think it also does the numbering of the cables based on the page as well. So like if you're looking at a cable in a panel and I don't know, it's got like, it starts with a 3, then straight away that I can find that cable straight away if I look on page 3. So that's sort of one way that some designers do it. For me, let me just pull up this because I think it has it written. Just bring up ProgiCAD. Guys, just a little shout out to ProgiCAD. I'm not affiliated with them in any way, but if you want a solid CAD software, this ProgiCAD is really, really worth getting. It's like 200 quid for a lifetime license rather than paying like 100 quid a month for AutoCAD. This ProgiCAD is exactly the same as AutoCAD, and it's just a one-off payment of like 200 quid. So highly recommend ProgiCAD. I've been using them for years. But yeah, this is kind of the standard that I go by, Russell. So all control circuits, like a supply, can't remember exactly what I mean by that. Yeah, control circuits. Yeah, mate, I can't explain it exactly what I mean, but you get an idea. So 200 circuit will be safety circuits. These, I think it depends on the control circuit, on how I'm numbering those. Pressurization, boiler interlock, lamp test circuit, MCBs. So if you look at the MCBs, they start with a 5. So like the first MCB will be 501, second one will be 502, and it will go up like that. Yeah, and PLC circuits 800. So, but it doesn't matter, mate, basically is the answer. It doesn't matter. You could, if you wanted to, just go 1, 2, 3, 4, 5 and just continue up like that. It really doesn't matter.
That's one. Cheers, Chris.
All right, bud. Cool. I'm going to call it a day then, guys. If there's no more questions, I think I'll call it a day. And yeah, just thanks again. It's been really enjoyable. Yeah, having you guys with me, certainly live. So yeah, really appreciate it. Really appreciate the debates. And hopefully you guys have learned something. If there's something that you're struggling with sort of in the future, if you come across something, like, please don't hesitate. Just give me a shout on social, email me, text me, whatever, and I'll do my best to help you guys out. Right, so
when you will start the...
Sorry, mate?
Yeah?
What's that, sorry?
When will you start the software for the KNX?
We're just going to have a quick look now, but we're not doing any training on it. I'm just showing you what it looks like.
Yeah.
Yeah, we're going to have a quick look now. So this is kind of like, so I've got locks on in my house, just playing with the lights at the moment. So this is kind of what it looks like on the front end, like from the app.
Yeah.
But in terms of like the software and the programming software, you can see my screen, right? Guys?
Yeah.
So let's have a look at what it looks like in config. So I've got 3 mini servers. I've got a mini server Go, got one in the workshop, and then I've got one up in the loft, and they're all working together. So I've got like a gateway mini server, which is like the master mini server, and then these 2 mini servers, which is basically, when I say mini server, it's the PLC for Loxon, basically. These 2 are the like the slave PLCs. So yeah, so programming, what it looks like in Loxon, it's function block based in Loxon. So for example, let's just find the study where I'm at. So we got our lighting controller function block. So I'm like sort of taking control through the programming software now. So this is me pretending like pressing the switch, but like using the actual programming software. So that's kind of what you're looking at for lighting. So you've got inputs over here, and then you've got your outputs over here, and it's drag and drop really with Loxon. It's really good for beginners. And then you can like double click into the block, and you can set all your lighting moods and whatnot. It's a similar thing for the heating. And then I've got some custom logic that I've built from scratch sort of down here. So if I want to boost the heating, I've got a little button within the app where I can just press the button and it boosts the heating in just this room for 30 minutes. Similar thing with motion. So if I want, so at the moment, like the lights are being controlled through the motion predominantly. But if I wanted to just switch that off and keep the lights off and not have them come on automatically all the time, I can just disable that. So that's another bit of custom logic that I've built. But that's basically what it looks like in terms of Loxon. And it's the same on all these different pages. It's the same sort of concept. KNX, on the other hand, looks like this. So ETS, let's bring up an old project. So this is what it looks like for KNX, and it's not as intuitive, and I've never even tried to explain it to anyone. So I've not thought about the best way to kind of communicate and train people on it. So I'm not even going to attempt to do that now. But this is kind of what it looks like. And ultimately, how you program KNX modules is through group addresses and group objects. So we've got our device list here. So this is a dimmer. So 230 volt dimmer module, and you can see it's got 4 channels. So this is how we can like dim our standard 230 volt lighting. So if we click into that module, and then these are all the group objects that we've got enabled at the moment. And off these group objects, like we've got a group object for on and off. So if we feed something into this group object, that switches the lights on and off. We've also got status, so that then gives us status back to our system. If it has actually received that signal and it's registered, yes, it is on, or yes, it is off. We got relative dimming or absolute dimming, etc., etc. And then you can determine what functions or what group object are switched on through this parameters tab. So channel 1, so we've got 4 channels. It's a 4-channel dimmer. We go into channel 1. Well, first we've got our general, so we can actually determine what channels are activated. And then once we determine what channels are activated, we can then decide what load type it is, the characteristics of the dimming curve, trailing edge, leading edge, etc., etc. And then we can go into like the configuration of this. This is where like the group objects are sort of determined. So if we go switch on the alarm and then go back to group objects, you can now see that alarm object that we can now use is available. If we go back and switch it off, it's no longer there. So that's within the device, whether it's a device in the panel or like a switch or a motion sensor outside of the panel. It's the same principles. You parameterize it. That's kind of what it's like in KNX. Is you're not necessarily building things using logic. You can get like a separate logic module. Like if you need to do complex things like with pumps in plant rooms, if you're using like what do they call it? A standby. Someone help me out. Something standby. Run and standby. Can't think of the right terminology. So basically, like you'll have two pumps in parallel, and you'll have one running for a week, and then you'll have a switch over so the other one runs. But then, say for example, then like this one say goes into fault, it then automatically switches over to this one. We get a notification that this one's in fault. But then it's like redundancy, especially in like commercial premises, you'll have like a backup pump.
Duty pump? Is it a duty pump?
That's it. Thanks, Mike. Yeah. Duty standby. So you have one running in duty and then you have one in standby and they switch over. So to do something like that's higher level logic that you can't do in KNX. You'd have like a logic controller, which is very similar to what you saw in Loxon, actually. It's more sort of function blocks and you can like create logic from scratch basically, whereas in KNX really you do have some logic functionality, but really what you're doing in KNX is you're parameterizing stuff. So some people find that easier, like you've got a fixed amount of parameters that you can tamper with and that's it really, whereas with Loxon you have to some degree got that. Like if you're using a lighting controller block, so you are fixed to some parameters, but you can also do things from scratch. You can build custom logic from scratch. Yeah, so that's kind of like, so that's what it looks like in terms of the devices in KNX. And then group addresses, this is like then what determines whether, for example, a light comes on or not. And actually, it'll be easier to show you. We go back to the devices. Well, here you go. You can see here. So the group addresses, so so the on and off signal for channel 1 on this dimmer that we're looking at, you can see that the group addresses that switch that on and off are 6150, 002, and 60100. Now, I'm just going to quickly run through this and then I'll leave it at that. So this 6150, that might be like a switch on the wall in that room, in the gym. So that might just be a local switch on the gym wall. So if someone taps that switch, it sends this address to this dimmer channel and switches it on or off. This second address here, that might be like by the front door. So you might have like an all off switch by the front door. And when you tap that switch, it sends this address. And we might also use this address for some of the other dimmers, like for all the other dimmers, because we want all the other lights to turn off as well when we send that address. So it's kind of like KNX in terms of the group addresses. It's a bit like IP addresses, like you're sending out IP addresses and devices are looking on that. It's a bus system as well. So devices are looking constantly for that address. And if it matches up with what's been programmed, then it will react however you're programming it. And then same sort of principle for this other one, but I can't think of an example. Any questions at all on that?
Which one would you likely use for plant room settings and not industrial, but just like AHU plant room settings? What would be your choice of use?
Yeah, I would. So I'm more experienced with Loxon. So it would depend on the application. It would depend on the client, their requirements. But if they didn't specify KNX or Loxon, or I didn't have to use a particular type of device, if I just wanted to do something really quickly, I'd probably use Loxon.
That's good. It's good for like that type of like commercial plant rooms, pumps, and everything else. Yeah.
Yeah, yeah.
Okay.
Both systems can do the same thing. So I'd use Loxon for BMS and KNX for BMS. I've done more BMS specific with KNX though, and that's just because of the company that I was contracting with. They used KNX, and especially when you're in high-end residential, where a lot of people have like Control 4. So like they have Control 4 on the front end. So like rather than the app that I showed you earlier, like they have Control 4 instead. But then to do all like the HVAC control on the back end, they'll have KNX. And you've got a much better integration between Control 4 on the front end and KNX on the back end. Whereas if you the integration between Control 4 and Loxon, it just isn't there. So it does depend on the application and the project. But yeah, if nothing mattered, and for me, just because I'm much quicker with Loxon, I'll just use Loxon.
What do you find with Trend? I mean, most buildings that I've been in is like Trend 965, isn't it?
Yeah. What's my opinion on Trend?
Yeah.
Yeah, I mean it's the go-to one. It's the one that's sort of been around for since God was a boy kind of thing. It's like the traditional BMS system. Problem is it can't do anything that any other system can't do. Like they're all PLC based systems, and like the problem with Trend, and I can't talk from any experience because I've never used it, but from what I sort of gather and what I hear and what I see, is like it's like if you want to be a Trend dealer or installer, you've got to, I think the barrier for entry is really high. You've got to have like a team of 3 engineers, and you've got to be spending 40k on hardware every year to even be, well, you need to be doing that to stay as a Trend installer. And it's quite a closed system, and it's expensive as well. And like when you can use other systems like Loxon, for example, anyone, like you can buy the hardware off the website, you can get the software for free. There's like no barrier to entry, which some people might argue is a bad thing, because I've seen it. I've seen like loads of shit installs out there. But yeah, it's also more affordable to the end client. So I think what you're starting to see is Trend lose market share.
Yeah. I mean, they've got a new update recently. There was on my site, they were talking about updating. I think they've changed the name. I know it's 965, but we had a couple of guys come in talking about updating Trend as such. But I even asked their Trend the engineers that were on there. And like you say, it's like a closed net. You can't really just jump in and have a pop or get some sort of training. It's expensive as well, isn't it? All that stuff, isn't it?
Yeah. There's lots of barriers to entry and hurdles you got to get over with Trend.
Definitely.
I'm going to shoot off, guys, unless anyone's got any burning questions.
No. Thanks a lot, Chris. Cheers.
Cool, guys.
I have one question.
Yeah.
Just a question. What tool do you normally use for your schematics?
What do I use for my schematics? Sorry, what?
What tool do you use to draw the schematic?
Okay, yeah. ProgiCAD or ProjCAD, however it's pronounced. This software here, really good. It's the same capability as AutoCAD, and it's just a one-off cost of 200 quid rather than paying like 100 every month for AutoCAD. It's brilliant. It's really, really good. Been using it for like 5-6 years.
Thank you. Thank you very much.
How long would that have taken you to do these drawings that we're looking at?
So it did because I did it from scratch, because I was using this project for training, I had to do it all from scratch. So it took me quite a while, probably, and if I wasn't doing filming and stuff around it, it would probably take me, I mean, if I'm doing a BMS project, I usually sort of cost in 5 days typically for design and documentation, depending on the size of the project. But like with this that you've seen here, like once you've designed a system, I just recycle a lot of the things that I've already drawn. So, you know, you don't have to draw things from scratch. You just sort of copy and paste it, and you might like build up a little library within your CAD software. And like it's a much quicker process once you've done it a few times. But yeah, 5 days is usually sort of a good amount of time to, because it's not just the design that you're doing. It's not just like drawing in AutoCAD. It's you know, looking through tech manuals. It's calling tech support. It's speaking to other trades. It's all like this admin-y stuff that kind of comes into the design as well.
Yes.
Right, man.
Can I just ask a favour? Sorry. On your drawing, when you've done the contactor and the overload loop, is there any chance of you just doing a scribble and uploading it to the Google place where we can have a look at that? Because, I mean, I know it's a bit, I can probably forget and I sort of remember it, but, you know, most of the drives are all variable drives and shit like that. But is there any chance of you just doing another scribble so I can just remember the overload part? You know, the overload and contactor. When you came back down from the supply, and then you went for the overload on the drawing where it's like it sends a signal down to the contactor.
I'll tell you what, Mike. You do it and you send it to me.
All right.
And then I'll check it.
All right, fair enough, then, mate. Yeah.
And then if once it's all good, I'll upload it for everyone.
Top man. Thank you.
Because then you're learning.
Yeah. Thank you.
Right.
Cheers, mate.
Cheers, guys.
See you.
Bye bye.
Chris, can I ask a question, please? Can you use signal generator for testing BMS testing?
What, sorry?
Signal generator.
Yeah, I've just muted myself.
I don't know what that is, man.
Signal generator, it's a device which can generate a signal, 0 10 volts or 4
Oh, yeah.
Can I use such a device for testing the panels? It's safe, it's okay.
I mean, you'll have to read the manual.
Okay.
But yeah, I mean, I've used
them
before. So yeah, I've used them for testing panels and testing variable frequency drives. Yeah, like a 0 to 10 or 4 to 20 milliamp control signal, like to test things.
Yeah. Okay.
I'll have to log off.
Thank you.
Right, I'm off, guys.